Section 1 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by BettyB. The Theory and Practice of Brewing by Michael COMBRUNE. Section 1. An explanation of the technical terms. The intent of every brewer, when he forms his drink, is to extract the fermentable parts of the malt, in the most perfect manner, to add hops, in such proportion as experience teaches him will preserve and ameliorate the beer, and to employ just so much yeast as is sufficient to obtain a complete fermentation. Perhaps it may be said, these particulars are already sufficiently understood, and that it would be a much more useful work to publish remedies for the imperfections, or diseases, beer is naturally or accidentally subject to, and which at present are deemed incurable. But if the designs just now mentioned be executed according to the rules of chemistry, such imperfections and such diseases not existing, the remedies will not be wanted, for beer brewed upon true principles is, neither naturally nor accidentally, subject to many disorders often perceived in it. Hence it is evident that some knowledge of chemistry is absolutely necessary to complete the brewer, as, without the informations acquired from that science, he must be unqualified to lay down rules for his practice, and to secure to himself the favor of the public, for which purpose, and to make this treatise useful to those concerned in the practical part of brewing, it has been thought advisable to avoid, as much as possible, the technical terms of art, to prefix an explanation of those that necessarily occur, and, in as short a manner as possible, to trace the properties of fire, air, water, and earth, as far as they relate to the subject. Acids are all those things which taste sour, as vinegar, juice of lemons, spirit of nitre, spirit of salt, the oil and spirit of vitriol, etc., and are put in a violent agitation by being mixed with certain earths or the ashes of vegetables. An acid enters more or less into the composition of all plants, and is produced by, or rather is the last effect of, fermentation. Mixed in a due proportion with an alkali, it constitutes a neutral salt, that is, a salt wherein neither the acid nor alkali prevail. Acids are frequently termed acid salts, though generally they appear under a fluid form. Alkalis, or alkaline salts, are of a nature directly contrary to the acids, and generally manifest themselves by effervescing therewith. They have a urinous taste, and are produced from the ashes of vegetables, and by several other means. They, as well as testaceous and calcareous substances, are frequently made use of by coopers, to absorb the acid parts of stale beer, by them called softening. Air is a thin elastic fluid, surrounding the globe of the earth. It is absolutely necessary to the preservation both of animal and vegetable life, and for the exciting and carrying on fermentation. Alcohol is the pure spirit of wine, generally supposed to be without the least particle of water or phlegm. Animals are organized bodies, endued with sensation and life. Minerals are said to grow and increase, plants to grow and live, but animals only to have sensation. Animal substances cannot ferment, so as to produce by themselves a vinous liquor, but there may be cases wherein some of their parts rather help than retard the act of fermentation. Atmosphere is that vast collection of air with which the earth is surrounded to a considerable height. Attraction is an indefinite term, applicable to all actions whereby bodies tend towards one another, whether by virtue of their weight, magnetism, electricity, or any other power. It is not, therefore, the cause determining some bodies to approach one another, that is expressed by the word attraction, but the effect itself. The space through which this power extends is called the sphere of attraction. Blacking is a technical term used by coopers to denote sugar that is calcined until it obtains the color that occasions the name. Brewing is the operation of preparing beers and ales from malt. Boiling may thus be accounted for, the minute particles of fuel being by fire detached from each other, and becoming themselves fire, pass through the pores of the vessel and mix with the fluid. These, being perpetually in an active state, communicate their motion to the water. Hence arises at first a small intestine motion, and from a continued action in the first cause, the effect is increased, and the motion of the liquor continually accelerated. By degrees it becomes sensibly agitated, but the particles of the fire, acting chiefly on the particles that compose the lowest surface of the water, give them an impulse upwards, by rendering them specifically lighter, so as to determine them to ascend, according to the laws of equilibrium. Hence there is a constant flux of water from the bottom to the top of the vessel, and reciprocally from the top to the bottom. This appears to be the reason why water is hot at the top sooner than at the bottom, and why an equal heat cannot be distributed through the whole. The thermometer therefore can be of little service to determine immediately the degree of heat, especially in large vessels, on which account it is better for brewers to heat a certain quantity just to the act of boiling, and to temper it by adding a sufficient quantity of cold water. Boiling water is incapable of receiving any increase of heat, though acted on by ever so great a fire, unless the atmosphere becomes heavier or the vapors of the water be confined. It occasions the mercury to rise, according to Fahrenheit's scale, to 212 degrees. Char. A body is said to be charred when, by fire, its volatile or most active parts are drove out, its coarse oils, by the same means, placed chiefly on the external parts, and so deprived of color as to be quite black. Cleansing is the act of removing the beer from the tun, where it was first fermented, into the casks. Cloudy is an epithet joined to such beers, which, from the violent heat given to the water that brewed them, are loaded with more oils than can be attenuated by fermentation, and incorporated with the water, from whence a muddy and gray oil is seen floating on the surface of the liquor. Though the body is often transparent, this oil is frequently extracted in such quantity as to exceed the power of any known menstruum. Cohesion is that action by which the particles of the same body adhere together as if they were but one. Cold is a relative term in opposition to heat. Its greatest degree is not known, and it is supposed that the colder a body is, the less is the agitation of its internal parts. Color. A greater or less degree of heat causes different colors in most bodies, and from a due observation of the color of malt, we may determine what degree of heat it has been impressed with. Density expresses the closeness, compactness, or near approach of the parts of a body to one another. The more a body weighs in proportion to its bulk, the greater is its density. Gold is the densest body in nature, because there is none known of the same bulk which weighs so much. Earth is that fossil matter or element whereof our globe partly consists. Ebullition is the boiling or bubbling of water or any other liquor, when the fire has forced itself a passage through it. Brewers suppose water to be just beginning to boil, when they perceive a small portion of it forced from the bottom upwards in a right line, so as to disturb the surface. When the liquor is in this state, they call it through, or upon the point of ebullition. The vulgar notion that the water is hotter at this time than when it boils is without any foundation. Effervescence is a sudden agitation arising in certain bodies upon mixing them together. This agitation most commonly generates heat. Elasticity, or springiness, is that property of bodies by which they restore themselves to their former figure, after any pressure or distension. Expansion is the swelling or increase of the bulk of bodies from heat, or any other cause. Extract consists of the parts of a body separated from the rest by cold or hot water. Fermentation is a sensible internal motion of the particles of a mixture, By the continuance of this motion, the particles are gradually removed from their former situation, and, after some visible separation, joined together again in a different order and arrangement, so as to constitute a new compound. No liquors are capable of inebriating except those that have been fermented. Fixed bodies are those which, consisting of grosser parts, cohering by a strong attraction, and by that means less susceptible of agitation, can neither be separated nor raised without a strong heat, or perhaps not without fermentation. Fire is only known by its properties, of which the chief are to penetrate and dilate all solid and fluid bodies. Freezing point is the degree of cold at which water begins to be formed into ice, which, according to Fahrenheit's scale, is expressed by 32. Foxed is a technical term, used by brewers to indicate beers in a putrid state. Gums are concreted vegetable juices which transude through the bark of certain trees and harden upon the surface. They easily dissolve in water, and by that means distinguish themselves from balsams or resins. Hermetically sealed is a particular method of stopping the mouth of vessels so close that the most subtle spirit cannot fly out, which is done by heating the neck of the bottles till it is just ready to melt, and then with hot pincers twisting it close together. Homogeneous is an appellation given to such parts or subjects which are similar or of the same nature and properties. Isinglass is a preparation from a fish called huso, somewhat bigger than the sturgeon, a solution of which in stale beer is used to fine or precipitate other beers. It is imported from Russia by the Dutch, and from them to us. Light consists of particles of matter inconceivably small, capable of exciting in us the sensation of colors by being reflected from every point of the surface of luminous bodies, but, notwithstanding they are so exceedingly small, Sir Isaac Newton found means to divide a single ray into 7 distinct parts, viz., red, orange, yellow, green, blue, indigo, and violet. Malt, in general, is any sort of grain, first germinated and then dried so as to prevent any future vegetation. That generally used is made of barley, which experience has found to be the fittest for the purpose of brewing. Medium is that space through which a body in motion passes. Air is the medium through which the bodies near the earth move. Water is the medium wherein fish live. Glass affords a medium or a free passage to light. This term is also made use of to express the meaning of 2 numbers, and sometimes the middle between several quantities. Musts are the unfermented juices of grapes, or of any other vegetable substances. Menstruum is any fluid which is capable of interposing its parts between those of other bodies, and in this manner either dissolves them perfectly or extracts some part of them. Oil is an unctuous, inflammable substance drawn from several animal and vegetable substances. Precipitation. Isinglass dissolved becomes a glutinous and heavy body. This put into malt liquors intended to be fined carries down, by its weight, all those swimming particles which prevent its transparency, and this act is called fining or precipitation. Repulsion. Dr. Knight defines it to be that cause which makes bodies mutually endeavor to recede from each other, with different forces at different times. In this case they are placed beyond the sphere of each other's attraction or cohesion, and mutually fly from each other. Resins, or balsams, are the oils of vegetables inspissated and combined with a proportion of the acid salts, as well as they mix with any spirituous liquor. As little are they soluble in water, but they become so either by the intervention of gums or soaps, or by the attenuating virtue of fermentation. Salts are substances sharp and pungent, which readily dissolve in water, and from thence, by evaporation, crystallize and appear in a solid form. They easily unite together and form different compounds. Thus salts, composed of acids and alkalis, partake of both and are called neutral. Set, A grist of malt is by brewers said to be set, when, instead of separating for extraction, it runs in clods, increases in heat, and coagulates. This accident is owing to the over quantity of fire in the water applied to any of the extractions. The air included in the grist, which is a principal agent in resolving the malt, being thereby expelled, the mass remains inert, and its parts, adhering too closely together, are with difficulty separated. Though an immediate application of more cold water to the grist is the only remedy, yet, as the cohesion is speedy and strong, it seldom takes effect. New malts, which have not yet lost the heat they receive from the kiln, are most apt to lead the brewer into this error, and generally in the first part of the process. Sugar, or saccharine salts, are properly those that come from the sugar canes. Many plants, fruits, and grains give sweet juices reducible to the same form. They are supposed to be acids smoothed over with oils. All vegetable sweets are capable of fermenting spontaneously when crude. If boiled, they require an addition of yeast to make them perform that act. Malt, or its extracts, have all the properties of saccharine salts. Sulfur. Though by sulfur is commonly understood the mineral substance called brimstone, yet in chemistry it is frequently used to signify in general any oily substance, inflammable by fire, and, without some saline addition, indissoluble in water. Soap, or saponaceous juices. Common soap is made of oil mixed with alkaline salts. This mixture causes a froth on being agitated in water. The oils of vegetables are, in some degree, mixed with their salts, and according to the nature of these salts, appear either resinous or saponaceous, that is, soluble or indissoluble in water. Sugar is a kind of soap, rendering oil miscible with water, and therefore all bodies from which saccharine salts are extracted may be termed saponaceous. Vegetable is a term applied to plants considered as capable of growth, having vessels and parts for this purpose, but generally supposed to be without sensation. Vinegar is an acid penetrating liquor, prepared from wine, beer, cider, or a must, which has been fermented as far as it was capable. Vitriol is, in general, a metalline substance combined with the strongest acid salt known. This acid, being separated from the metal, differs in nothing from that which is extracted from alum or brimstone. It is improperly called spirit of vitriol when diluted with water, and, with as little propriety, oil when free from it. Volatile bodies are those which, either from their smallness or their form, do not cohere very strongly together, and being most susceptible of these agitations, which keep liquors in a fluid state, are most easily separated and rarefied into vapor with a gentle heat, and on the contrary condensed and brought down with cold. Wine is a brisk, agreeable, spirituous, fluid cordial, formed from fermented vegetable bodies. In this sense beers and ales may be called, and really are, barley wines. Worts are the unfermented extracts of malt. Yeast is both the flowers and lees of a fermented wort, the former of these being elastic air enveloped in a subject less strong and less consistent than the latter. End of section 1.
Section 2 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gren. The Theory and Practice of Brewing by Michael COMBRUNE. Section 2 of Fire. Though fire is the chief cause and principle of almost every change in bodies, and though persons untaught in chemistry imagine they understand its nature, yet certain it is few subjects are so incomprehensible or elude so much our nicest research. The senses are very inadequate judges of it. The eye may be deceived, and suppose no fire in a bar of iron because it does not appear red, though at the same time it may contain enough to generate pain. The touch is equally unfaithful, for a body containing numberless particles of heat will to us feel cold if it is much more so than ourselves. The great and fundamental differences among philosophers in respect to the nature of fire is, whether it be originally such, formed by the Creator himself at the beginning of things, or whether it be mechanically producible in bodies, inducing some alteration in particles thereof. It is certain that heat may be generated in a body by attrition, but whether it existed there before, or was caused immediately by the motion, is a matter of no great import to the art of brewing, for the effects with which we are alone concerned are the same. Fire expands all bodies, both solid and fluid. If an iron rod just capable of passing through a ring of the same metal is heated red hot, it will be increased in length and so much swelled as not to be able to pass through the ring as before. If a fluid is put into a long-bellied glass with a long slender neck and properly marked, the fluid by being heated will manifestly rise to a considerable height. The expansion of fluids by heat is different in different fluids. With some exceptions, it may be said to be in proportion to their density. Pure rainwater, gradually heated to ebullition, is expanded 1/26th part of its bulk, so that 27 gallons of boiling water will, when cold, measure no more than 26, and 27 gallons of boiling wort will not yield so much, because worts contain many oily particles, which, though less dense than water, have the property of being more expansible. Hence we see the reason why a copper containing a given number of barrels of wort, when cold, is not capable to hold the same of beer when boiling. Bodies are weakened or loosened in their texture by fire. The hardest, by an increased degree of heat, will liquefy and run, and vegetables are resolved and separated by it into their constituent parts. It must be owned, vegetables seem at first, on being exposed to the fire, to become rigid or stiff, but this is owing to the evaporation of the aqueous particles, which prevented a closer adhesion of the solid matter. It is only in this manner fire strengthens some bodies which before were weak. That the texture of bodies should be loosened by fire seems a consequence of expansion, for a body cannot be expanded but by its particles receding farther from one another, and if these be not able to regain the situation they had when cold, the body will remain looser in its texture than before it suffered the action of fire. This is the case of barley when malted. Fire may be conveyed through most bodies, as air, water, ashes, sand, etc. The effect seems to be different according to the different conveyance. A difference appears between boiling and roasting, yet they answer the same purpose, that of preserving the subject, and this in proportion to the degree of heat it has suffered. A similar variety appears, even to our taste, from the different conveyance of fire to malt. For acids having a greater tendency to unite with water, if this element does not naturally contain any itself, is the reason why a great heat is conveyed through water and applied to extract the virtues of pale malt. The water gaining from the grain some of these salts, or possessing them itself, the effect of this great aqueous heat is not to imprint on the palate a nauseous burnt taste, as is the case of great heats, when conveyed through air to the same grain. The salts the water has obtained, or perhaps had, being sheathed by the oils it draws from the malt, rather become saccharine, which cannot be the case when oils are acted upon by a strong heat, entirely void of any such property. But malt, the more it is dried, the longer is it capable of maintaining itself in a sound state, and the liquor brewed with it will, in proportion to its dryness, keep the longer sound the hotter the water is, applied to malt, provided its heat doth not exceed the highest extracted degree, the more durable and sound will the extract be. The last consideration of fire or heat, relative to brewing, is the knowledge of its different degrees, and how to regulate them. Till of late, chemists and all others were much to seek in this respect. They distinguished more or less fire in a very vague and indeterminate manner, as the first, second, third, and fourth degree of heat, meaning no precise heat or heat measured by any standard. But by the invention of the thermometer, we are enabled to regulate our fires with the utmost precision. Thermometers are formed on different scales, and therefore, when any degree of heat is mentioned, in order to avoid confusion, the scale made use of should be indicated. I have constantly employed Fahrenheit, as it is the most perfect and the most generally received. According to this instrument, by the author of it, an artificial cold was made so as the mercury stood at 72 divisions below the first frost. The gentleman of the French Academy, in the winter of the year 1736, observed at Torneo, latitude 65 degrees 51 minutes, the natural cold to be 33 degrees below zero. These are proofs there are colds much more intense than the first frost, or 32 degrees, where water first begins to harden into ice. From 32 to 90 degrees are the limits of vegetation, according to the different plants that receive those or the intermediate heats. The 40th degree is marked by Boerhaave as having the first fermentable heat, and the 80th as the last. 47 degrees I have found to be generally the medium heat of London throughout the year in the shade. 98 degrees is said to be that of our bodies when in health, as from 105 to 112 are its degrees when in a fever. Hay, stacked with too much moisture when turned quite black in the heart of the rick, indicated a heat of 165 degrees. At 175, the purest and highest rectified spirits of wine boil, and at this degree I have found well-grown malts to char. At 212 degrees, water boils. At 600, quicksilver and oil of vitriol. Gold, silver, iron, and most other metals in fusion exceed this heat. Greater still than any known is the fire in the focus of the burning lens of Tschirnhausen, or of the concave mirror made by Villette. They are said to volatilize metals and vitrify bricks. Thus far experiments have reached, but how much more, or how much less, the power of this element extends, will probably be forever hid from mankind. End of section 2.
Section 3 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording by Peter Musgrove. The Theory and Practice of Brewing by Michael COMBRUNE. Section 3 of the Nature of Air. None of the operations, either of nature or art, can be carried on without the action or assistance of air. It is a principal agent in fermentation, and therefore brewers ought to be well acquainted with its principal properties and powers. By air we mean a fluid, scarcely perceptible to our senses, and discovering itself only by the resistance it makes to bodies. We find it everywhere incumbent on the surface of the globe, rising to a considerable height, and commonly known by the name of atmosphere. The weight of air is to that of water as 1 to 850, and its gravitating force equal to that of a column of water of 33 feet high, so that an area of 1 foot square receives, from air, a pressure equal to 2,080 pounds weight. Elasticity is a property belonging only to this element. We scarcely find this element, any more than the others, in a pure state. 1,000th part of common air, says Boerhaave, consists of aqueous, spirituous, oily, saline, and other particles scattered through it. These are not, or but little, compressible, and in general prevent fermentation. Consequently, where the air is purest, fermentation is best carried on. The same author suspects that the ultimate particles of air cohere together, so as not easily to insinuate themselves into the smallest pores, either of solids or fluids. Hence, those acquainted with brewing easily account why very hot water, which forces strong and pingous particles from the malt, forms at the same time extracts unfavourable for fermentation, as oils are an obstruction to the free entrance of air, And, from an analogous reason, extracts which are much less impressed with fire, in them fermentation is so much accelerated that the whole soon becomes sour. Air, like other bodies, is expanded and rarefied by heat, and exerts its elasticity in proportion to the number of degrees of fire it has received. The hotter therefore the season is, the more active and violent will the fermentation be. Air abounds with water, and is perpetually penetrating and insinuating itself into everything capable of receiving it. Its weight, or gravitating force, must necessarily produce numberless effects. The water contained in the air is rendered more active by its motion, hence the saline, gummus, and saponaceous particle it meets with are loosened in their texture, and, in some degree, dissolved. As principles similar to these are the chief constituent parts of malt, the reason is obvious why such, which are old, or have lain a proper time exposed to the influence of the air, dissolve more readily, or, in other words, yield a more copious extract than others. All bodies in a passive state, remaining a sufficient time in the same place, become of the same degree of heat with the air itself. On this account, the water lying in the backs used by brewers is nearly of the same degree of heat as the thermometer shows the open air in the shade to be. When this instrument indicates a cold below the freezing point, or 32 degrees, if the water does not then become ice, the reason is because it has not been exposed long enough to be thoroughly affected by such a cold. For water does not immediately assume the same degree of temperature with the air, principally on account of its density. Also, from its being pumped out of the deep and hot wells, from it being kept in motion, and from many other incidents. Under these circumstances, no great error can arise to estimate its heat equal to 35 degrees. Air is not easily expelled from bodies, either solid or fluid. Water requires 2 hours boiling to be discharged of the greatest part of its air. That it may be thus expelled by heat appears from thence. Water, if boiled the space above mentioned, instead of having any air bubbles when it is froze, as ice commonly has, becomes a solid mass like crystal. Worts or musts, as they contain great quantities of salts and oils, require a greater degree of heat to make them boil. Consequently, more air is expelled from boiling worts than from boiling water in the same time. And as air doth not instantaneously re-enter those bodies, when cold, they would never ferment of themselves. Were it not for the substitute of yeast to supply the deficiency of air lost by boiling, they would fox or putrefy, for want of that internal elastic air, which is absolutely necessary to fermentation. As air joined to water contributes so powerfully to render that fluid more active, that water which has endured the fire the least time, provided it be hot enough, will make the strongest extracts. Though there is air in every fluid, it differs in quantity in different fluids, so that no rule can be laid down for the quantity of air which worts should contain. Probably the quantity sufficient to saturate one sort will not be adequate proportion for another. Air in this manner encompasses, is in contact with, confines, and compresses all bodies. It insinuates itself into their penetrable passages, exerts all its power either on solids or fluids, and in finding bodies some elements to which it has a tendency, unites with them. By its weight and perpetual motion, it strongly agitates those parts of the bodies in which it is contained, rubs, and intermixes with them intimately together. By disuniting some and joining others, it produces very singular effects not easily accomplished by any other means. That this element has such surprising powers is evident from the following experiment. Fermentable parts duly prepared and disposed of in the vacuum of Mr. Boyle's air pump will not ferment, though acted on by a proper heat, but, discharging their air, remain unchanged. End of section 3. This recording by Peter Musgrove.
Section 4 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Christina Clark. Section 4 of Water. As water is perpetually an object of our senses, and made use of for most of the purposes of life, it might be imagined the nature of this element was perfectly understood, but they who have inquired into it with the greatest care find it very difficult to form a just idea of it. One reason of this difficulty is water is not easily separated from other bodies, or other bodies from water. Hartshorn, after having been long dried, resists a fire more than iron, yet on distillation yields much water. I have already observed that air is intimately mixed with and possibly never entirely separated from it, but in a vacuum. How is it possible then ever to obtain water perfectly pure? In its most perfect state, we understand it to be a liquor very fluid, inodorous, insipid, pellucid and colourless, which in a certain degree of cold freezes into a brittle, hard, glassy ice. Lightness is reckoned a perfection in water, that which weighs less being in general the purest. Hence the great difficulty of determining the standard weight it should have. Fountain, river or well waters, by their admixture with saline, earthy, sulphurous and vitriolic substances, are rendered much heavier than in their natural state. On the other hand, an increase of heat or an addition of air by varying the expansion diminishes the weight of water. A pint of rainwater, supposed to be the purest, is said to weigh 15 ounces, 1 dram and 50 grains, but, for the reasons just now mentioned, this must differ in proportion as the seasons of the year do from each other. Another property of water, which it has in common with other liquors, is its fluidity, which is so great that a very small degree of heat above the freezing point makes it evaporate. Experiments to ascertain the proportion steamed away of the quantity of water used in brewing is an object worthy of the artist's curiosity, but the purer the water is, the more readily it evaporates. Seawater, which is supposed to contain 1/40th part of salt, more forcibly resists the power of fire and wastes much less than that which is pure. The ultimate particles of this element Boerhaave believed to be much less than those of air, as water passes through the pores and interstices of wood, which never transmit the least elastic air, nor is there, says he, any known fluid, fire excepted, which forces itself through every subject, whose parts are more penetrating than those of water. Yet as water is not a universal dissolver, there are vessels which will contain it, though they will let pass even the thick syrup of sugar, for sugar makes its way by dissolving the tenacious and oily substance of the wood, which water cannot do. Water, when fully saturated by fire, is said to boil, and by the impulse of that element comes under a strong ebullition. Just before this violent agitation takes place, I have already observed it occupies 1/76th more space than when cold, so the brewer who would be exact when he intends to reduce his liquor to a certain degree of heat must allow for this expansion, abating therefrom the quantity of steam exhaled. As water by boiling may be said to be filled or saturated with fire, so may it be with any other substance capable of being dissolved therein, but though it will dissolve only a given quantity of any particular substance, it may at the same time take in a certain proportion of some other. 4 ounces of pure rainwater will melt but 1 ounce of common salt, and after taking this as the utmost of its quantity, it will still receive 2 scruples of another kind of salt, viz. Nitre. In like manner, the strongest extract of malt is capable of receiving the properties belonging to hops, but in a limited proportion. This appears from the thin, bitter pellicle that often swims on the surface of the first wort of brown beers, which commonly are overcharged with hops by putting the whole quantity of them at first therein, the wort not being capable of suspending all that the heat dissolves. It no sooner cools but these parts rise on the top. This may serve as a hint to prevent this error, by suffering the first wort to have no more hops boiled therein than it can sustain. But as this incident must vary in proportion to the heat of the extracts and quantity of water used, some few experiments are necessary to indicate the due proportion for the several sorts of drink. This, however, should always be extended to the utmost for the first wort, which, from its nature and constituent parts, stands most in need of the preservative quality the hops impart. Water acts very differently as a menstruum according to the quantity of fire it contains. Consequently, its heat is a point of the utmost importance with regard to brewing, and should be properly varied according to the dryness and nature of the malt, according as it is applied either in the first or last mashes, and in proportion also to the time the beer is intended to be kept. These ends, we hope to show, are to be obtained to a degree of numerical certitude. Nutrition cannot be carried on without water, though likely water itself is not the matter of nourishment, but only the vehicle. Water is as necessary to fermentation as heat or air. The farmer, who stacks his hay or corn before it is sufficiently dried, soon experiences the terrible effects of too much moisture or water residing therein. All vegetables, therefore, intended to be long kept ought to be well dried. The brewer should carefully avoid purchasing hops that are slack-bagged or kept in a moist place, or malt that has been sprinkled with water soon after it was taken from the kiln. By means of the moisture, an internal agitation is raised in the corn, which agitation, though soon stopped for want of a sufficient quantity of air, yet the heat thereby generated remaining, every adventitious seed fallen from the air and resting on the corn begins to grow, and forms a moss which dies and leaves a putrid musty taste behind, always prevailing, more or less, in beer made from such grain. That water is by no means a universal solvent, as some people have believed, has been already observed. It certainly does not act as such on metals, gems, stones, and many other substances. It is not in itself capable of dissolving oils, but is miscible with highly rectified spirits of wine or alcohol, which is the purest vegetable oil in nature. All saponaceous bodies, whether artificial or natural, fixed or volatile, readily melt therein, and as many parts of the malt are dissoluble in it, they must either be or become by heat of the nature of soap, that is, equally miscible with oils and water. When a saponaceous substance is dissolved in water, it lathers, froths, and bears a head. Hence, in extracts of malt, we find these signs in the underback. Weak and slack liquors, which contain the salts of the malt without a sufficient quantity of the oils, yield no froth. Somewhat like this happens when the water from the extract is overheated, for then as more oils are extracted than are sufficient to balance the salts, the extract comes down as before with little or no froth or head. This sameness of appearance, from two causes directly opposite to each other, has many times misled the artist, and shows the necessity there is to employ means less liable to error. This might be a proper place to observe the difference between rains, spring, river, and pond waters, but as the art of brewing is very little affected by the difference of waters, if they be equally soft, but rather depends on the due regulation of heat, and as soft waters are found in most places, and become more alike when heated to the degree necessary to form extracts from malt, it is evident that any sort of beer or ale may be brewed with equal success where malt and hops can be procured proper for the respective purposes. If hitherto prejudice and interest have appropriated to some places a reputation for particular sort of drinks, it has arose from hence. The principles of the art being totally unknown, the event depended on experience only, and lucky combinations were more frequent where the greatest practice was. Thus, for want of knowing the true reason of the different properties observed in the several drinks, the cause of their excellencies or defects was ignorantly attributed to the water made use of, and the inhabitants of particular places soon found an advantage in availing themselves of this local reputation. But just and true principles, followed by as just a practice, must render the art more universal, and add dignity to the profession, by establishing the merit of our barley wines on knowledge, not on opinion void of judgment. To place this truth in a fuller light, and to communicate to the brewer the readiest means to examine any waters he may have occasion to use, I have extracted from Dr. Lucas's essay on waters the experiments he made on the Thames, New River and Hampstead Company's waters, but without closely adhering to the accuracy this gentleman prescribed to himself, such exactness much better suiting a man of his abilities. For the purposes of brewing, it is not of absolute necessity. Experiments on the Thames, New River and Hampstead waters, which in general are in use in the cities of London and Westminster. Thames Somerset House. Quantity of insoluble matter in 1 pint, 1 grain and a half. New River. Quantity of insoluble matter in 1 pint, 1 grain and a half. Hampstead. In 24 hours discharges air, lets some light sediment fall and grows clearer. Thames. Quantity of water used 2 ounces. New River. Quantity of water used 2 ounces. Hampstead. Quantity of water used 2 ounces. Subject employed. Infusion of Campeche wood to a dark orange. Thames, a pink colour heightened to crimson. Inference from the experiment on Thames water: a calcareous earth dissolved in a marine acid, perhaps something of a volatile alkali, whence the water appears unfit for the scarlet dye. In the New River, a paler pink, but heightens as Thames. In Hampstead, a pink bloom, upon standing heightens, after fades, and comes to the colour of old canary wine. Subject employed: 1 grain of cochineal in powder. In the Thames, a pink bloom heightens to crimson, fades to a pale muddy purple, letting fall obscure green clouds. Inference from experiment on Thames water confirms the preceding experiment. The New River water, the same as Thames water. Hampstead water, a very beautiful crimson, heightens upon standing, in 12 hours suffers no diminution of colour. Subjects employed: alkaline lye, 5 drops. In the Thames water, slight milky cloud, becomes milky all over, a light sediment of pale earth coats the glass and is found at bottom. Inference from experiment on Thames water: charged with terrene parts, dissolved by means of an acid, at high water more acid in the water than at low, and the alkaline principle in this river more at low water than at high. New River water, less milky with less sediment. Hampstead water, of alkaline lye used 10 drops, worked no sensible change in this water. Subject employed: solution of soap. In the Thames water, a pearl-coloured milkiness, but no coagulation. Inference from this test on Thames water confirms the former observation. New River water, less milky, no coagulation. Hampstead water, mixes smoothly and causes a slight lactescence. Subject employed: a diluted acid of vitriol. Thames water, no perceptible change. Inference from experiment on Thames water shows an alkali not predominant. New River water, no sensible change. Hampstead water, upon standing shows some air bubbles and seems somewhat brighter. Subjects employed: mercury sublimate dissolved in pure water, 10 drops. Thames water, no change. Upon standing, a mother of pearl coloured pellicle covered the surface, the liquor beneath slightly milky. Inference from experiment on Thames water: the quantity of alkali inconsiderable. New River water, the same appearance as Thames, rather slighter precipitation. Hampstead water, the same appearance, but rather slighter than any of the other two. Subject employed: a solution of mercury in the acid of nitra. Thames water, pale clouds of every drop, first white and milky, then yellowish, 4 drops more got the same colour all over. Upon standing, a slight pale pellicle arose, and a muddy ochre-coloured sediment subsided. Inference from the experiment on Thames water shows some absorbent earth by means of an acid suspended in the water. New River water, the same as Thames but slighter. Hampstead water, upon dropping no change appears, upon standing grows milky, then to a pale yellow, with a slight pearl-coloured pellicle, shows no air nor sediment, the glass slightly coated upon standing, precipitated fairly. Subject employed, a solution of lead in distilled vinegar, at every drop as far as 4 drops. On the Thames water, a bright milky cloud, which growing more opaque and white, subsided upon being stirred, had a milky opacity all over, upon standing threw up a pale pellicle, and let fall white precipitate. Inference from this experiment on Thames water confirms the preceding observation. On the New River water, the same as Thames, but in a lower degree. On the Hampstead water, the same as New River. Subject employed, a solution of silver in the acid of nitra, 4 drops. On the Thames water, caused a pearled milkiness, upon standing subsided, a violet-purple colour precipitate. Inference from the experiment on Thames water shows some portion of sea salt, of which the Thames has more at high water than at low. On the New River water, the same effects but slighter, the precipitate of pale violet colour. Hampstead water, pale bluish-white clouds, the precipitate a bluish slate colour, thinly covered the sides and bottom of the glass. All these waters appear to be sufficiently pure for the common use of life. The difference between them is very trivial, if any. Those of Hampstead approach nearest to the simple state this element is to be wished for. Although it cannot be said to have an immediate relation to this work, yet it may not, perhaps, be disagreeable or useless here to add the quantities of water the cities of London and Westminster and the adjacent buildings are daily supplied with. From the New River Company, 57,897 tons per day. London Bridge, 8,500. Chelsea, 1,740. Hampstead, 1,200. York Buildings, 849. Hartshorn Lane, 205. 70,391 tons required every 24 hours. End of section 4.
Section 5 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Foon. The Theory and Practice of Brewing by Michael COMBRUNE. Section 5 of Earth. Regularity requires some notice should be taken of this element. The great writer on chemistry, so often mentioned, defines it to be a simple, hard, friable, fossil body fixed in the fire, but not melting in it, nor soluble in water, air, alcohol, or oil. These are the characters of pure earth, which, no more than any of the other elements, comes within our reach, free from admixture. Though it is one of the component parts of all vegetables, yet as, designedly, it is never made use of in brewing, except sometimes for the purpose of precipitation. It is unnecessary to say anything more upon it. Whoever desires to be farther informed concerning its properties may consult all or any of the authors before mentioned. End of section 5. Section 6 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Foon. The Theory and Practice of Brewing by Michael COMBRUNE. Section 6 of Menstruums or Dissolvents. By menstruums is understood a body which, in a fluid or subtilized state, is capable of interposing its small parts betwixt the small parts of other bodies. This act so obviously relates to the art of brewing, especially where the extracting of the malt and the boiling of the hops are concerned, that it should not be passed unheeded by. The doctrine of menstruums, as laid down by Boerhaave, seems most intelligible and applicable to our purpose. He says, the solutions of bodies in general are the effect only of attraction and repulsion between the particles of the menstruums and those of the body dissolved, the whole action depending on the relation between these two. Of consequence, there cannot be any body, natural or artificial, which, without distinction, will dissolve all bodies whatsoever, nor is the cause assignable why certain menstruums dissolve certain bodies. The effects of alkaline, acid, neutral, fixed, or volatile salts, any more than those of oils, water, alcohol, fire, or air, are not to be accounted for by any general rule that universally holds true, nor even in many cases doth the dissolution of a body depend on the purity or simplicity of the menstruum. The nearest path then to success is cautiously to apply every menstruum we know of to the body whose solvent we want to discover. The elements of fire and air greatly promote the action and effect of menstruums, and in this light they are admitted as such. Water dissolves most salts, all the natural saples of plants, and the ripe juices of fruits. For in these, the oils, salts, and spirit of the vegetables are accurately mixed and concreted together, and malts having the same constituent parts with them, this element becomes a proper menstruum to extract this grain, though malts, by being dried with heats which greatly exceed what is necessary to bring barley to a state of maturity, do, from hence, require greater though determinate heats, yet inferior to that at which water boils. But such heats must be applied in proportion to their dryness, to extract their necessary parts. Even earths, by the intervention of acids, dissolve in water. But having treated of the 4 elements already, as far as we conceived was requisite for the art of brewing, we shall, in this chapter, confine ourselves to oils and salts, and view these acting as menstruums only. To the definition already given of oils, it may be necessary to add, in general, they contain some water and a volatile acid salt, that they receive different applications and have different properties in proportion to their respective spicitudes. Oils from vegetables are obtained by expression, infusion, and distillation, in either of which methods a too great heat is to be avoided, as this gives them a prejudicial rancidness, and where water does not interpose, alters their colour until thereby they are turned black. In general, oils unite with themselves, but, excepting alcohol, not with water, unless when combined with salts, for salts attract water, and so they do oils. Hence arises many elegant preparations both natural and artificial, from which wines are formed. The power of oils in dissolving bodies is in a proportion to their heat, and being capable, when pure, of receiving a quantity of fire equal to 600 degrees, it is not surprising this liquid should mix with gums and with resinous bodies. But the colour of these, and of every subject when thrown into boiling oils, changes in proportion to the impression made on them by heat, either to a yellow, a red, or a black. Oils which are inspissated or thickened by heat are termed balsams. Do not the oils of malt, from the heat they have undergone, resemble these, and from the circumstance of their having endured a heat superior to that necessary for putrefaction, may they not be suspected to possess a volatile alkaline salt? Beyond doubt, the extracts from malt, though they boil at a heat of 218 degrees only, yet do they, in great measure, dissolve hops, which are gum resinous. Salt may well be denominated a menstruum, as it is easily diluted with water. Fixed alkaline salts we have already seen appear to be the produce of fire alone. Such are never distinguished in the composition of vegetables in their natural state, though a volatile alkalious salt, the effect of heat equal or superior to that necessary for putrefaction, is found in many, and especially in such as are putrefied. The power of a fixed alkali as a solvent is great, applied, says Boerhaave, to animal, vegetable, or fossil concretions, so far as they are oils, balsams, gummy, resinous, or of gummy resinous nature, and therefore concreted from oily substances. These this salt intimately opens, attenuates, and resolves, disposing them to be perfectly miscible with water, oils of alcohol leaving however the impression of taste naturally belonging to this salt. Vegetable acid salt dissolves animal, vegetable, fossil, and methylene substances, except mercury, silver, and gold. In most terrestrial vegetables this salt is evident. Ripe, mealy corn has the least indication of it, yet extracts therefrom, when fermented, and sometimes before they are fermented, discover sensibly their acidity. Sea plants in general have not their roots inserted in the earth at the bottom of the sea, and these in distillation yield an oily volatile alkali. But more subtle than the native acids of vegetables are the vinous acids produced by fermentation. They dissolve equally most matters put into them, and render the whole homogeneous. Into a must or wort, when under this act, by means of an aleosaccharum, might be introduced the choicest flavors, and the aromatics of the Indies be applied to heighten the taste and flavor of our barley wines. The laws of England at present subsisting are indeed opposite to any improvement of this sort, from the apprehension of abuse. But where elegance alone is intended, undoubtedly the merit of our beers and ales might thereby be increased. As such, this is a part of chemical knowledge well worth the enquiry and attention of the brewer. Neutral salts have already been mentioned. These are very various, and very different when acting as menstruums. Resins and gum resins are generally said to be most effectually dissolved by alcohol, but Boerhaave informs us that sal ammoniac, a very salutary subject and a neutral salt, if boiled with gums, resins, or the gum resins of vegetables, intimately resolves and disposes them to be conveniently mixed in aqueous and fermenting spirituous menstruums. Of this class of salts thus much is sufficient. This observation perhaps is of too much consequence to escape the notice of the artist. End of section 6.
Section 7 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 7 of the Thermometer. This instrument is designed for measuring the increase or decrease of heat. By doing it numerically, it fixes in our minds the quantity of fire, which any subject, at any time, is impregnated with. If different bodies are brought together, though each possesses a different degree of heat, it teaches us to discover what degree of heat they will arrive at when thoroughly mixed, supposing effervescence to produce no alteration in the mixture. The inventor of this admirable instrument is not certainly known, though the merit of the discovery has been ascribed to several great men of different nations, in order to do them and their countries honor. It came to us from Italy about the beginning of the 16th century. The first inventors were far from bringing this instrument to its present degree of perfection. As it was not then hermetically sealed, the contained fluid was, at the same time, influenced by the weight of the air and by the expansion of heat. The Academy of Florence added this improvement to their thermometers, which soon made them more generally received. But, as the highest degree of heat of the instrument constructed by the Florentine gentlemen was fixed by the action of the strongest rays of the sun in their country, this vague determination, varying in almost every place, and the want of a fixed universal scale, rendered all the observations made with such thermometers of little use to us. Boyle, Halley, Newton, and several other great men thought this instrument highly worthy of their attention. They endeavored to fix two invariable points to reckon from, and by means of these to establish a proper division. Monsieur de Amatons is said to have first made use of the degree of boiling water for graduating his mercurial thermometers. Fahrenheit, indeed, found the pressure of the air in its greatest latitude would cause a variation of 6 degrees at that point. He therefore concluded a thermometer made at the time when the air is in its middle state might be sufficiently exact for almost every purpose. Long before the heat of boiling water was settled as a permanent degree, many means were proposed to determine another. The degree of temperature in a deep cave or cellar, where no external air could reach, was imagined by many a proper one. But what that degree truly was, and whether it was fixed and universal, was found too difficult to be determined. At last the freezing point of water was thought of, and although some doubts arose, with Dr. Haley and others, whether water constantly froze at the same degree of cold, Dr. Martin has since, by several experiments, proved this to be beyond all doubt, and this degree is now received for as fixed a point as that of boiling water. These 2 degrees being thus determined, the next business was the division of the intermediate space on some scale that could be generally received. Though there seemed to be no difficulty in this, philosophers of different countries had not been uniform in their determinations, and that which is used in the thermometer at present, the most common, and in other respects the most perfect, is far from being the simplest. The liquid wherewith thermometers were to be filled became the object of another inquiry. Sir Isaac Newton employed, for this purpose, linseed oil. But this, being an unctuous body, is apt to adhere to the sides of the glass, and when suddenly affected by cold, for want of the parts which thus stick to the sides, does not show the true degree. Tinged water was employed by others, but this freezing, when Fahrenheit's thermometer points 32 degrees, and boiling when it rises to 212, was, from thence, incapable of denoting any more intense cold or heat. Spirit of wine, which endures much cold without stagnating, was next made use of, but this liquor, being susceptible of no greater degree of heat than that which, in Fahrenheit scale, is expressed by 175, could be of no service where boiling water was concerned. At last the properest fluid, to answer every purpose, was found to be mercury. This had never been known to freeze, and not to boil under a heat of 600 degrees, and is free from every other inconveniency attending other liquors. As the instrument is entirely founded on this principle, that heat or fire expands all bodies, as cold condenses them, there was a necessity of employing a fluid easy to be dilated. A quantity of it is seated in one part of the bulb. This being expanded by heat, is pushed forward into a fine tube, or capillary cylinder, so small that the motion of the fluid in it is speedy and perceptible. Some thermometers have been constructed with their reservoir composed of a larger cylinder, but in general, at present, they are made globular. The smaller the bulb is, the sooner it is heated through, and the finer the tube, the greater will be the length of it, and the more distinct the degrees. It is scarcely possible that any glass cylinder, so very small, should be perfectly regular. The quicksilver, during the expansion, passing through some parts of the tube wider than others, the degrees will be shorter in the first case, and longer in the latter. If the divisions, therefore, are made equal between the boiling and freezing points, a thermometer whose cylinder is irregular cannot be true. To rectify this inconveniency, the ingenious Mr. Bird, of London, puts into the tube about the length of an inch of mercury, and measuring, with a pair of compasses, the true extent of this body of quicksilver in one place, he moves it from one end to the other, carefully observing where it increases or diminishes in length, thereby ascertaining the parts, and how much the degrees are to be varied. By this contrivance his thermometers are perfectly accurate, and exceed all that were ever made before. I shall not trouble my reader with numerous calculations that have been made to express the quantity of particles of the liquor contained in the bulb, in order to determine how much it is dilated. This, Dr. Martin seems to think a more curious than useful inquiry. It is sufficient for our purpose to know how the best thermometers ought to be constructed. They who have leisure and inclination may be agreeably entertained by the author last cited. By observing the rise of the mercury in the thermometer during any given time, as, for instance, during the time of the day, we ascertain the degree and the value of the heat of every part of the day, from whence may be fixed the medium of the whole time, or any part thereof. By repeated experiments, it appears, the medium heat of most days is usually indicated at 8 o'clock in the morning, if the instrument is placed in the shade, in a northern situation, and out of the reach of any accidental heat. Though water is not so readily affected as air by heat or cold, yet, as all bodies long exposed in the same place become of the same degree of heat with the air itself, no great error can arise from estimating water, in general, to be of the same heat as the air at 8 o'clock in the morning in the shade. The thermometer teaches us that the heat of boiling water is equal to 212 degrees, and by calculation we may know what quantity of cold water is necessary to bring it to any degree we choose. So, notwithstanding the instrument cannot be used in large vessels, where the water is heating, yet by the power of numbers the heat may be ascertained with the greatest accuracy. The rule is this: multiply 212, the heat of boiling water, by the number of barrels of water thus heated, suppose 22, and the number of barrels of cold water to be added to the former, suppose 10, by the heat of the air at 8 o'clock, suppose 50. Add these two products together, and divide by the sum of the barrels. The quotient shows the degree of heat of the water mixed together. 161 1/3 degrees will be the heat of the water when mixed together. The calculation may be extended to 3 or more bodies, provided they are brought to the same denomination. Suppose 32 barrels of water to be used where there is a grist of 20 quarters of malt. If these 20 quarters of malt are of a volume or bulk equal to 11 barrels of water, and the malt, by having lain exposed to the air, is of the same degree of heat with the air, in order to know the heat of the mash, the calculation must be thus continued. We shall meet thereafter with some incidents which occasioned a difference in the calculations made for the purpose of brewing, but of these particular mention will be made in the practical part. The thermometer, by showing the different degrees of heat of each part of the year, informs us, at the same time, how necessary it is that the proportions of boiling water to cold should be varied to effect a uniform intent. Also that the heat of the extracts of small beer should differ proportionally as the heats of the season do. It assists us to fix the quantity of hops necessary to be used at different times, how much yeast is requisite in each term of the year to carry on a due fermentation, and what variation is to be made in the length of time that worts ought to boil. Indeed, without this knowledge, beers, though brewed in their due season, cannot be regularly fermented, and whenever they prove good, so often may it be said fortune was on the brewer's side. Beers are deposited in cellars, to prevent their being affected by the variations of heat and cold in the external air. By means of the thermometer may be determined the heat of these cellars, the temper the liquor is kept in, and whether it will sooner or later come forward. The brewing season, and the reason why such season is fittest for brewing, can only be discovered by this instrument. It points out likewise our chance for success, when necessity obliges us to brew in the summer months. As all vegetable fermentation is carried on in heats, between two settled points we are, by this instrument, taught to put our worts together at such a temperature as they shall neither be evaporated by too great a heat, nor retarded by too much cold. If curiosity should lead us so far, we might likewise determine, by it, the particular strength of each wort, or of every mash. For if water boils at 212 degrees, oil at 600, and worts be a composition of water, oil, and salt, the more the heat of a boiling wort exceeds that of boiling water, the more oils and salts must it contain, or the stronger is the wort. A given quantity of hops, boiled in a given quantity of water, must have a similar effect. Consequently, the intrinsic value of this vegetable may, in the same manner, be ascertained. The more the malts are dried, the more do they alter in color, from a white to a light yellow, next to an amber, further on to a brown, until the color becomes speckled with black, in which state we frequently see it. If more fire or heat is continued, the grain will at last char and become entirely black. By observing the degrees of heat necessary to induce these alterations, we may, by the mere inspection of the malt, know with what degree of fire it has been dried, and fixing upon such which best suits our purpose, direct, with the greatest accuracy, not only the heat of the first mash, but the mean heat the whole brewing should be impressed with to answer our intent, circumstances of the greatest consequence to the right management of the process. If I have not already said enough to convince the brewer of the utility of this instrument, how curious he ought to be in this choice, and how well acquainted with the use of it, I should add the heat gained by the effervescing of malt is to be determined by it alone. The quantity of heat lost by mashing, by the water in its passage from the copper to the mash tun, and by the extract coming down into the underback, these can be found by no other method, and above all, that there is no other means to know with certainty the heat of every extract. I know very well good beers were sometimes, perhaps often, made before the thermometer was known, and still is, by many who are entirely ignorant of it. But this, if not wholly the effect of chance, cannot be said to be very distant from it. They who carry on this process, unassisted by principles in the use of the thermometer, must admit they are frequently unsuccessful, whereas did they carefully and with knowledge apply this instrument, they certainly would not be disappointed. It is equally true, the brewing art for a long space of time has been governed by an ill-conveyed tradition alone. If lucky combinations have sometimes flattered the best practitioners, faulty drinks have as often made them feel the want of certain and well-established rules. It is just as absurd for a brewer to refuse the use of the thermometer as it would be for an architect to reject the informations of his plummet and rule, and to ascertain they were unserviceable because the first house, and probably many others, were built without their assistance. End of Section 7. Recording by Todd.
Section 8 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bailey Gower. The Theory and Practice of Brewing by Michael COMBRUNE. Section 8. Of the Vine, its Fruits, and Juices. After these short accounts of the principles and instrument necessary to the right understanding of the brewing art, we should now draw near to the particular object of this treatise, but as the most successful method to investigate it must be first to inspect the great and similar example nature has set before us. Our time will not be lost by making this inquiry. Any fermented liquor that in distillation yields an inflammable spirit miscible with water may be called wine, whatever vegetable matter it is produced from. As beer and ales contain a spirit exactly answerable to this definition, brewing may justly be called the art of making wines from corn. Those, indeed, which are the produce of the grape, have a particular claim to the name, either because they are the most ancient and the most universal, or that a great part of their previous preparation is owing to the care of nature itself. By observing the agents she employs and the circumstances under which she acts, we shall find ourselves enabled to follow her steps and to imitate her operations. Most grapes contain juices which, when fermented, become in time as light and pellucid as water, and are possessed of fine spirituous parts sufficient to cherish, comfort, and even inebriate. But these properties of vinosity are observed not to be equally perfect in the fruits of all vines. Some of them are found less, others not at all proper for this purpose. It is therefore necessary to examine the circumstances which attend the forming and ripening of those grapes, whose juices produce the finest liquors of the kind. All grapes, when they first bud forth, are austere and sour, therefore of a middle nature. And this can be no other than the effect of the autumnal remaining sap mixed with the new raised vernal one, the consequence of which mixture will be found greatly to merit our inquiry. As far as our senses can judge at first, it appears that the juice in this state consists of somewhat more than an acid combined with a tasteless water. When the fruit is ripe, it becomes full of a rich, sweet, and highly flavored juice, the color, consistency, and taste of which shew that, by the power of heat, a considerable quantity of oil has been raised, and sheathing the salts is the reason of its saccharine taste and saccharine properties. In England, grapes are probably produced under the least heat they can be raised by. They discover themselves in their first shape about June, when the medium heat of the 24-hour shade is 57.6. This, with what more should be added for the effect of the sun's beams, are the degrees of heat which first introduced the juices into this fruit. The highest degrees of heat in the countries where grapes come to perfect maturity have been observed to be in various parts of Italy, Spain, and Greece 100, and at Montpellier 88 in the shade. To which, according to Dr. Lining's observations, 20 degrees must be added for the effect of the sun's beams. The greatest heat in Italy will then amount to 120 degrees, and in the south of France to 108. These approach nearly to the strongest heats observed in the hottest climates which, in Astrakhan, Syria, Senegal, and Carolina, were from 124 to 126 degrees. Those countries where the heat is greatest in general produce the richest fruits, that is, the most impregnated with sweet, thick, and oily juices. We are told among the Take wine hills there is one which, directly fronting the south, and being the most exposed to the sun, yields the sweetest and richest grapes. It is called the Sugar Hill, and the delicious wines extracted from this particular spot are all deposited in the cellars of the imperial family. Those grapes, some in the Canaries, some in other places, being suffered to remain the longest on the tree with their stems half cut through, by this means procure their juices to be highly concentrated, and produce that species of sweet, oily, balmy wines, which, from this operation, are called sac, a derivation of the French word sec or dry. In all distillations of unfermented vegetables, water and acid salts rise first. A more considerable degree of fire is required for the elevation of oils, and a still greater one for the lixivial salts, which render those oils miscible with water. A plant exposed to a very gentle heat at first yields a water which contains the perfect smell of the vegetable blended with a subtle oil. If more heat be added, a heavier oil will come over. From some, a volatile alkali, from others, a phlegm will rise, which gradually grows acid. And last of all, with the farther assistance of fire, the black, thick, empyreumatic sulfur. Nature, in a less degree, may be said to place a like series of events before our eyes, in the forming and maturating of grapes, and it is by imitating what she does that the inhabitants of different countries may improve the advantages of their soil and of their air. In order to illustrate the doctrine that grapes are endued with various properties in proportion to the heat of the air they have been exposed to, let us remember what Bohov has observed, that, in very hot weather, the oleous corpuscles of the earth are carried up into the air and, descending again, cause the showers and dews in summer to be very different from the pure snow of winter. The first are acrid and disposed to froth, the last is transparent and insipid. Hence summer rain, or rain falling in hot seasons, is always fruitful, whereas in cold weather it is scarcely so at all. In winter the air abounds with acid parts, neither smoothed by oils nor rarefied by heat. Cold is the condensing power, as heat is the opener of nature. In summer, the air, dilating itself, penetrates everywhere, and gives to the rain a disposition to froth, occasioned by the admixture of oleous and aerial particles. Thus the acid salts, either previously existing or by the vernal heat introduced into the grapes, and necessary to their preservation, are neutralized by coming in contact with the juices the foregoing autumn produced. After which a hotter sun, covering or blending these juices with oils, changes the whole into a saccharine form. In proportion as these acids are more or less sharp and counterbalanced by a greater or lesser quantity of oils, the juices of grapes approach more or less to the state of perfection which fermentation requires. There are many places, as Jamaica, Barbados, etc., in which experience shews the vine cannot be cultivated to advantage. By comparing the heat of these places with those in Italy and Montpellier, it appears this defect is not owing to excessive heats, but to their constancy and uniformity. The temperature of the air of these countries seldom being so low as the degree necessary for the first production of the fruit. Whenever the cultivation of the vine is attempted in these parts of the West Indies, the grapes on their first appearance are shaded and screened from the beams of the sun, which in their infancy they are not able to bear. Hence we learn, though nature employs both the autumnal and vernal seasons, yet there are lesser heats with which she prepares the first juice of grapes, a stronger power of the sun she requires to form the fruit, and a greater than either to ripen it. We have investigated the lowest degrees of heat in which grapes are produced, and nearly the highest they ever receive to ripen them. Let us call the first the germinating degrees, and the last those of maturation. If nearly 58 be the lowest of the one, and 126 the highest of the other, and if a certain power of acids is necessary for the germination of the grapes, which must be counterbalanced by an equal power of oils raised by the heat of the sun for their maturation, then the medium of these two numbers, or 92, may be said to be a degree at which this fruit cannot possibly be produced, and inferior to that by which it should be maturated. At Panama, the lowest degree of heat in the shade is 72, to which 20 being added for the sun's beams, the sum will be 92, and consequently no grapes can grow there, except the vines be placed in the shade. If we recollect that we can scarcely make wine which will preserve itself of grapes produced in England, we shall be induced to think that the reason of this defect is the want of the high degrees of heat. Our sun seldom raises the thermometer to 100 degrees, and that but for a short continuance. Our medium heat is far inferior to 92, and hence we see at several distant terms in summer new germinated grapes, but seldom any perfectly ripe. These observations, the use of which in brewing we will endeavor to apply, likewise point out to us what part of our plantations are fit to produce this fruit, and to what degree of perfection. A research made for each constituent part forming grapes, as well as the proportion they bear to one another at first sight, appears to be an eligible method to discover the nature of wines. But in every vegetable their parts are mixed and interwoven, and every degree of heat acting on them finds these so blended as to render their division too imperfect for such inquiry to be made with sufficient accuracy, to deduce therefrom the rules of an art. In the producing, ripening, and fermenting the juice of the grapes, as well as in forming beers and ales, the element of fire so superlatively influences and governs every progressive act as to occasion some remarkable difference in their appearance. From hence, then, we may expect the information we want, and be enabled to discover the laws by which nature forms her wines. When the constituent parts of a subject are to be estimated by heat alone, the number of degrees comprehended between the first heat which formed it and the last which brought it to a perfect state must express the whole of its constituent parts. Complete finished substances must have been benefited by the whole latitude of degrees applicable thereto, and in proportion as part of the whole latitude is wanting, will their nature be different, and themselves less perfect. This variety is remarkable in the fruit we are now treating of. A country endued with the lowest germinating and with the highest maturating degrees of heat for grapes would produce them in the utmost perfection. That is, they would possess all the several properties they could obtain from this circumstance. Consequently, such are capable of forming wines that would preserve themselves a very long time, and would also become spontaneously fine. From the several heats we have observed that this fruit is capable of enduring, it is reasonable to believe the greatest number of degrees of heat employed to form all their constituent parts must be where, during the whole space of vegetation, the heat in the shade varies from 60 to 106 degrees, and constitutes a difference of 46 degrees. So great a latitude, ordered by nature, most certainly denotes the general utility of the plant. The climate of the southern part of France approaches nearest to this, but Spanish wines are richer. Their grapes are formed by a warmer sun, their vernal and maturating heats exceed those of France, but at the same time their wines are more stubborn and, to be made fine, require the help of precipitation. This variety increases according to the heat of climates. Thus we see wines which come from the coast of Africa, whose richness and stubbornness are beyond the reach of any menstruum employed to find them. Let us endeavor to reduce this apparent inconstancy to rule in order to assist our art. If the lowest heat which forms the grape in the southern parts of France be 60 degrees, and if 88 degrees in the shade be the mean of their maturating heat, the difference between 60 and 88, or 28 degrees, is the number which includes the constituent parts of grapes in this country, as these degrees imply the whole space of their progress. If like juices were to be imitated by art, as in our hothouses, it is clear half the number of the degrees of heat which form the whole of the constituent parts, or 14, deducted from 74, the mean heat of their whole vegetation would give 60 for the first heat to be employed, and this to be raised for maturation to 88, the greatest heat nature in this case permits, or 14 degrees to be added to the same whole mean. To liken the wines of Spain, where the autumnal and vernal heats are greater than in France, the heat forming the first juices must be more, as also the maturating heats. But with such practice, the number of constituent degrees would be found to be fewer, and spontaneous brightness could no more be expected than it is found in their wines. A strict inquiry after the heats first and last applied to grapes is of such consequence to ascertain the principles by which malt liquor should be formed, that though grapes produced in England scarcely make wines which can maintain themselves sound, yet, as the rule is universal, even from them we shall be able to establish not only its certainty, but also the application of the number of the degrees found between the heats which germinate the fruit and those which ripen them. From 12 years' observation, we have found the mean heat in the shade from the 1st of June to the 15th, when grapes with us first bud forth, to be 57.6. Our greatest heat under like circumstances from the 15th to the 31st of July to be 61.1, their difference 3.5, their medium 59.35. If from their medium 59.35 we subtract 1.75, half their difference or half their constituent parts, we must have left 57.6 for the germinating heat. And if to their medium 59.35 we add 1.75, half the number of their constituent parts, we shall have 61.1, the highest mean heat in the shade, at the time the richest juices of our grapes are formed. It is true, in July, nor even in the following months, when the heat continues nearly alike, our grapes are not ripe nor gathered. The properties raised by our greatest sunshine as yet have not reached the fruit, and though the mean heat of the air in September and October is less, yet it is sufficient to place in the grapes the juices raised by the preceding hot sun, which concentrate and grow richer by remaining on the plant, though, for want of a sufficient heat, they do not reach that perfection obtained in warmer climates. The want of grapes in many parts both of America and Africa, and the reason we gave for this, see page 55, warrants the truth of the division we have just now made between the germinating and maturating heats. And if the effects caused by a hot sun do not immediately benefit the fruit, by a parity of reason, after the grapes are gathered, the plant must possess, and surely for some longer space, by a continued heat equal and often superior to the vernal sun, juices which nature is too frugal not usefully to apply. These juices, we apprehend, assist in forming the embryo of the leaves which are fully to expand the ensuing year, and serve by their oleaginous quality to preserve these and the whole plant during the cold of the winter, which cold, at the same time that it contracts the pores of the vine, condenses and thickens these richer juices, from whence few, if any of them, are lost or expended by perspiration. The heat of the following spring renews their activity. When blending with those this season attracts, the leaves open, the flowers appear, and the fruit forms. Thus far we conceive the act of germination extends, provided for and assisted both by the autumnal and vernal heats, and which, in point of power, are nearly equal and uniform. The heat of the sun during summer months, and if to this we add the more constant heat at the roots of the vine, retained there by the density of the earth. These, though superior to the germinating heat, produce a like uniformity for maturating the fruit. Thus nature, in order to implant in wines an original even taste, and to facilitate the fermentable act, amidst the great variety that appears to us in the heat of the air, seems, upon the whole, to act by steady and equal motions. Or rather, perhaps, this is the best manner by which we can reduce to rule the inconstancy of the atmosphere. I am sensible these facts had been represented in a more natural light had I observed the degrees of heat impressed on the vine in every season of the year. The difference of the sun's heat in every hour of the day, a variety exceeding that in the shade, that between night and day, the aspect of the plant, the heat of the earth at its surface, as well as the roots of the vine, all these would have increased the circumstances to a prodigious extent, which, though perhaps requisite to satisfy philosophic investigation, might from their number and variety have been the means rather to induce us to error than to discover the general rules by which nature acts. From the above related process we are taught that nature in forming wines is not confined to a certain fixed number of degrees, but admits for this act of a considerable latitude according to the extent of which the wines vary in taste and properties, and that she effects an equality of heat in each period of vegetation, from whence the brewer is taught, if he form his malt liquors with 4 mashes, as in the autumn and spring the vine is impressed with heats nearly uniform, so ought his first 2 mashes to be. The third, in imitation of the high heat of summer, should be much hotter, and the heat of his last mash the same with this. And this general rule has been found universally true for beers expected to preserve themselves sound a sufficient time, and admits but of a proportional variation when fewer or more mashes are employed, as the degrees of heat denominating the constituent parts of the grain must be applied in proportion to the quantity of water used to each mash. But in malt liquors speedily to be drank, or when we deviate greatly from the more perfect productions of nature, we are then compelled to swerve from her rules, a practice never profitable, and which nothing but necessity can justify. The nature of soil proper for the vine might, in another work, be a very useful inquiry. It will be sufficient here barely to hint at the effect which lixivial soils produce in musts. The Portuguese, when they discovered the island of Madeira in 1420, set fire to the forest with which it was totally covered. It continued to burn for the space of 7 years, after which the land was found extremely fruitful and yielding such wines as, at present, we have from thence, though in greater plenty. It is very difficult to find these wines, and though the climate of this island is more temperate than that of the Canaries, the wines are obliged to be carried to the Indies and the warmer parts of the globe, to be purged, shook, and attenuated before they can arrive to an equal degree of fineness with other wines. Were the Portuguese acquainted with what may be termed the artificial method of exciting periodical fermentation, much or the whole of this trouble might be avoided. Hence we see that soils impregnated with alkaline salts will produce musts able to support themselves longer, and to resist acidity more than other soils under the same degree of heat. Grapes have the same constituent parts as other vegetables. The difference between them as to their tastes and properties consists in the parts being mixed in different proportions. This arises either from their absorbent vessels more readily attracting some juices than others, or from their preparing them otherwise under different heats and in different soils. We find, says Dr. Hales, by the chemical analysis of vegetables, that their substance is composed of sulfur, volatile salts, water, and earth, which principles are endued with mutual attracting powers. There enters likewise in the composition a large portion of air, which has a wonderful property of attracting in a fixed, or of repelling in an elastic state, with a power superior to vast compressing forces. It is by the infinite combinations, actions, and reactions of these principles that all the operations in animal and vegetable bodies are effected. Bohov, who is somewhat more particular with regard to the constituent parts of vegetables, says that they contain an oil mixed with a salt in form of a sapo, and that a saponaceous juice arises from the mixture of water with the former. Thus we see from the composition of grapes that they have all the necessary principles to form a most exquisite liquor, capable by a gentle heat to be greatly attenuated. They abound with elastic air, water, oils, acid, and neutral salts, and even saponaceous juices. The air contained in the interstices of fluids is more in quantity than is commonly apprehended. Sir Isaac Newton has proved that water has 40 times more pores than solid parts, and the proportion likely is not very different in vegetable juices. When the fruit is in its natural entire state, the viscidity of the juices and their being enveloped by an outward skin prevent the expansion of the enclosed air. It lies as if it were active. In this forced state, it causes no visible motion, nor the principles thus confined either subjected to any apparent impressions of the external atmosphere, or so intimately blended as when they are expressed. A free communication of the external air with that contained in the interstices of the liquor is required to form a perfect mixture. By what means this is effected, what alterations it produces, or in general in what manner the juice of the grape becomes wines, must be the subject of our next inquiry. The process of a perfect fermentation is undoubtedly the same where the due proportions of the constituent parts forming the must are exactly kept, whatever vegetable juices it is excited in. For this reason we will observe the progress of this act in beers and ales, these being subjects we are more accustomed to, and where the characters appear more distinct, in order to apply what may be learned from thence to our chief object, the business of the brewer. End of section 8. Recording by Bailey Gower.
Section number 9 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Santoni. The Theory and Practice of Brewing by Michael COMBRUNE. Section number 9 of Fermentation in General. Vegetable fermentation is that act by which oils and earth, naturally tenacious by the interposition of salts and heats, are so much attenuated and divided as to be made miscible with, and to be suspended in an homogeneous pellucid fluid, which, by a due proportion of the different principles, is preserved from precipitation and evaporation. According to Boerhaave, a less heat than 40 degrees leaves the mass in an inert state, and the particles fall to the bottom in proportion to their gravity. A greater heat than 80 degrees disperses them too much, and leaves the residuum a rancid, acrimonious, putrid mass. It is certainly very difficult, if not impossible, to discover the true and adequate cause of fermentation. But by tracing its several stages, circumstances, and effects, we may perhaps perceive the agents and means employed by nature to produce this singular change, a degree of knowledge which, we hope, is sufficient to answer our practical purposes. The must, when just pressed from the grapes, is a liquid composed of neutral and lixivial salts, oils of different spicitude, water, earth, and elastic air. These, irregularly ranged, if I may be permitted the expression, compose a chaos of wine. Soon after the liquor is settled, a number of air bubbles arise, and at first adhere to the sides of the containing vessel. Their magnitude increases as they augment in number, so that at last they cover the whole surface of the must. It has been long suspected, and, if I mistake not, demonstrated that an acid of which all others are but so many different species is universally dispersed through and continually circulating in the air, and that this is one of nature's principal agents in maturating and resolving of bodies. Musts, like other bodies, being porous, the circulating acids very powerfully introduce themselves therein by the pressure of the atmosphere, in proportion as the pores are more or less expanded by the heat they are exposed to. The particles of acids are supposed by Newton to be endued with a great attractive force, in which their activity consists. By this force they rush towards other bodies, put the fluid in motion, excite heat, and violently separate some particles in such manner as to generate or expel air, and consequently bubbles. From hence it appears that as soon as the acid particles of the air are admitted into the must, they act on the oils, and excite a motion somewhat like the effervescence generated when acids and oils come in contact, though in a less degree. This motion is the cause of heat, by which the included elastic air, being rarefied, occasions the bubbles to ascend towards the surface. These, by the power of attraction, are drawn to the sides of the vessel. At first they are small and few, but increase both in number and magnitude, as the effect of the air continues, till at last they spread over the whole surface. The first stage of vegetable fermentation shews itself to be a motion excited by the acids floating in the air, acting on the oleous parts of the liquor, which motion gives an opportunity to the divided minute parts of air, dispersed throughout the whole, to collect themselves in masses. From hence they become capable to exert their elasticity, and to free themselves from the must. See Arbuthnot on Air, page 116. It may perhaps be proper to observe that all musts, which ferment spontaneously, contain for this purpose a large portion of elastic air. Bubbles still continue to rise after the must is entirely covered with them, and a body of bladders is formed, called by the brewers the head of the drink. As the bubbles increase, the head rises in height, but the oils of the must, being as yet of different spicitudes, those which are least tenacious soon emit their air, others, somewhat stronger, being rarefied by the fermenting heat, rise on the surface higher than the rest, while such aerial bubbles as are more dense take their place below them. From hence, and from the constituent parts of the drink not being as yet intimately mixed, the head takes an uneven and irregular shape, and appears like a beautiful piece of rockwork. After this, it requires some time, and it is by degrees that the particles dispose themselves in their due order, to be farther attenuated by the act of fermentation, which, when effected, the saline, oily, and spirituous parts become perfectly miscible with water. The head of the liquor then is more level. Heterogeneous bodies, as dirt, straw, corks, etc., assisted by bubbles of air adhering to them, are now buoyed on the surface, and should be skimmed off, lest, when the liquor becomes more light and spirituous, they should subside. About this time, such parts of the must are too coarse to be absorbed in the wine, as they consist chiefly of pinguous oils mixed with earth, though they strongly envelop much elastic air, from their weight sink to the bottom, and form the lees. But the internal motion increasing, the air bubbles grow larger, some not formed of parts so strong as the others, which generally are the first, burst and strengthen the rest, and thereby a heat is retained in the fermenting liquor, which carries the act onto a farther degree. The particles of the must become more pungent and spirituous, because more fine and more active. Some of the most volatile ones fly off, hence that subtle and dangerous vapor, called gas, which extinguishes flame and suffocates animals. The wine, by these repeated acts, being greatly attenuated, is at last unable to support on its surface the weight of such a quantity of froth, rendered more dense by the repeated explosions of the air bubbles. Now, lest the liquor should be fouled by the falling in of the froth, it is put in vessels having only a small aperture, where it continues to ferment with a slower and less perceptible motion, which gradually diminishing until it reaches the period when it neither attracts or repels air, it admits of its communications with it to be cut off. Not that thereby, in a strict sense, the fermentation can be said to be completely ended. The least heat is sufficient to renew, or rather to continue the act, more especially if by any means the atmosphere can gain any admittance, however small. The alteration caused in the liquor by the pressure of the external air, from the very first of its fermenting, not only occasions the particles of the must to form themselves in their due order, but also, by the weight and action of that element, grinds and reduces them into smaller parts. From hence they more intimately blend with each other. The wine becomes of an equal and even taste, and if the constituent parts of the must be in a perfect proportion, it will continue to ferment, until, these being disposed in range and right lines, a fine and pellucid fluid is produced. That this operation subsists, even after the liquor becomes fine, is evident, for every fretting is a continuance of fermentation, though often almost imperceptible. Thus, the component parts of the liquor are continually reduced to a less volume. The oils become more attenuated and less capable of retaining elastic air. As these frettings are often repeated, it is impossible to determine by any rule the exact state in which wine should be in order to be perfect for use. It would seem, however, that the more minutely the parts are reduced, the more their pungency will appear, and the easier their passage be in the human frame. Both wines and beers, when new, possess more elastic air than when meliorated by age. To be wholesome, they must be possessed of the whole of the fermentable principles. For these reasons, beers and ales, when substituted for wines in common, and more especially when given to the sick, should always be brewed from entire malt. For the last extracts, possessing but the inferior virtues of the grain, have by so much less the power to become light, spirituous, and transparent. Wines never totally remain inactive. Fermentation in some degree continues, and in time the oils, by being greatly attenuated, volatilize, fly off, and permit a readier admission of the external air into the drink. In proportion as this circumstance takes place, the latent acids of the liquor shew themselves, the wine becomes sour, and in this state is termed vinegar. Its last stage or termination is, when the remaining active principles, which the vinegar possessed, being evaporated in the air, a pellicle forms itself on the surface of the liquor, and dusts and seeds, which always float in the atmosphere, depositing themselves thereon, strengthens this film into a crust, on which grows moss and many other small plants. These vegetables, together with the air, exhaust the watery parts, after which no signs of fermentable principles remain, but like the rest of created beings, all their virtues being lost, what is left is a substance resembling common earth. Upon the whole, then it appears that a liquor fit for fermentation must be composed of water, acid smoothed over with oils, or saccharine salts, and a certain portion of elastic air. The heat of the air the liquor is fermented in must be in proportion to the density of its oils, and lastly, that the pores are to be expanded by slow degrees, lest the air, by being admitted too hastily, should cause an effervescence rather than a fermentation, and occasion the whole to become sour. Wines, therefore, fermented in countries where the autumn is hot, require their oils to be more pinguous than where the season is cooler. For the same reason beers are best made when the air is at 40 degrees of heat, or below the first fermentable point, because the brewer in this case can put his wort to work at a heat of his own choosing, which will not be increased by that of the air. On the contrary, when by its internal motion the heat becomes greater, it will again be abated and regulated by the cold of the medium. The pores of a wort are expanded in proportion to the heat it is impressed with, on which account common small beer, brewed in summer when the air and acids more easily insinuate themselves into the liquor, ought to be enriched with oils obtained by hotter extracts to sheath these salts, and in winter the contrary method must be pursued. From this history of fermentation, we can, with propriety, account for the many accidents and varieties that accompany this act, and a comparative review of some of them may not be unnecessary. A cold air, closing the pores of the liquor, always retards and sometimes stops fermentation. Heat, on the contrary, constantly forwards this act, but if carried too high, immediately prevents it. A must, loaded with oils, will ferment with more difficulty than one which abounds with acids. It likewise is longer before it becomes perfectly fine, but when once so, will be more lasting. If the quantities of oil are increased, they will exceed the power both of the acids naturally contained in the must and of those absorbed from the air in fermenting. The liquor will therefore require a longer time before it becomes pellucid, unless assisted by precipitation, and there may be cases where even precipitation cannot fine it. These considerations naturally lead us to a general division of wines into three classes. First of such as soon grow fine, and soon become acid, being the growth of cold countries. Secondly, of those which, by a due proportion of heat, both when the grapes germinate and when they come to maturity, form a perfect must, and not only preserve themselves, but in due time, more especially when assisted by precipitation, become transparent. And thirdly, of such as, having taken their first form under the highest degrees of germination, as I term them, are replete with oils, disappoint the copper, and render the application of menstruums useless, unless in such quantities as to change the very nature of the wine. This remarkable difference in wines appears chiefly to arise from the climate, and it will confirm the observation before made, that as wines are neither naturally nor uniformly perfect, they must be subject to many diseases. All vegetable substances possess fermentable principles, though in a diversity of proportions. For those juices only, whose constituent parts approach to the proportion necessary for the act of fermentation, can be made into wines. I would not, however, from what I have attributed to a difference of heat in different climates, be understood as if I thought that vegetables are more or less acid, more or less sulphureous, or in general more or less fermentable, merely from the heat of the country they grow in. This, though likely one of the principal causes of their being so, is by no means the only one. The form and constitution of the plant is another. In very hot climates we find acid fruits, such as limes, tamarinds, lemons, and oranges. The proportions of fermentable principles in these fruits are such as to render them incapable of making sound wines, though their juices may, in some degree, be susceptible of fermentation. In countries greatly favored by the sun, some vines and other fruit trees there are, which attract the acids from the air, and possibly from the earth, so greedily that when their juices are fermented, they soon become sour. On the contrary, in cold climates, we see warm, aromatic vegetables grow, as hops, horseradish, chamomile, wormwood, etc., whose principles cannot, without difficulty, and perhaps not perceptibly, be brought to ferment. But these instances must be accounted the extremes on each sides, for in cold, as well as in hot countries, fruits are produced susceptible of a perfect natural fermentation. With us, for example, apples, some species of which are endued with such austere and aromatic qualities that their expressed juices ferment spontaneously until they become pellucid and are capable of remaining in a sound state many years. From hence it appears that proper subjects which will naturally ferment for making wines may be found in almost every climate. England, says Boerhaave, on this account is remarkably happy. Her fruits are capable of producing a great variety of wines, equal in goodness to many imported, where not our taste but too often subservient, not to reason, but to custom and prejudice. A similar want of perfection to that observed in wines may be noticed in our beers and ales, and it chiefly has its origin in the different degrees of heat the malt has been impressed with, both in drying and extracting, where, in the processes of malting and brewing, a sufficient heat has not been maintained, the liquor undoubtedly must become acid. In proportion as the contrary is the case, or that the beer is overcharged with hops, if this is in no great excess, it retains still a greater tendency to fermentation than to putrefaction, acids not being wanting, but only enveloped. In this case, time will get the better of the disease. Like to the wines made from the growth of too hot a sun, these liquors, at a certain period, sicken, smell rancid, and have a disagreeable taste, but by long standing they begin to fret, and receiving more acids from the air, recover their former health and improve in taste. But should the quantity of oils exceed this last proportion, in wines formed from corn, the must, instead of fermenting, would putrefy, even though by some means elastic air has been driven into them. In this case, the overproportion of the oil and its tenacity prevents the entrance of the acids. The wort receives no enlivening principle from without, and the air, at first conveyed into it, is enveloped with oils so tenacious as to be incapable of action. Nothing so much accelerates putrefaction as heat, moisture, and a stagnating air, and all substances corrupt, sooner or later, in proportion to the inactivity of the contained air, to the want of a proper vent, and to the closeness of their confinement. Besides these cases, beers and ales, as well as wines, sometimes are vapid and flat, without being sour. This does not so much arise from the imbibing the air of the atmosphere, as from their fermenting, generating and casting off too much air of their own. To prevent this accident, they are best preserved in cool cellars, where their active invigorating principles are kept within due bounds, and not suffered to fly off. These facts ought to convince us of the truth, deduced by Dr. Hales from many experiments, that there is a great plenty of air incorporated in the substance of vegetables, which by the action of fermentation is roused into an elastic state, and is as instrumental to produce this act as it is necessary to the life and being of animals. I should here close this short and imperfect account, but as, in the art of brewing, there is no part so difficult and at the same time so important to be in some measure understood as the cause and effects of fermentation, and as the examination of this act in all the different lights in which it offers itself to our notice can hardly be thought uninteresting, these few detached thoughts I hope will be allowed of. The effect of the act of fermentation on liquors is so to attenuate the oils, as to cause them to become spirituous and easily inflammable. When a wine is dispossessed of such oils, which is nearly the case in vinegar, far from possessing a heating or inebriating quality, it refreshes and becomes a remedy against intoxication. The term of fermentation ought, perhaps, only to be applied to that operation which occasions the expressed juices of vegetables to become wine, but as several acts have assumed the same name, it may not be improper here to notice the difference between them. Vegetation, one of them, is that operation of nature wherein more air is attracted than repelled. I believe all that has been said above concerning the juice of grapes is a convincing proof thereof. Fermentation is where the communication of the external and internal air of a must is open and in a perfect state, when the power of repelling is equal to that of attracting air. Putrefaction is when, by the power of strong oils or otherwise, the communication between the external and the internal air of the must is cut off, so that the liquor neither attracts the one nor repels the other, but, by an intestine motion, the united particles separate and tend to fly off. Effervescence is when, by the power of attraction, the particles of matter so hastily rush into contact as to generate a heat which expels the enclosed air, and this, more or less, in proportion to the motion excited. End of section 9. Section 10 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Santoni. The Theory and Practice of Brewing by Michael COMBRUNE. Section 10 of Artificial Fermentation. By what has been said, it appears that though fermentation is brought on by uniform causes and productive of similar effects, it is subject to many varieties, both in respect to its circumstances and to its perfection. One difference is obvious and seems to deserve our attention, as it furnishes a useful division between natural and artificial fermentation. The first rises spontaneously and requires nothing to answer all the necessary purposes, but the perfection of the juices and the advantage of a proper heat. The other, at first sight less perfect, wants the assistance of ferments or substitutes without which the act could, either not at all or very imperfectly, be excited. There are undoubtedly liquors which, though they have of themselves a tendency to fermentation and are naturally brought to it, yet, from some defect in the proportions of their constituent parts, either do not acquire a proper transparency or cannot maintain themselves in a sound state for a sufficient time. These disadvantages, inbred with them, can hardly ever be entirely removed. They gain very little, especially the latter, from age, and therefore are really inferior to liquors, which require the assistance of substituted ferments to become real wines. In some artificial fermentations, the ferments are so duly and properly supplied and so intimately blended with the liquor, and in the end they approach very near to, and even vie with, the most perfect natural wines. Were I to enter into a more minute detail, it might be shown that wines, when transported from a hot climate to a cold one, are often hurt and checked in the progress of the repeated frettings they require, from whence they become or remain imperfect, unless racked off from their grosser lees, or precipitated with strong menstruums, whereas beers may be so brewed as to be adapted either to hot or a cold region, not only without any disadvantage, but with considerable improvements. Hitherto I have considered grapes as a most pulpous fruit, sufficient to furnish the quantity of water necessary for extracting its other parts, but the natives of the countries where this fruit abounds, in order to preserve them as near as possible in their primitive state after they are gathered, suspend them in barns or place them in ovens to dry. Thus, being in a great measure divested of their aqueous parts, these grapes remain almost inactive and without juices sufficient to form wines. In all bodies, the various proportions of their constituent parts produce different effects. Hence, they remain more or less in a durable state, and tend either to inaction, fermentation, or putrefaction. Now, by a judicious substitution of such parts as shall be wanting, they are nearly, if not wholly, restored to their pristine nature, as may be proved by the observations and experiments communicated to the public by Dr. Pringle. Thus grapes, though dried and exported from their natural climate to another, by the addition of water only, ferment spontaneously, and form wines very near alike to such as they would have produced before. It may with confidence be said, that when any considerable difference appears, it arises from the injudicious manner in which the water is administered, from the fruit not being duly macerated, or from want of such heat being conveyed to the water and fruit as the juices would have had, if they had been expressed out of the grapes when just gathered. Often from the whimsical mixture of other bodies therewith, and perhaps too from the quantity of brandy which is always put to wines abroad, to prevent their fretting on board a ship. Upon the whole, though, from what just now has been observed, some small difference must take place. It rather proves than contradicts the fact that a due quantity of water being applied to dry raisins, an extract may be formed, which will be impregnated with all the necessary constituent parts the grapes had in them when ripe upon the vine, consequently will spontaneously ferment and make a vinous liquor. Water, then, in this case, becomes a substitute, and the liquors produced in this manner may be accounted of the first class of artificial wines. Vegetables, in their original state, are divisible into pulpous and farinaceous kinds, both possessing the same constituent parts, though in different proportions. If from the farinaceous such parts be taken away as they superabound in, and others be added, of which they are defective, these vegetables may, by such means, be brought to resemble, in the proportion of their parts, more especially in their musts, the natural wines I have before been treating of. And these being universally acknowledged to be the standard of wines, the nearer any fermented liquor approaches thereto, by its lightness, transparency, and taste, the greater must its perfection be. To enquire which of the pulpous or which of the farinaceous kinds of vegetables are fittest for the purpose of wine-making would here be an unnecessary digression. Experience, the best guide, hath, on the one side, given the preference to the fruit of the vine, and on the other to barley. To make a vinous liquor from barley, having all the properties of that produced from the grape, is a task, which can only be compassed by rendering the wort of these similar to the must of the other. As malt liquors require the addition of other substitutes besides water to become perfect wines, they can only be ranked in the second class of artificial fermentation. These substitutes are properly called ferments and merit the brewer's closest attention. Ferments in general, such as yeast, flowers or lees of wine, honey, the expressed juices of ripe fruits, are subjects more or less replete with elastic air and convey the same to musts which stand in need thereof. Boerhaave has ranged these, and several others, in different classes, according to their different powers, or rather in proportion to the quantity of air they contain for this purpose. The juice of the grape, when fermented, forms more lees than the extracts of malt. May we not from thence infer that in the fruit the elastic air is both more abundant and contained in a greater number of stronger, though smaller vesicles than it is in the malt? The barley, being first saturated with water, germinated only, and then dried with a heat far exceeding that which ripened it, or that which fermentation admits of, has its air in part driven out. The expulsion of air from the worts of beers and ales is still farther affected by the long boiling they undergo. Hence, the necessity of replacing the lost elastic air in order that these extracts may become fermentable. This is effected by means of the yeast, which, consisting of a collection of small bubbles filled with air and ready to burst by a sufficient heat, becomes the ferment, which facilitates the change of the wort into a vinous liquor. The musts of malt generally produce 2 gallons of yeast from 8 bushels of the grain, whereas, in the coldest fermentable weather, and for the speediest purpose, 1 gallon of yeast is sufficient to work this quantity of malt. Much elastic air still remains in beer, or wine from corn after the first part of the fermentation is over. For the liquor, separated from the yeast above mentioned, is, at the time of this separation, neither flat, vapid, nor sour. But as yeast, the lees and flowers of malt liquors are of a weaker texture than those of grapes. All artificial fermentation should be carried on in the coolest and slowest manner possible. And beers, but more especially such as are brewed from high-dried brown malts, the heat of whose extracts approaches much nearer to that which dried the grain than is the case in brewing pale malt, ought not to be racked from their lees, as it is frequently practiced for natural wines, unless, on account of some defect, they are to be blended with fresh worts under a new fermentation. As all ferments are liable to be tainted, great care ought to be taken in the choice of them, every imperfection in the ferment being readily communicated to the must. It would not, therefore, be an improper question to be determined by physicians whether, in a time of sickness, the use of those which have been made in infected places ought to be permitted, and whether, at all times, a drink fermented in a pure and wholesome air is not preferable to that which is made among fogs, smoke, and nauseous stenches. Wines from corn are distinguished by two appellations, viz., those of ale and beer. As each of these liquors have suffered in character, either from prejudice or want of a sufficient enquiry, it may be proper to levy the objections made against their use, before we inquire into the means of forming them. The most certain sign of the wholesomeness of wines is transparency and lightness, yet some, which are rich, more especially ales, though perfectly fine, have been said to be viscid. Transparency appears indeed in many wines, before the oils are attenuated to their highest perfection, and some viscidity may therefore be consistent with some degree of brightness. Where the power of the oils and the salts are equal, which is denoted by the transparency of the liquor, viscidity can only arise from the want of age. This cannot be said to be a defect in, but only misapplication of the liquor by being used too soon. That beers retain igneous or fiery particles seems equally a mistake. Malt dried to keep has undoubtedly its particles removed by fire, so far as the cohesion of them is thereby destroyed. Otherwise it would not be in a fit state to preserve itself sound, or readily to be extracted. For this reason, when the grain comes in contact with the water, which is to resolve it, an effervescent heat is generated, which adds to the extracting power, and should be looked on by the brewer as an auxiliary help. But it is impossible that the malt or the must should ever enclose and confine the whole or part of fire employed to form them. Fire is of so subtle a nature that its particles, when contained in a body, continually tend to fly off and mix with the surrounding air, so that only an equal degree with what is in the atmosphere can be continued in the grain, or any liquor whatever, after it has been, for some time, exposed thereto. Brown beers made from malt more dried than any other, from experience, are found to be less heating than liquors brewed from pale malt, which probably arises from hence that brown beers contain a less quantity of elastic air than pale beers, as pale malt liquors contain less than wines produced from vegetables in their natural state, and as malt liquors contain their elastic air and bubbles of a weaker consistence than those made from the juices of the grape. The effect of beer, when taken in an overabundant quantity, is neither of so long a continuance nor so powerful as that of wine, supposing the quality and quantity of each to be equal. This may appear to some persons to be the effect of prejudice, yet it is but a justice due to the produce of my country, to add that some physicians have given it as their opinion that strong drinks from malt are less pernicious than those produced from grapes. As far as these gentlemen have, I hope I may advance without being thought guilty of assuming too much, or countenancing debauch, by pointing out the wines that occasion the fewest disorders. End of section 10.
Section 11 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE, Section 11 of the Nature of Barley. Barley is a spicated, oblong, ventricose seed, pointed at each end and marked with a longitudinal furrow. The essential constitution of the parts in all plants, says Dr. Grew, is the same. Thus, This seed, like those which have lobes, is furnished with radical vessels, which, having a correspondence with the whole body of the corn, are always ready, when moistened, to administer support to the plume of the embryo, usually called the acrospire. These radical vessels at first receive their nourishment from a great number of glandules dispersed almost everywhere in the grain, whose pulpous parts strain and refine this food so as to fit it to enter the capillary tubes, and such an abundant provision is made for the nourishment of the infant plant that the same author says these glandules take up more than 9/10 of the seed. Barley is sown about March, sooner or later, according to the season or soil that is to receive it, and generally housed from 10 to 20 weeks after. Most plants, which so hastily perform the office of vegetation, are remarkable for having their vessels proportionably larger, and that these may be thus formed, the seed must contain a greater quantity of tenacious oils, in proportion to those seeds, whose vessels, being smaller, require more time to perform their growth and come to maturity. This grain, as may be observed, grows and ripens with the lower degrees of natural heat, from whence, and from the largeness of the size of its absorbent vessels, it must receive a great portion of acid parts. It is said to be viscid, though, at the same time, a great cooler, water boiled with it being often drunk as such, and, however it be prepared, it never heats the body when unfermented. From these circumstances, of its being viscous and replete with acids, it would at first appear to be a most unfit vegetable, from which vinous liquors, to be long kept, should be made, and indeed the extracts from it in its original state are not only clammy, but soon become sour. When the grain is at full maturity, its constituent parts seem to be differently disposed than when in a state of vegetation. By germination alone, all its principles are put in action. The fibrous parts possess themselves of a great quantity of tenacious oils, leaving the glandules and finer vessels replete with water, salts, and the purest sulfur. If, in this state, the corn is placed in such a situation that, by heat, the acid and watery parts may be evaporated, the more such heat is suffered to affect it, the more dry and less acid will the corn become. Its parts will be divided, its viscidity removed, its taste becomes saccharine, by the acids being sheathed or covered over with oils, and these last be rendered more tenacious in proportion to the greater quantity of heat they are made to endure. This process, regularly carried on, is termed malting, and will hereafter be explained more at large. But before we enter thereon, it is necessary to consider the state of the grain as it comes from the field. When mowed, though, upon the whole, it may be said to be ripe, yet every individual part, or every corn, cannot be so. In some seasons, this inequality is so remarkable as to be distinguished by the eye. The difference in the situation, the soil and the weather, the changes of the winds, the shelter some parts of the field have had from such winds, are sufficient to account for this, and a much greater variety. When the greater part of the corn is supposed to have come to maturity, it is cut and stacked, the ripest parts having the least moisture and the fewest acids, as the greenest abound in both. In this state the unripe grains of the corn communicate to such as are more dry their moisture and acid parts, which, coming in contact with their oils, an agitation ensues, more or less gentle, in proportion to the power of the acids and water, and from hence is generated a heat, the degree whereof is with difficulty determined. When this sweating in the mow is kept within its proper limits, the whole heap of the corn, after this internal emotion is over, becomes of one equable dryness, and is not discolored. But if the grain be put together too wet or too green, the effervescence occasioned thereby will produce such a violent intestine heat as to char and blacken the greatest part thereof, nay, often make it burst into actual flame. The effect which a moderate and gentle heat has on the corn is that of driving the oils toward the external parts of its vessels and skin. By this means it becomes more capable to preserve itself against the injuries of the weather. The more it is in this state, the backwarder it will be to germinate when used to this purpose, and if this act is carried too far, or to somewhat like what we have just now mentioned, the plume and root of the enclosed embryo must be scorched, the corn become inert and incapable of vegetation. This effect is produced by a motion sufficient to remove the particles of the grain from each other beyond their sphere of attraction, and the heat by which this motion is excited has been found in malted corn to be at about 120 degrees. It is likely that vegetables in general are susceptible of a large latitude in this respect, according to their different textures. The degree of heat just now mentioned may perhaps be applicable to barley alone. The seeds of some grapes endure 126 degrees of heat, and may be capable of being impressed with more and yet vegetate. But with corn, if their oils have endured so great a heat as thereby to be discolored, the seed can by no means be revived. The color of the grain properly indicates the healthy state of the embryo or future plant, but this more immediately is the business of the farmer and maltster than that of the brewer. Thus, though it may be disadvantageous to the maltster to steep grain which has not sweated in the mow, as for want of this it will not equally imbibe the water, so barley that is overheated or mow burnt cannot be fit for his purpose. It is in fact scarcely possible that any large quantity of barley from the same stack should make equally perfect malt, as, on its being put together, the heat generated is always greatest in the center of the rick, and considerably more there than in its exterior parts. End of section 11. Recording by Pete McElveen.
Section 12 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 12 of Malting. This process is intended to furnish proper means for setting the constituent principles of the grain in motion, so that the oils, which before served to defend the several parts, may be enabled to take their proper stations. This is effected by steeping the barley in water, where it strongly attracts moisture, as all dry bodies do, but it requires some time before the grain is fully saturated therewith. 2 or 3 days, more or less, are necessary, in proportion to the heat of the air, for vegetables receive the water only, by its straining through the outward skin and absorbent vessels, and their pores are so very fine that they require this element to be reduced almost to a vapor, before it can gain admittance. Heat hath not only the property of expanding these pores, but perhaps also that of adding to the water a power more effectually to insulate itself. By the water gaining admittance into the corn, a great quantity of air is expelled from it, as appears from the number of bubbles which arise on its surface when in contact with the grain, though yet much remains therein. A judgment is formed that the corn is fully saturated, so as not to be able to imbibe any more water from its turgidity and pulpousness, which occasions it readily to give way to an iron rod dropped perpendicularly therein. At this time the water is let to run, or drawn off, the grain taken out of the cistern, and laid in a regular heap, in height about 2 feet. We have before accounted why moist vegetables, when stacked together, grow hot. So doth this heap of barley. The heat, assisted by the moisture, puts in motion the acids, oils, and elastic air remaining in the corn, and these not only mollify and soften the radical vessels, but, with united power, force the juices from the glandular parts into the roots, which are thereby disposed to expand themselves, and empowered to convey nourishment to the embryo enveloped in the body of the grain. The corn is in this heap, or couch, is however not suffered to acquire so great a degree of heat as to carry on germination too fast, by which not only the finer but also the coarser oils would be raised and entangled together, and the malt, when made, become bitter and ill-tasted. But before the acrospire is perceived to lengthen, the barley is dispersed in beds on the floor of the malt house, and, from being at first spread thin, gradually, as it dries, and as the germination is thereby checked in its progress, it is thrown into larger bodies, so that, at the latter part of this operation, which generally employs 2 days, much of the moisture is evaporated, its fibers are spread, and the acrospire near coming through the outward skin of the barley. By these signs, the maltster is satisfied that every part of the barley has been put in motion and separated. It is of great consequence, in making of malt, that the grain be dried by a very slow and gradual heat. For this purpose it is now thrown into a large heap, and there suffered to grow sensibly hot, as it will in about 20 or 30 hours, thus prepared for drying. In this lively and active condition, it is spread on the kiln, where, meeting with a heat superior to that requisite for vegetation, its farther growth is stopped, though, in all probability, from the gentleness of the first fire it ought to be exposed to, none of the finer vessels are, by this sudden change, rent or torn, but, by drying, only the cohesion of its parts removed, rendered inactive, and put in a preservative state. Often, to a fault, the drying of a kiln of malt is performed in 6 or 8 hours. It would be to the advantage of the grain that more than double this time was employed for any intent whatever. It may here be observed that those oils, which in part form the roots, being with them pushed out from the body of the corn, and dried by heat, are lost to any future wort, not being soluble in water, which is likewise true of those oils which are contained in the shoot or plume, so that the internal part of the malt has remaining in it a greater proportion of salts to the oils than before, consequently are less viscid, more saccharine, and easier to be extracted. In this process, the acid parts of the grain, though they are the most ponderous, yet being very attractive of water, become weaker, and, by the continued heat of the kiln, are volatilized and evaporated with the aqueous steam of the malt. Thus, by malting, the grain acquires new properties, and these vary at the different stages of dryness. In the first, it resembles the fruit ripened by a weaker sun, and in the last those which are the growth of the hottest climates. When the whiteness of the barley has not been greatly changed by the heat it has been kept in, it is called pale malt, from its having retained its original color. But when the fire in the kiln has been made more vehement, or kept up a longer time, it affects both the oils and the salts of the grain, in proportion to the degree of the heat, and to the time it has been maintained, and thus occasions a considerable alteration in the color. Actual blackness seldom is, and ought to never be, suffered in malts, but in proportion to the intenseness of the fire they have been exposed to, the nearer do they come to that tinge, and from the different brown they show, receive their several denominations. The condition the barley was gathered in, whether green or ripe, is also clearly discernible when it is malted. If gathered green, it rather loses than gains in quality, for the stock of oils in unripe corn being small, the whole is spent in germination, from whence the malt becomes of a smaller body, appears shriveled, and is often unkindly or hard. That, on the contrary, which hath come to full maturity, increases by malting, and if properly carried through the process, appears plump, bright, clean, and, on being cracked, readily yields the fine mealy parts, so much desired by the brewer. The malts, when dried to the pitch intended by the maker, are removed from the kiln into a heap. Their heat gradually diminishes and, from the known properties of fire, flies off, and disperses itself in the ambient air. Sooner or later, as the heap is more or less voluminous, perhaps too in some proportion to the weight of the malt, and as the fire has caused it to be more or less tenacious. Nor can it be supposed that any of its parts are capable of retaining the fire in such a manner as not to suffer it to get away. So subtle an element cannot be confined, much less be kept in a state of inactivity, and imperceptible to our senses. Bars of iron, or brass, even of a considerable size, when heated red hot, cool and lose their fire, though their texture is undoubtedly much closer than that of malt or barley. The experiments made by Dr. Martin on the heating and cooling of several bodies leave no room to doubt of this fact, which I should not be so particular about, nor in some measure repeat, was it not to explain the technical phrase used by brewers, when they say, malts are full of fire, or want fire. Hence a prejudice hath by some been conceived against drinks made from brown malts, though they have been many months off the kiln, and have no more heat in them, either whole or ground, than the air they are kept in. The truth of the matter is, that, in proportion as malts are dried, their particles are more or less separated from one another, their cohesion is thereby broke, and, coming in contact with another body, such as water, strongly attract from it the uniting particles they want. The more violent this intestine motion is, the greater is the heat just then generated, though not durable. An effect somewhat similar to what happens on malt being united with water must occur on the grain being masticated, and the impression made on the palate most probably gave rise to the technical expression just taken notice of. The minute circumstances of the process of malting will be more readily conceived from what will hereafter be said. The effects that fire will have, at several degrees, on what, from having been barley, is now become malt, are more particularly the concern of the brewer, and that these differ, both as to the color and properties, is certain. A determinate degree of heat produces, on every body, a certain alteration, and hence, as the action of fire is stronger or weaker, the effect will not be the same as what it would have been in any other degree. Barleys, at a medium, may be said to lose, by malting, 1/4 part of their weight, including what is separated from them by the roots being screened off, but this proportion varies according as they are more or less dried. As the acrospire, and both the outward and inward skins of the grain are not dissoluble in water, the glandular or mealy substance is certainly very inconsiderable in volume and weight. But as in this alone are contained the fermentable principles of the grain, it deserves our utmost attention. We have therefore seen that wines, beers, and ales, after the first fermentation, are meliorated through age by the more refined and gentle agitations they undergo, and which often are not perceptible to our senses. To secure this favorable effect, we must form worts capable of maintaining themselves, for some time, in a sound state. This quality, however, if not originally in the malt, is not to be expected in the liquor. Some objections have been raised against this method of arguing, and these aided by prejudices, often more powerful than the objections themselves. It is therefore necessary, as malting may be esteemed the foundation of all of our future success, to inquire after the best and properest methods of succeeding in this process. Let us, for this purpose, reassume the consideration of the grain, as it comes from the mow, trace it to the kiln, and observe every change it undergoes by the action of fire, from the time that it receives the first degree of preservation to that when it is utterly altered and nearly destroyed. Barley in the mow, though there its utmost heat should not much exceed 100 degrees, may be extracted or brewed without malting. This the distiller's practice daily evinces, but then the extracts, made from this unchanged corn, are immediately put in the still after the first fermentation, else they would not long remain in a sound state. Nor is this method practicable in summertime, as the extracts would turn sour, before they were sufficiently cooled to ferment. It is true, by this means, all the charge of the malt duty is saved, but our spirits thereby are greatly inferior to those of the French. Boerhaave recommends the practice of that nation, which is to let the wines ferment, subside, and be drawn off fine from the lees, before they are distilled. Was this rule observed in England, distillation would be attempted only from malted grain, which, if properly extracted for this purpose, the difference in the spirit would soon show how useful and necessary it is to give wines, either from grapes or corn, time to be softened, and to gain some degree of vinosity before they are used to this intent. But might not barleys be dried without being germinated? Undoubtedly they might, but as they abound with many acids and strong oils, they would require a heat more intense than malt does, before they were sufficiently penetrated. Then the oleaginous parts would become so compact and so resinous as nearly to acquire the consistence of a varnish, scarcely to be mollified by the hottest water, and hardly ever to be entirely dissolved by that element. Barley then ungerminated, either in its natural state or when dried, is not fit for the purpose of making wines, but when, by germination, the coarser oils are expelled, and the mealy parts of the grain become saccharine, might not this suffice? And where is the necessity of the grain being dried by fire? I shall not dwell on the impossibility of stopping germination at a proper period without the assistance of fire, so that sufficient quantities of the grain thus prepared may always be provided for the purposes of brewing, nor even insist upon the difficulty of grinding such grain as, in this case, it would be spongy and tough. I think it sufficient to mention solely the unfitness of this imperfect malt for the purpose it is to be applied to, that of forming beers and ales capable of preserving themselves for some time. We should find so many acids blended with the water still remaining in the grain that, in the most favorable seasons for brewing, they would often render all of our endeavors abortive and, in summertime, make it impracticable to obtain from them sound extracts in any manner whatsoever. I have heard of a project of germinating grain and drying it by the heat of the sun in summertime in order, by this means, to save the expense of fuel. Though the hottest days in England may be thought sufficient for this act, as well as for making hay, yet, as barley and grass are not of equal densities, the effects would not be the same. This, however, is not the only objection, as the corn, after a sufficient germination, should be made inactive. This very hot season, favorable in appearance to one part of the process, would rather forward than stop or retard vegetation, for the barley, by this heat, would shoot and come forward so fast as to entangle too much the constituent principles of the grain with one another, and drive the coarser ill-tasted oils among the finer sweet mealy parts, which alone, in their utmost purity, are the subject required for such as would obtain good drinks. There often appears in mankind a strange disposition to wish for the gifts of Providence in a different manner than they have been allotted to us. The various schemes I have just now mentioned, if I mistake not, have sprung from the desire of having beers and ales of the same appearance with white wines. But as they are naturally more yellow or brown, when brewed from malts dried by heats equal or superior to that which constitutes them such, all such projects, by which we endeavor to force some subjects to be of a like color with others, are but so many attempts against nature, and the prosecution of them must commonly be attended with disappointments. It is true that though the germinated grain be dried slack, yet, if they are speedily used, and brewed in the most proper season, they may make a tolerable drink, which will preserve itself sound for some time. But the proportion, which should be kept between the heat which dried the malt, and that which is to extract it, cannot, in this case, be truly ascertained. And, as the grain will be more replete with air, water, and acids, than it ought to be, the drink, even supposing the most fortunate success, and that it does not soon turn acid, will still be frothy, and therefore greatly wanting in salubrity, for an excess in any of the fermentable principles must always be hurtful. Barley, then, to be made fit for the purpose of brewing, must be malted. That is, it must be made to sprout or germinate with degrees of heat nearly equal to those which the seed should be impressed with when sown in the ground, and it must be dried with a heat superior to that of vegetation, and capable of checking it. How far germination should be carried on, we have already seen. The law seems to be fixed universally. As to the extent of the acrospire, the degree of dryness admits of a larger latitude, the limits of which shall be the subject of our next enquiry. Malt dried in so low a degree, as that the vegetative power is not entirely destroyed, on laying together in a heap, will generate a considerable degree of heat, germinate afresh, and send forth its plume or acrospire quite green. The ultimate parts of the nourishing principles are then within each other's power of acting, else this regermination could not take place, and such grain cannot said to be malted, or in a preservative state. Bodies whose particles are removed by heat beyond their sphere of attraction can no more germinate, but, coming in contact with other bodies, as malt with water, they effervesce. The grain we are now speaking of first shows this act of effervescence when it has been thoroughly impressed with a heat of 120 degrees, and a little before its color, from a white, begins to incline to the yellow. Such are the malts, which are cured in a manner to be able to maintain themselves sound, though in this state, and at this degree of dryness, they possess as much air and as many acid and watery particles as their present denomination can admit of. This, therefore, may be termed the first or lowest degree of drying this grain for malt. To discover the last or greatest degree of heat it is capable of enduring, the circumstance to guide us to it, though equally true, is not so near at hand as effervescence, which helped us to the first. We must therefore have recourse to the observation of that heat, which wholly deprives the grain of its principal virtues. Dr. Shaw observes, alcohol is one of the most essential parts of wine. When absent, the wine loses its nature, and, when properly diffused, it is a certain remedy for most diseases incident to wines, and keeps them sound and free from corruption, from whence was derived the method of preserving vegetable and animal substances. The same excellent author had before this observed, that no subjects but those of the vegetable kingdom are found to produce this preserving spirit. Is alcohol, then, a new body, created by fermentation and distillation, or did it originally, though latently, reside in the vegetable? I have for a good while been satisfied by experiments, says Boerhaave, that all other inflammable bodies are so only as they contain alcohol in them, or, at least, something that, on account of its fineness, is exceedingly like it, the grosser parts thereof that are left behind, after a separation of the subtle one, being no longer combustible. Now, as the same author has clearly proved that fire, by burning combustible bodies, as well as by distilling them, separates their different inflammable principles according to their various degrees of subtlety, the alcohol residing in the barley, when exposed to such a degree of heat as it would cause it to boil, i.e. 175 degrees, must make great efforts to disengage itself from the grain. It is not, therefore, natural to conclude that, in a body like malt, whose parts have been made to recede from one another, from whence it is porous and easily affected by fire, prepared for fermentation, or the making of vinous liquor. This event will probably happen at the same time when the body of the grain has been ultimately divided by fire, or that malt chars? And if this is true, may not charring be termed the last degree of dryness when, even somewhat before it takes place, the acid parts and the finest oils, which are necessary for forming a fermentable must, fly off and cannot be recovered? Charring seems to be a crisis in solid bodies, somewhat analogous to ebullition in fluids. Both being thereby perfectly saturated with fire, their volatile and spirituous parts tend to fly off. In charring, the subject being ultimately divided by fire, the constituent principles are set at liberty and escape in the atmosphere, in proportion to their several degrees of subtlety, and to the fire which urged them. In boiling they are equally divided and inclined to disperse, but, even the more volatile, being surrounded with water, a medium much denser than themselves, they are caught up therein, and, by the violent motion caused in boiling, entangled with it, and with other parts it contains, so as not to be extricated or divided therefrom except by the act of fermentation. Now, as liquors boil with a greater or less fire in proportion to their tenacity and gravity, solid bodies may likewise be charred by various proportions of heat. The whole body of the barley, as its different parts are of different texture, cannot, at the same instant, become black, nor, where any quantity of the grain is under similar circumstances, if not equally germinated, can the whole char with the same degree. To the several reflections before made, I thought proper to add the surer help of experience. I therefore made the following trial, with all the care I was capable of. If the effects of it appear satisfactory, by gaining 2 limited and distant degrees, we may determine and fix the properties of the intermediate spaces, in proportion to their expansion. In an earthen pan of about 2 feet diameter and 3 inches deep, I put as much of the palest malt, unequally grown, as filled it on a level to the brim. This I placed over a little charcoal, lighted in a small stove, and kept continually stirring it from top to bottom. At first it did not feel so damp as it did about half an hour after. In about an hour more, it began to look of a bright orange color on the outside, and appeared more swelled than before. Everyone is sensible that a long-continued custom makes us sufficient judges of colors, and this sense in a brewer is sufficiently exercised. Then I masticated some of the grain, and found them to be nearly such as are termed brown malts. On stirring, and making a heap of them towards the middle, I placed therein, at about half depth, the bulb of my thermometer. It rose to 140 degrees. The malt felt very damp, and had but little smell. At 165 degrees, I examined it in the same manner as before, and could perceive no damp. The malt was very brown, and on being chewed, some few black specks appeared. Many corns, nearest the bottom, were now become black and burnt. I placed my thermometer nearly there, and it rose to 175 degrees. But as the particles of fire ascending from the stove act on the thermometer, in proportion to the distance of the situation it is placed in, through the whole experiment an abatement of 5 degrees should be allowed, as near as I could estimate. Putting, a little after, my thermometer in the same position, where about half the corns were black, it showed 180 degrees. I now judged that the water was nearly evaporated, and observed the heap grew black apace. Again, in the center of the heap, raised in the middle of the pan, I found the thermometer at 180 degrees. The corn tasted burnt, the surface appeared, about 1/2 part a full brown, and the rest black. On being masticated, still some white specks appeared, which I observed to proceed from those barley corns which had not been thoroughly germinated, and whose parts cohering more closely together, the fire, at this degree, had not penetrated. The thermometer was now more various as it was nearer to, or farther from, the bottom, and, in my opinion, all the true-made malt was charred, for their taste was insipid, they were brittle, and their skins parting from the kernel. I, nevertheless, continued the experiment, and, at 190 degrees, still found some white specks on chewing the grain. The acrospire was always appearing of a deeper black or brown than the outward skin, the corn at this juncture fried at the bottom of the pan. I still increased the fire, and the thermometer placed in the middle, between the bottom of the pan and the upper edge of the corn, showed 210 degrees. The malt hissed, fried, and smoked abundantly, though, during the whole process, the grain had been kept stirring, yet, on examination, the whole was not equally affected by the fire. A great part thereof was reduced to perfect cinders, easily crumbling to dust between the fingers, some of a very black hue without gloss, some very black, with oil shining on the outside. Upon the whole, 2/3 of the corn were perfectly black, and the rest of a deep brown, but more or less so, as the grains were hard, steely, or imperfectly germinated. This was easily discovered by the length of the shoot. Most of the grains seemed to have lost their cohesion, and had a taste resembling that of high-roasted coffee. In the last stage of charring the malt, I placed over it a wine-glass inverted, into which arose a pinguous oily matter, and tasted very salt. It may, perhaps, not be unnecessary to say that the length of time this experiment took up was 4 hours, and that the effect it had, both on myself and on the person who attended me, was such as greatly resembled that of inebriation. Though, from this experiment, the degree of heat at which malt chars is not fixed with the utmost precision, yet we see that black specks appeared when the thermometer was at 165 degrees. Some of the corns were entirely black at 175, others at 180. In proportion as fire causes a deficiency of color, it must occasion a want of fermentable properties, the whole of which are certainly dispersed, when the grain becomes of an absolute black. Thus we may conclude, with an exactness surely sufficient for the purposes of brewing, that true germinated malts are charred in heats at about 175 degrees. As these correspond to the heat at which pure alcohol or the finest spirit of the grain itself boils, it seems to require this heat wholly to extricate itself from the more tenacious parts of the corn, which, when deprived of this ethereal enlivening principle, remains inert, incapable of forming fermentable must or wort, and indicates to us that the constituent parts of vegetables may be resolved by heats equal to those between the first degree which formed them, and the last, which ultimately destroys their properties, though the extracts will possess different qualities or virtues, according to the determinate heat which is applied. End of section 12. Recording by Valentina Vocelli.
Section 12 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Mark Edward Vogt, North Aurora, Illinois. Section 12 of the different properties of malt and of the number of its fermentable parts. The consequences resulting from the before-mentioned experiment have already been hinted at, but it is necessary to trace them farther and to shew how much they tend to the information and the use of the brewer. Germinated barleys, so little dried as their particles remain within their sphere of attraction, are not in a preservative state, and therefore cannot properly be termed malts. The first degree of dryness, which constitutes them such, as we have seen before, is that which occasions them to cause some effervescence. This cannot be effected when they are dried with less than 120 degrees of heat, the highest that can leave them white. When urged by a fire of 175 degrees, they are charred, black, and totally void of fermentable principles. Now this difference of heat, being 55 degrees, and producing in the grain so great an alteration as from white to black, the different shades or colors belonging to the intermediate degrees cannot, with a little practice, be easily mistaken. White, we know from Sir Isaac Newton's experiments, is a composition of all colors, as black is owing to the absence of them. These two terms indicate the extremes of the dryness of malt. The color which the medium heat impresses upon it is brown, which, being compounded of yellow and red, the four tinges of which shade malt differently, may be said to be white, yellow, red, and black. The following table, constructed on these principles, will, on chewing the grain, readily inform the practitioner of the degree to which his malts have been dried. It is true some doubts have arisen whether the increase of heat is by equal divisions according to the scales marked on thermometers, or whether the degrees should not rather be in proportional parts. But if the effect of fire on bodies, as every experiment shews, is exactly corresponding to the expansion it is the cause of, this undetermined question in no wise affects the brewery. A table of the different degrees of the dryness of malts with the changes of color occasioned by each increase of the degrees. Degrees in the left column, color in the right. 119 degrees, white. 124 degrees, white, white, yellow, white turning to a light yellow. 129 degrees, white, white, yellow, yellow, otherwise yellow. 134 degrees, high yellow. 138 degrees, amber. 143 degrees, light brown. 148 degrees, brown. 152 degrees, high brown. 157 degrees, brown inclining to black. 162 degrees, high brown speckled with black. 167 degrees, half brown, half black. 171 degrees, coffee colored. 176, black. NB. The several letters against each degree, it is apprehended, will help in the practice to fix the color. The foregoing table not only enables us to judge of the dryness of the malt by its color, but also, when a grist is composed of several sorts of malt, to foresee the effect of the whole when blended together by extraction. Some small error may be possibly occur in judgments thus formed upon the report of our senses, but as malt occupies different volumes in proportion to its dryness, if, in the practice of brewing, upon mixing the water with the malt, the expected degree is observed, such parcel of malt may be said to have been judged of rightly, and in regard to its dryness, so that the first trial either confirms or corrects our opinion thereof. Though malt, dried to 120 degrees, is in a preservative state, yet it is the least so as malt. It then possesses the whole of its fermentable principles, which, if not impeded in the extraction, would be very speedy and active. The duration of the worts to be formed from the grain so low dried must entirely depend on the power given to the water by heat to draw from the malt oils of such consistence as shall sheathe and retard the hasty effects of the fermentable parts. By extraction, then, malted grain, even so low dried as this, may, with very hot waters, and with the farthest assistance of hops, be made to produce beers, which for years will be capable of maintaining themselves sound, or for a long time to resist the effects of the hottest climates. They may also, by a less degree being given to the extracting water, and blended with less hops, form drinks, which shall be fit for use in so short a time as a week, and perhaps a term much shorter. Hence we see the degree of heat which dried the malt, and the degree of heat given to the water to extract it. The means of these numbers, making an allowance for the quantity of hops used, is that which directs us to fix the properties and the duration of the wort. In one sense, then, we may consider malt, so low dried as this, as being such as would in the shortest time furnish us with a fermented liquor, and in another such as would yield the most delicate and strongest drink. When malt chars and becomes black, its parts are ultimately divided. It has lost the principles fit to form a fermentable wort, and which it once possessed. The degree of heat, prior to that which produces this effect, is the last which still retains any part of the fermentable properties. In worts from malt thus highly impressed by fire, fermentation would proceed was so slow and reluctant to pace that in this case they might be said to be in the utmost state of preservation. No term can be fixed for their duration. A liquor of this sort, brewed with the greatest heat it would admit of in the extracting water, might keep many years and become rather accommodated to the temperature of the place it was deposited in than to its own constituent parts. Experience has shewn that drinks impressed by the drying and extracting heat with a medium of 148 degrees, with a proper addition of hope, at the end of 18 months have been found sound and in a drinkable state, and that this degree we find the middling brown. From these two extremes, and on these principles, the following table is formed, exhibiting the length of time drinks made from malt, impressed with each respective degree of heat, properly brewed in the most favorable season, will require before they come to their due perfection to be used. Equally as with hot extracting waters, low-dried pale malt may be made to yield beers which will long continue in a sound state. So high-dried malt, acted upon by cooler and low extracting water, may be made to furnish a wort soon fit for use, though less agreeable and more inelegant. It might be here asked, why then, at any time, is malt dried with heats exceeding 120 degrees? In answer to this, it might justly be said, it would be very difficult for the maltster to exactly hit this point of drying without deviating from it either on one side or the other. And suppose this difficulty removed, still he could not be certain every individual grain was equally affected. If the drying was less than 120 degrees, the malt, by receiving the moist impressions of the air, would re-germinate and be spoiled. Before the use of hops, malt was high-dried as a means to keep the extracts sound. To eradicate an ancient custom or prejudice requires a long time. This, and the conveniency of keeping malts, was the reason why, for many years, it was in general dried to excess, an error for which some time has been losing ground, as no reason at present subsists why malts should exceed in color a light amber. A table shewing the age of beers will require, before being used, when brewed from malts which, in drying and extracting, have been impressed with a medium heat corresponding to the following degrees. Column title, degrees. Column title, shortest time with 12 pounds of hops. Column title, longest time with 12 pounds of hops. Column, shortest time with fewest quantity of hops possible. Row, 119, 2 weeks. Row, 124, 1 month, 3 months, 2 weeks. Row, 129 degrees, 3 months, 6 months, 4 weeks. Row, 134 degrees, 4 months, 9 months, 6 weeks. Row, 138 degrees, 6 months, 12 months, 6 weeks. New row, 143 degrees, 7 months, 3 months, 2 weeks. New row, 148 degrees, 9 months, 3 months, 2 weeks. New row, 152 degrees, 10 months, 18 months. New row, 162 degrees, 2 years. End of table. It must be observed that the foregoing table is constructed on the supposition that these different sorts of malt are brewed, fermented with the utmost care, with waters heated to extract it in proportion to the dryness of the grain and to the intent of time there set down, and with an adequate addition of hops, an ingredient which shall be considered in its proper place. What is meant by the water being heated to extract malt in proportion to the dryness of grain may merit some explanation. Grapes, when ripe, carry with them the water that they have received both during their growing state and that of their maturity. This quantity is sufficient to form their musts from. To dried grapes or raisins, water is added to supply what they have lost, and for the same reason it is requisite in regard to malt. But as grapes stand in no need of artificial fire to give their fermentative principles a due proportion, so that what they produce themselves or cold water applied to them when dry is a sufficient menstruum, but barleys, wanting the assistance of a great heat to bring their parts to the necessary proportion, require, when malt, a similar or rather greater heat to resolve them, without which, experiment shews, the flour of the grain would come away undissolved, and thus considerably impoverish the grist. Should, on the other hand, too great a heat be applied, an equal loss would be sustained from the finer parts being coagulated or blended with oils, tenacious beyond the power of fermentation to exhibit them. The proportioning, therefore, the heat of the water to the dryness of the malt, more especially to obtain from the grain the whole strength it is capable of yielding, as well as to cause the drink to preserve itself sound its intended time, is of real necessity. Well-brewed drinks should not only preserve themselves sound their due space, in order to be meliorated by time, they should likewise be fine and transparent. These circumstances prove the artist's skill and care, as well as the celebratory of the drink, and are of the surest signs of a well-formed must and of a perfect fermentation. If, then, the rules for obtaining these ends can be deduced from the foregoing principles and experiments, we may flatter ourselves with possessing a theory, which will then answer our expectations in practice. According to the laws of nature discovered by Sir Isaac Newton, the spaces between the parts of opaque bodies are filled with mediums of different densities, and the discontinuity of parts, each in themselves transparent, is the principal cause of their opacity. Salts in powder, or infused in an improper medium, will intercept the light. Gums make a muddy compound when joined to spirits, and oils, unassisted by salts, refuse to be incorporated with water. Musts, therefore, whose constituent parts are not capable of being dissolved by water into one homogeneous body, are not fit either for a perfect fermentation or a pellucid drink. Length of time, which improves beers and wines, often rectifies our errors in this respect, for the oils being, by various frettings, more attenuated and more intimately mixed, the liquor is frequently restored and becomes of itself pellucid. Yet I never found this to succeed where the error upon the whole of the dryness of the malt and the heat of the extracts exceeds the medium by 10 degrees. Art has also, in some measure, concurred with nature to remedy this defect. When beers or wines have been suffered to stand till they are rather in an attracting than in a repelling state, that is, when their fermentations and frettings apparently stand still, then, if they do not become spontaneously fine, they may be precipitated by mixing them with a more ponderous fluid. The floating particles that occasion the foulness are, by this means, made to subside to the bottom and leave a limpid wine. But the power of dissolved isinglass, the ingredient usually used for this purpose, seldom takes effect when the error exceeds the medium, as before, by more than 10 degrees. Other ingredients, indeed, have been used, which carry this power near 10 degrees farther. It is not my province to determine whether or not such be salutary. Undoubtedly, it would be better if there were no occasion for them. Beyond these limits, precipitation has no effect. The liquor, which cannot be fined thereby, if attempted, by increasing the quantity of the precipitants, will be overpowered by the menstruum and injured in its taste. How frequent this last case of cloudiness is would answer no purpose in this place to inquire. The use of doubtful ingredients and such errors as have been mentioned need no longer blemish the art, when a constant and happy practice will both the effect and the proof of a solid and experimental theory. Beers which become bright of themselves or by time alone, as well as those precipitated either by dissolved isinglass or by more powerful means, each possess their respective properties in a certain latitude or number of degrees. And as these effects arise wholly from the heats employed in the drying the malts and in forming the extracts, the following table will be of use to point out the limits within which each drink may be obtained. A table shewing the tendencies of beers to have become fine when the malt in drying and extracting has been impressed with heats, the medium of which answers to the following degrees, supposed to be brewed and kept in the most eligible manner. 3 columns. Column 1, degrees. Column 2, colors. Column 3, the length of time. Row, 119 degrees, white. Row, 124 degrees, inclining to yellow, immediately. Row, 129 degrees, yellow, 2 months. Row, 134 degrees, high yellow, 4 months. Row, 138 degrees, amber, 6 months. Row, 143 degrees, light brown, 8 months. Row, 148 degrees, brown, 10 months. Row, 152 degrees, high brown, 12 months. Row, 157 degrees, brown inclining to black, 14 months. Row, 162 degrees, high brown speckled with black, 18 months. Row, 167, high brown, half black, 18 months. Row, 171 degrees, coffee colored, 20 months. And last row, 176 degrees, black, 20 months. The difference between the heat for forming grapes and the greatest heat which ripened them affords to us the number of degrees answerable to their constituent parts. The investigation of barley, in like manner, though less important to our purpose, yet may, with some propriety, be admitted. Upon examination it will be found barley ears and the new grain begins to form, being still in possession of its flower, about the same time with us as grapes do, in June, when we found the mean heat of the air to be in the shade to be 57.60 degrees. Barleys in general are mowed from August to September, so that in their growth they are benefited by the whole of our summer's heat, and for like reasons, as in page 59, we estimate this 61.10 degrees. 3.50 degrees then would be the number of their constituent parts taken from the degrees of heat in the shade, and which perhaps would be different if the actual sunshine heat and what is reflected from the earth were accounted for. Barleys are annual, unbenefited by the whole of the autumn sun, but after being mowed they are stacked, retaining still much of their straw, leaves, and outward skins. In these heaps they heat more or less according to the condition in which they were housed, and which heat may reach to 120 degrees or more, but in general is equal or somewhat superior to that of our bodies. The properties of the grain, by this means improved, ripen, and from hence are more capable of preserving themselves. This might be a reason why a farther allowance should be made to the number of degrees denoting their constituent parts. How much, by a very great number of observations made from the germination, ripening to the stacking of the barley, in many years and in many cases, might probably be ascertained. But the difficulty of doing this, and afterwards the impossibility of complying with the information such enquiries would afford, and the little need there is for it, as nature has allowed a considerable latitude for our deviating from what may be styled perfection without any sensible injury. These circumstances render such enquiries unnecessary, if not fruitless. Vegetables, but more particularly barley, from their first origin to such time as they might be ultimately separated by fire, may be divided into different periods according to the distinct properties belonging to each, and each of these require again a more exact enquiry. Barley is under the act of germination so long as the acrospire or stem is within the outer skin of the parent corn. This excluded, it vegetates so long as it receives nourishment by the interposition of its roots. It may be said to be in a state of concentration when receiving but little or no support from the earth, yet it is acted upon by such heats as do not exceed what it might bear in the vegetative period, and that of inaction when, by the power of heat, it is placed in a passive state. Now malt is barley germinated, and by a quick transition is impressed with heats superior to those admitted in vegetation, and as such places the corn in a state of inaction. In the beginning of the process of malting, the more tenacious oils, together with some salts, are excluded from the body of the grain to form the vessels requisite to forward the growth of the future plant. What remains in the parent grain, that choice food at first necessary to the infant barley, are saccharine salts, alone applicable to the brewer's purpose, and of the nature and quantity of which he ought to be well acquainted. To retain these, and prevent a waste thereof, the germinated corn is placed in such heat as destroys the union between its parts, from whence it becomes inactive. When this intent is obtained by the least heat capable of affecting it, the malt retains both its color and the whole of its properties. Vegetables, in no part of their growth, are ever affected by heats so great as to disperse their constituent parts. On the contrary, by natural heats, in general, they are improved. The whole of their elements, then, must be measured from the first degrees which form them to the last which procure their highest perfection. And in climates where they are not benefited by the whole of such heat, their properties must be accounted only so many degrees, as in such places are between the extremes of their germination and maturation. Alike with malt, their whole number of constituent parts, denoted by degrees of heat, must be so many as are comprehended between that degree which leaves in its possession of the whole of their elements, and the first heat which excludes a part. For malt more dried than this, being less perfect, and losing some of its properties, fewer must remain. The degree of heat which in malt divides the period of germination from that of inaction, we have found to be 119. The grain, then, is perfectly white, and shews little if any sign of effervescence. The first change fire occasions therein is to impress it with a light yellow color. This takes place at 129 degrees of heat, an alteration which can proceed from no other cause but in removing its original whiteness to have expelled some of its primitive parts. The difference then between these two numbers of 10 specifies in degrees of Fahrenheit scale the number of properties constituting barley malt. It must be confessed this is establishing a principle of the art of brewing upon the uncertain report of our senses, as perhaps our sight may deceive us in fixing this change of color exactly at 129 degrees. But we know black and white to be the two extremes of the dryness of malt, and that the middle color between them is brown, while being compounded of yellow and red, these four tinges, equally divided, as we have done in the foregoing tables, will corroborate our fixing the taint of the yellow at this degree. The table, shewing the tendency of beers to become fine, was formed from experiments made on brewings whose governing medium heats were from 134 to 148. The proportion in point of time given by these justifies the division between immediate pellucity at 119 and that taking place at 2 months or 129 degrees. So from hence we may be satisfied. However, an absolute perfection cannot be depended upon, yet this being the most exact division our senses can afford, it approaches so near to truth that if any mistake remains, it can be but trivial compared to the latitude of errors, fermentation, and time correct. But this number, 10 degrees, denoting the quantity of fermentable parts, must lessen in proportion as a continued or a greater heat deprives the grain of more properties. A speedy, spontaneous pellucity is the effect of the whole fermentable parts. Malt affected by heat, conveyed either through air or water, or through both, so the medium of these exceeds not 138 degrees, if assisted by the acids gained to the drink by long standing, such will obtain transparency. Beers, then, intended to be formed of themselves to become fine, in the calculations used to discover their elements, so many of the members of the constituent parts must be implied as corresponds with the time the beer is intended to be kept. But when beers are made intentionally to require precipitation to become fine, in such proportions as we purpose to impress opacity on the drink, we must, in the calculations made to discover the temperature of the extracts, imply only so many of the constituent parts as correspond to the medium heat which will occasion this foulness. These few observations shew the necessity of establishing this fundamental doctrine, the use of which will obviously appear in practice. Thus does the success of this art depend on the instrument so often mentioned, which, by indicating the expansions caused by different heats, becomes a sure guide in our operations. I shall now close this account by comparing with principles here laid down the defects which we but too often meet in barley when malted. End of section 12. Recording by Mark Edward Vogt, North Aurora, Illinois.
Section 14 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 14. Observations on Defective Malts. In the preceding inquiry, some of the defects of malt have been occasionally mentioned, but as a perfect knowledge of the grain, especially when it has undergone this process, is a matter of no small concern to the brewer, I shall now bring such defects into distinct view, both to compare them with the foregoing principles, and that the knowledge of them may be more at hand on every occasion when wanted. Every different degree of heat acting on bodies causes a different effect, and this varies also as such heat is more or less hastily applied. The growth of vegetables is in general submitted to these laws, but yet I conceive there is some difference between germination and vegetation which I beg leave to point out. The former seems to be the act caused by heat and moisture, while the plume or acrospire is still enveloped within the teguments of the parent corn, and it is most perfectly performed by the gentlest action, and consequently by the least heat, that is capable of moving the different principles in their due order. Vegetation, again, is that act which takes place when the plant issues forth, and, being rendered stronger by the impressions of the air, becomes capable of resisting its inclemencies, or the warmth of the sunshine. Germination is the only act necessary for malting, the intention being solely to put in motion the principles of the grain, and not to rear up the embryo to a plant. Now, as this begins in barley, at the degree where the water first becomes fluid, or nearly so, the cold season, when the thermometer shews from about 32 to 40 degrees, would seem the most proper for its purpose. How far its latitude may with propriety be extended, experience alone can determine. Maltsters continue to work so long as they think the season permits, and leave off generally in May, when the heat of the water extends at a medium from 50 to 55 degrees. But the nearer they come to this medium, with the greater disadvantage must they malt, as by such warmth the vessels of the corn are much distended, the motion of the fluids violent, and the finer parts too apt to fly off. Thus, the coarser oils gaining admittance, the glandular parts become filled with an impure and less delicate sulfur, which, instead of a sweet, inclines to a bitter taste. This is so manifest and so universally experienced that in general brewers carefully avoid purchasing what is termed ladder-made malts. Malt which has not had a sufficient time to shoot, so that its plume may have reached to the extent of the inward skin of the barley, remains overburthened with too large a quantity of earth and oils, which otherwise would have been expended in the acrospire and radical vessels. All those parts of the corn which have not been separated and put in motion by the act of germination will, when laid on the kiln to dry, harden and glutenize. No greater part thereof will be soluble in water than so far as the stem or spire of the barley rises to, or very little farther, and as much as is wanting thereof will be lost to the strength of the drink. When malt is suffered to grow too much, or until the spire is shot through the skin of the barley, which is not often the case, though all that is left to be malt that is containing salts dissoluble in water, yet as too large a portion of oils has been expended out of the grain, such malts cannot be fit to brew drinks for long keeping. There is, besides, a real loss of the substance of the corn, occasioned by its being overgrown. Malt, the germination of which has been reached and been stopped at the proper period, and has been duly worked upon the floors, if not sufficiently dried on the kiln, even though the fire be excited to a proper heat, retains many watery parts. The corn, when laid together, will be apt to germinate afresh, perhaps to heat so as to take fire. Should not this extreme be the case, at least it must grow moldy and communicate an ill flavor to the drink. Malt well grown and worked as before, but over-dried, though with a proper degree of heat, will become of so tenacious a nature as to require a long time before it can admit of the outward impressions of the air to relax or mellow it. That is, before it is fit to be brewed with all the advantages it otherwise would have, and in proportion as it has black specks on being masticated, so much of its parts being charred is a diminution to the strength of the liquor, besides impressing it with a burnt or nauseous taste. Malt dried on a kiln not sufficiently heated must require proportionably a longer time to receive the proper effect of the fire, the want of which will bring it into the same state as malt not thoroughly dried. If too quick or fierce a fire be employed instead of gently evaporating the watery parts of the corn, it torrefies the outward skin, divides it from the body of the grain, and so rarefies the enclosed air as to burst the vessels. Such is called blown malt, and by the internal expansion occupies a larger space than it ought. If the fire be continued, it causes its constituent parts to harden to the consistence of a varnish, or changes it into a brittle substance, from which the malt is said to be steely and glassy. It dissolves, but in a small proportion, is very troublesome and dangerous in brewing, and frequently occasions a total want of extraction, by the brewery termed setting the grist. Malt, just or but lately taken from the kiln, remains warm for a considerable time. Until the heat becomes equally cool with the surrounding air, it cannot be said to be mellow or in a fit state to be brewed. Its parts being harsh and brittle, the whole of its substance cannot be resolved, and the proper heat of the water which should be applied to it for that purpose is therefore more difficult to be ascertained. The practice of those maltsters who sprinkle water on malt newly removed from the kiln to make it appear as having been made a long space of time, or as they say, to plump it, is a deceit which cannot too much be exposed. By this practice the circumstance of the heat and harshness of the malt is only externally and in appearance removed, and the purchaser grossly imposed on. The grain, by being moistened, occupies a greater volume, and if not speedily used, soon grows moldy, heats, and is greatly damaged. The direct contrary is the case of malt which has been made a long time. The dampness of the air has relaxed it, and so much moisture has insinuated itself into the grain that some doubt must arise how much hotter the mash should, for this reason, be. Yet, supposing no distemper, such as being moldy, heated, or damaged by vermin, it is observed, malt under this circumstance may more certainly be helped in brewing than those just above mentioned. From what has been said, it appears how necessary it is to procure malt which has been properly steeped, germinated to its true pitch, and dried by a gentle, moderate heat, so as the moisture of the corn be duly evaporated, then cured by just so much fire as to enable it to preserve itself a due time without being blown or burnt. How easy it is to regulate this process in the cistern, in the couch, on the floors, and on the kiln, when the maltster intends no artifice to save his excise, I need not say, but with what certainty and ease the whole might be carried on by the help of the thermometer, I leave such to determine as are modest enough to think that the art may be brought to more accurate rules than those of the bare report of our unassisted senses. As such rules may be easily deduced from the principles here laid down, I shall not be more particular in shewing their application, as not being my immediate purpose, nor my business as a brewer, nor have I leisure or the conveniency of a malt house to make experiments of this sort. Yet with truth it may be said that such as would not be disappointed with their brewing must take care not to be deceived in their malt. This, however, being but too frequently the case, we should constantly be on our guard against its defects, and know how to correct them. If it is treated in the same manner as if it was perfect, the well-malted parts alone will be digested. If too slack-dried, it may be corrected by an addition of heat. If over-dried or injured by fire, it may be proportionably helped. By applying the thermometer to the extracts, more particularly to the first, the brewer thereby will be informed to a sufficient degree of exactness of the defects he can mend, and hardly be ever at a loss for the properest means to work the grain to the greatest advantage. As far as we have proceeded in our inquiry, though some satisfaction must arise from our being enabled to account for the greater part of the process of brewing, yet it may be observed, even with the assistance of the thermometer, as yet a geometrical exactness in many respects has not been attained. But nature, when the interest and necessities of mankind are the object, apparently has supplied our wants and rectified our defects. In this art, fermentation, when allowed to display itself, corrects all our errors to a considerable latitude, though as yet of this act it may be said we scarcely conceive its cause or properly discern its effects. End of section 14. Recording by Pete McElveen.
Section 15 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Christina Clark. The Theory and Practice of Brewing by Michael COMBRUNE. Section 15. Part 2. The Practice of Brewing. Before I enter upon the practical and indeed most important part of this work, it will not be improper to give a distinct, though general, view of the different parts it is to consist of. To extract from malt a liquor which, by the help of fermentation, may acquire the properties of wine, is the general object of the brewer, and the rules of that art are the subject of these sheets. An art truly very simple if, according to vulgar opinion, it consisted in nothing else than applying warm water to malt, mashing these together, multiplying the taps at discretion, boiling the extracts with a few hops, suffering the malts to cool, adding yeast to make it ferment, and trusting to time, cellars, and nostrums for its taste, brightness, and preservation. A few notes and observations, such as are too often found to be foisted under the articles of beer and brewing, in some books of agriculture and others of cookery, might be sufficient, were the place and constitution of the air always the same, the materials and vessels employed entirely similar, and lastly, the malt drinks intended for the same use and time. But as every one of these particulars is liable to variations, and can be complied with only by the application of different determinate heats, was the artist to submit himself to loose, vague, and erroneous directions like those above mentioned, they would only serve to deceive him, and his case would be but little mended if he trusted to indefinite signs and insufficient maxims in his deviation from them. A more certain foundation has been laid down in the first part of this treatise, and the principles there established will, I trust, in all cases, answer our ends, provided we make use of proper means to settle their application. The most eligible means to effect this must be to follow, as near as possible, such plan, which the rational brewer would, in every particular circumstance, sketch to himself before he proceeded to business. His first attention ought to be directed not only to the actual heat of the weather, but also to that which may be expected in the season of the year he is in. The grinding of his malt must be his next object, and as the difference of the drinks greatly depends upon that of the extracts, he cannot but choose to have distinct ideas of what may be expected from the amount of the heat of them. Hops, which are added as a preservative to the extracts, form too important a part to be employed without a sufficient knowledge of their power. The strength of malt liquors depending principally on their quantity or lengths, it is necessary to ascertain the heights in the copper to answer what on this account is intended, the difference in boiling for different drinks or seasons, the loss of water by evaporation, the proper division of the whole quantity of this element employed, and, in proportion to such division, that of the heat to be given in each part of the process, the means to ascertain these degrees by determining what quantity of cold water is to be added to that which is at the point of ebullition, come afterwards under his consideration. The manner and time of mashing, the many expected incidents which must produce some small variations between the actual and the calculated heat of his extracts, it will be incumbent upon him to make a proper estimation and allowance for. To dispose of the worts in such forms and at such depths as may render the influence of the ambient air the easiest and most efficacious, and then by the addition of yeast, to provide the drink with that internal and most powerful agent it had lost in boiling, are the next requisites. Fermentation, which follows, and which the brewer retards or forwards, according to his intentions, completes the whole process. After these necessary precautions, to compare his operations with those of the most approved practitioners in his art, and to find himself able to account for those signs and established customs which before were loosely described, authoritatively dictated, and never sufficiently determined or explained, must be to him an additional satisfaction. As precipitation is requisite in certain cases, the common methods for effecting it should be known, and likewise the means practised among coopers to correct the real or imagined errors of the brewer, in order to render the drink agreeable to the palate of the consumers, will naturally lead him to consider what true taste is, and by employing the means by which it may safely be obtained and improved, he will have done all in his power to answer his customer's expectation and to secure his success. This arrangement, which appears the most simple, is that which the reader will find observed in the following sections. The proper illustrations of tables and examples have not been omitted, and from the complete plans for brewing under two forms of the most dissimilar kind, it will be found the rules are adapted to all circumstances and applicable to every purpose. I must here add, somewhat in justification for publishing what may be said to be the mysteries of an art, often too cautiously precluded from the sight and attention of the public, but every art and science whatever have equally been laid open, and from such communication receive greater improvements, and become more useful to mankind in general, and the professors of them in particular. If attention is given to the rules and practice here laid down, it will be found that the brewer, from the large quantities he manufactures, from repeated experience, from the conveniency of his utensils, and more than all from the interest he has to be well acquainted with his business, is most likely to be successful, in preference to anyone else, and therefore can have no reason to be displeased on being presented with a theory and practice which, far from being the sole right of the brewery, the discovery of the principles was certainly the property of the author and of his friends, whose names would do his work honour if mentioned. From the application of these principles, being convinced of their exactness and facility in practice, he offers his labour to a trade he esteems, with no other view than the hope he entertains of being of some service to it and to the public. If, notwithstanding repeated endeavours, some things in this treatise should appear out of their places, others in more than one, if redundancies, chiefly occasioned by the natural temptation of accounting for particular appearances, have not always been avoided, if inaccuracies should now and then have escaped me, let it be remembered, by the good-natured it certainly will, that in new and intricate subjects, digressions and repetitions are in some measure allowable, that an over-fullness is preferable to an affected and often obscure brevity, and that the improvement of the art, rather than the talent of writing, must be the brewer's merit, and was my only aim. End of section 15.
Section 16 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Stearns, Holly Springs, North Carolina. The Theory and Practice of Brewing by Michael COMBRUNE. Section 16. Of the heat of the air as it relates to the practical part of brewing. In and about the city of London, the most intense cold that has been observed is 14 degrees, and the greatest heat has made the thermometer rise in the shade to 89. Within these limits are comprehended all the fermentable degrees, and consequently those necessary for carrying on the process of brewing. If the lowest degree proper for fermentation be 40, and the highest 80, the medium of these two would, at first sight, appear to be the fittest for this purpose, but the internal motion necessary to carry on fermentation excites a heat superior to the original state of the must by 10 degrees. Hence, if 60 degrees be the highest eligible heat a fermenting must should arise to, 50 should be the highest for a wort to be let down at to begin this act, which heat can only be obtained when that of the air is equal thereto, so that it denotes the highest natural heat for beers and ales to be properly fermented. With regard to the other extreme, or the lowest heat, however cold the air may be, as the worts, which form both beers and ales, gain, by boiling, a degree greatly superior to any allowed of in fermentation. It is constantly in the artist's power to adapt his words to a proper state. The brewing season, then, may justly be esteemed all that part of the year in which the medium heat of the day is at or below 50 degrees. This, in our climate, is from the beginning of October to the middle of May, or 32 weeks, the most eligible period of time for brewing all kinds of beers. But, as many incidents often make it necessary to extend these limits, the only time for venturing to comply therewith is when the medium heat of the season is at 55 degrees, by which 6 weeks more may be obtained. But under these circumstances, the quantity of beer brewed should be less, that the worts may cool more readily by being thinner spread, and to gain more time, the brewing is best carried on with 2 worts only. Taking these precautions, and beginning early in the morning, the first wort, by laying long enough in the coolers, will, towards evening, be brought to a heat of 55 degrees. The night in this season of the year being generally colder by 10 or 12 degrees than the medium heat of the whole 24 hours, the second wort may be reduced to a cold of 43 degrees. The mean of 55 and 43, being 49 degrees, would be the real heat of the worts in the tun, and with 10 degrees more, the heat gained by fermentation, still it would not reach 60 degrees, the highest fermentable heat. Beers intended to preserve themselves long should arrive to, but so near would it be to this, and so little is the uniformity of the heat of the air to be relied on, that necessity alone can justify the practice of brewing such drinks, when the heat of the air is so high as 55, Consequently, where it exceeds this, it should never be attempted. As the extractions are made by heats far superior to any natural ones, though the actual temperature of the air neither adds to nor diminishes from their strength, yet it is to be known for the following reason. The proper heat given to the mash is by means of cold added to boiling water, and cold water generally is of no other heat than that of the air itself. Indeed, when the cold is so intense as to occasion a frost, and to change water into ice, that which is then used for brewing, mostly being drawn from deep wells, or places where frost never or but seldom takes place, may be estimated at 35 degrees, and this will be sufficiently exact. The following table shews the temperature of the air for every season in the year, and confirms what I have just now said concerning the season proper for brewing, and the actual heat of the water. It was deduced from many years' observations, made with very accurate instruments at 8 o'clock in the morning, the time in which the heat is supposed to be the medium of that of the whole day. A table shewing the medium heat for every season of the year in and about London, deduced from observations made from 1753 to 1765 at 8 o'clock each morning. January 1st to 15th, 36.38 degrees. January 15th to 31st, 34.97 degrees. February 1st to 14th, 35.51 degrees. February 14th to 28th, 38.11 degrees. March 1st to 14th, 37.99 degrees. March 14th to 28th, 39.72 degrees. April 1st to 14th, 43.13 degrees. April 14th to 28th, 46.4 degrees. May 1st to 14th, 49.5 degrees. May 14th to 28th, 55.67 degrees. June 1st to 14th, 57.2 degrees. June 14th to 28th, 59.14 degrees. July 1st to 15th, 60.52 degrees. July 15th to 31st, 34.97 degrees. August 1st to 15th, 59.89 degrees. August 15th to 31st, 38.48 degrees. September 1st to 15th, 55.17 degrees. September 15th to 31st, 54.13 degrees. October 1st to 15th, 48.66 degrees. October 15th to 31st, 46.72 degrees. November 1st to 15th, 42.26 degrees. November 15th to 31st, 39.40 degrees. December 1st to 15th, 38.61 degrees. December 15th to 31st, 37.54 degrees. To ascertain the authority of this table, and to make it useful to several purposes, I have carried to decimals the mean numbers resulting from my observations, but such an exactness has been found in the practice of brewing to be more troublesome than necessary. I have therefore constructed another table similar to the former, but where the fractions are omitted, and the whole numbers carried on from 5 to 5. The heats of the latter end of October and beginning of November have here been set down rather higher than they really are, as at this time of the year the hops fit to brew with are old and weak, and I could not devise any means more easy to allow for their want of strength. A table shewing the medium heat of the air in and about London for every season of the year applicable to practice. January 1st to 15th, 35 degrees. January 15th to 31st, 35 degrees. February 1st to 14th, 35 degrees. February 14th to 28th, 40 degrees. March 1st to 15th, 40 degrees. March 15th to 31st, 40 degrees. April 1st to 15th, 45 degrees. April 15th to 30th, 45 degrees. May 1st to 14th, 50 degrees. May 14th to 31st, 60 degrees. June 1st to 14th, 60 degrees. June 14th to 28th, 60 degrees. July 1st to 15th, 60 degrees. July 15th to 31st, 60 degrees. August 1st to 15th, 60 degrees. August 15th to 31st, 60 degrees. September 1st to 15th, 55 degrees. September 15th to 30th, 55 degrees. October 1st to 15th, 50 degrees. October 15th to 31st, 50 degrees. November 1st to 15th, 45 degrees. November 15th to 31st, 40 degrees. December 1st to 15th, 35 degrees. December 15th to 31st, 35 degrees. As nothing is so inconsistent as the heat of the air, we are not to be surprised when it deviates from the progression specified in the table. The flowing water used in the brewery, at the coldest seasons, we have fixed at 35 degrees, and the highest heat in the air to carry on the process for beers brewed for long keeping at 55 degrees. The length proper to be drawn, or the quantity of beer to be made from each quarter of malt, being fixed, the brewer at any time has it in his power to make calculations for brewings, supposing the mean heat of the air to be at 35, at 40, at 45, at 50, and even at any degree of heat whatever, so as never to be unprovided for any season. Water, being a body more dense than air, requires some time to receive the impressions either of heat or cold, for which reason the medium heat of the shade of the preceding day will most conveniently govern this part of the process, unless some very extraordinary change should happen in the atmosphere. This must make the business of the artist in this respect very easy, as in the course of his practice he will have only to correct the little changes that occasional incidents give rise to, and the calculations will answer all his purposes so long as the lengths of beer to be brewed from the same quantity of malt remain unaltered, and with very little variation and trouble, when the coppers employed, by being changed, are of different dimensions. The best method to know the true heat of cold water would be to keep a very accurate and distinct thermometer in the liquor back, but as this, in every place, is not to be expected, and inaccuracies must arise from a change in the air to prevent their consequences in practice, we must have recourse to experience. This has taught us that a difference of 8 degrees between the actual heat of the water and that from which the brewing was computed will produce, in the first extract, a difference of 4 degrees. Most brewers' coppers, though they vary in their dimensions, are generally made in proportions nearly uniform. The effect of 1 inch of cold water, more or less, will therefore nearly answer alike, that is, it will alter the heat of the tap by 4 degrees. But this will only hold good in such cases where the water is in the same proportion to the volume of the grist. In brewing brown beers, or porter, 3 worts are generally made. The extracts, therefore, must be of different lengths from what they are in beers brewed at 2 worts only. In this case the quantity of water for the first wort is less than it otherwise would be, and what must be allowed for the first mash to wet the malt is so much as to occasion the second, or piece liquor, to be proportionately less also, as it is of great consequence, if the first tap doth not answer to its proper degree, that the second should be brought to such a heat as to make up the medium of the first and second extracts. The second, or piece liquor, by reason of its shortness, is more conveniently and more exactly tempered in the little copper, and 1 inch cooling in is in this case found, both by calculation and experience, to occasion a difference of 1 degree of heat only in the mash. One of the principal attentions in forming beers and ales of any sort whatever is that they may come to the most perfect state at the time they are intended to be used. Common small beer is required to be in order from 1 to 4 weeks, and as it is impossible to prejudge the accidental variations, as to heat and cold, that may happen in any one season of the year, it is rational to act up to what a long experience has shown is to be expected, and to mix such quantity of cold water with that which is made to come to ebullition, as to bring the extract to the degree fixed for each particular season. Let the heat at the time of brewing vary therefrom in any degree whatever. In treating on the subject of air, in the former part of this work, I observed the effect it had in penetrating the parts of the malt, or in the technical term used by brewers, in slacking it. As such is the case, when the grain is entire and whole, it is most so when ground, and experience teaches us, when malt has been about 24 hours from the mill, that dampness it has imbibed is equal to half an inch more of cold water added to that which is to be made to boil for the first liquor, and produces therefore a diminution of 4 degrees in the heat of the tap. An effect, somewhat resembling this, is caused by the impression of the air on the utensils of a brewhouse, which are not daily used. The heat received from a foregoing process has expanded their pores, and rendered them more susceptible of cold and moisture. From this circumstance, the heat of the first mash will be affected in a proportion equal to half an inch less cooling in, or in the space of 24 hours, to 4 degrees of heat. The time of the day in which the first extract is made becomes another consideration. For as 8 o'clock in the morning is the time of the medium heat in the whole 24 hours, the other hours will give different degrees. When a first mash is made about 4 o'clock in the morning, the following table shews the difference between the heat at 4 and 8. That of the other hours, in the like case, may be learned by observation. It has been observed that in the cold months, from the sun's power being less, the heat of the day and night are more uniform, and also that the coldest part of the 24 hours is about half an hour, or an hour before sunrising. I have judged it convenient to place in the same table the several incidents affecting the first extract. Incidents occasioned by the air affecting the heat of the first extract, to be noticed more particularly when small beer is brewed, as the quantity of water is then greatest, and the mash more susceptible of its impressions. Morning at 4 o'clock, colder by so many degrees than at 8 o'clock in the morning. January, 0 degrees. February, 0 degrees. March, 2 degrees. Utensils for want of being used in 24 hours lose 4 degrees of heat, equal to half an inch of cold water. April, 4 degrees. May, 6 degrees. June, 8 degrees. Malt, which has been ground 24 hours, imbibes moisture equivalent to half an inch, which lessens the heat by 4 degrees. July, 10 degrees. August, 8 degrees. September, 6 degrees. The difference between the actual heat of the air and that naturally expected is to be allowed in proportion of 8 degrees to 1 inch cooling in. October, 4 degrees. November, 2 degrees. December, 0 degrees. Malts, from having been long kept or old, become considerably slacked. Before we quit the subject, it may not be improper to observe that in the hottest season and in the hottest part of the day, the differences between the heat of the air in the shade and that in the sun's beams in and about London is nearly 16 degrees, and also that cellars or repositories for beers are, in winter, generally hotter by 10 degrees than the external air, and in summer colder by 5. End of section 16. Recording by Jennifer Stearns, Holly Springs, North Carolina.
Section 17 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by COMBRUNE. Section number 17. Of grinding. Malt must be ground in order to facilitate the action of the water on the grain, which otherwise would be obstructed by the outward skins. Every corn should be cut, but not reduced to a flour or meal, for in this state the grist would not be easily penetrable. It is therefore sufficient that every grain be divided into 2 or 3 parts, nor is there any necessity for varying this, for one sort of drink more than another. In every brewing the intention of grinding is the same, and the transparency of the liquor, mentioned by some on this occasion, depends by no means on the cut of the corn. It has been a question whether the motion of the mill did not communicate some heat to the maul. Should this be the case, it can be but in a very small degree, and what may arise from hence will be lost by shooting the grain out of the sacks or uncasing the grist into the mash tun. Of late years it has been recommended, instead of grinding the malt, to bruise it between 2 iron cylinders, If by this means some of the fine mealy parts are prevented from being lost in air, it must be very inconsiderable and perhaps not equal to the disadvantage of the water not coming in immediate contact with the flour of the grain. In brewing, not all, but only a certain portion of the constituent parts of the malt are requisite. These heated water alone is sufficient to procure, so that, upon the whole, the difference between bruising and grinding the grain can be of no great consequence. We have before observed malt, by being ground and exposed for some time to the air, more readily imbibes moisture than when whole, and the dampness thus absorbed being in reality so much cold water a grist that has been long ground is capable of being impressed with hotter waters than otherwise it would require. In country places, where the quantity brewed consists only of a few bushels of malt, and makes so small a volume as to be incapable to maintain an uniform heat, where the people are ignorant that a certain degree is necessary to form a proper extract with, and where, instead of this, boiling water is indifferently applied, the effects of these errors are in some measure prevented, by grinding the malts a considerable time, as a month or 6 weeks before the brewing, and by the excess of fire readily escaping from so small a quantity. This method, from the inconstant state of the air, and from the impossibility of acting up to rule, must be very uncertain and fortuitous, so that few or no arguments are necessary to explode it. The truth is, the merit of country ales, so often mentioned, proceeds from the forbearing to use the drink, but when it is in the fittest state. Thus time not only corrects the errors of the operators, but also gives them, in the eyes of the consumers, the credit of an extraordinary knowledge and unmerited ability. End of section 17. Recording by Monika MC.
Section 18 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jeffrey Wilson, Ames, Iowa. The Theory and Practice of Brewing by Michael COMBRUNE. Section 18 of Extraction Part 1. Fire impressed on malt, either through air or water, it is true, has similar effects as to preservation, but the fact is not the same as to taste. The sweet, the burnt flavor, or the proportion of both the malt originally had sensibly appear in the extracts. But water heated to excess will not, in extracting pale malt, communicate to the worts an empyreumatic taste. Whether this proceeds from some acid parts still residing in the heated waters, which might help the attenuated oils to tend towards a sweet, or from other reasons, is not easily determinable. Certain it is, the foundation of taste in malt liquors is in the malt itself. The basis of all wines is a sweet. This circumstance for brewing beers agreeable to the palate must always be attended to. Next to this, it is required that the liquor should possess all the strength it can fittingly be made susceptible of. Pale malt, as it retains the whole virtue of the grain, yields the strongest beers. The finest oils being fittest for fermentation, malt dried by fierce heats in a great measure loses these, and what remains are not only coarser oils, less miscible with water, but such as bring with them the impressed taste of fire. To answer the purposes of taste, strength, and preservation, from what has been said, it appears that the extracting water must be of a heat superior to that which dried the malt. No other rule appears to direct in this than to make choice of malt of such dryness, the delicacy of which has not been removed by fire, and such as will at the same time admit of a sufficient number of superior degrees of heat to extract all its fermentable parts. That is,
see page 124, malt whose dryness is nearly 19 degrees less than the mean of the drying and extracting heats applicable to the purpose intended. As 119 degrees, the first heat forming pale malt, and at which it possesses the whole of its sweetness and virtues, may be said to be the lowest degree of dryness in the grain to form keeping beers with, so 138 degrees, above which the native whiteness of the grain is so subdued as to remain but in a very small proportion, is the highest dried malt fit to be used for any purpose. From these premises the following table is formed to show the degree of dryness of malt where taste and strength are equally consulted, to brew drinks capable of keeping themselves sound a long time at any medium required. The proper choice of malt I thought necessary to point out previous to entering more at large on the subject of extraction. This table, it must be observed, is in no wise directive for brewing common small beer soon to be expended, that liquor depending on many other circumstances, of which notice will be taken immediately under that head. A table showing the proper dryness of malt applicable to the mean of the drying and extracting heats under which keeping malt liquors should be formed. Mean degrees of dryness of malt and heat of extracts versus color of malt expressed in degrees. Mean 138 degrees for color 119 degrees. Mean 140 for color 121. Mean 142 for color 123. Mean 144 for color 125. Mean 146 for color 127. Mean 148 degrees for color 130. Mean 150 for color 132, mean 152 for color 134, mean 155 for color 136, mean 157 for color 138. The subject to be resolved having been examined as to its dryness, we now come to the immediate matter for which this section was intended. Extraction is a solution of part or the whole of a body made by means of a menstruum. In brewing, it is chiefly the mealy substance of the grain that is required to be resolved. Fire and water combined are sufficient to perform this act. Water properly is the receptacle of the parts dissolved, and fire the power which conveys into it a greater or less proportion of them. When all the parts necessary to form a vinous liquor are not employed, or when more than are required for this purpose are extracted, the liquors must vary in their constituent parts and consequently be different in their effects. This difference arises either from heat alone or from the manner of applying it, and the properties of beers and ales will admit of as many varieties as may be supposed in the quantity of the heat and in its application. But as the useful differences are alone necessary to the brewer, they may be reduced to the four following modes of extraction. First, that which is most perfect, and for which malt is chosen of such dryness in which it with certainty possesses the whole of its constituent parts, and the extracts are made with such heats as to give the beer an opportunity to be improved by time, and to become of itself fine and transparent. Secondly, that from which, in order to obtain every advantage of time, strength, and flavor, such extracts are produced as cannot become pellucid of themselves, but require precipitation. Thirdly, that which is intended soon to become intense, where soundness and transparency are for some short time expected, but not always obtained, because brewed in every season of the year, and deprived of the advantages which age and better managements procure to the first. Fourthly, that where the advantages of strength and pellucidity are to be procured in a very short space. These four modes of resolving the grain, being the fundamental elements on which almost every species of drink is brewed, I must observe the two first may be said to be an exact imitation of natural wines, in forming which the principles we have laid down may fully be applied. The third is the effect of necessity, by which we are deprived of that time nature directs for properly producing fermented liquors, and where we are subjected to many disadvantageous circumstances. to guard against the consequences of which we must rely in some measure upon opinion formed from observation alone, and the fourth may be said to be art too precipitately carried on. Before I treat of them separately, it is requisite to mention a few general rules applicable to all. In the inquiry we made of the means which nature employs to form the juices of grapes, we found two remarkable circumstances. The first, a necessary lesser heat for the production of the fruit, and the second, a much greater for its maturation. The former useful to incline the must to fermentation, the latter to raise therein such oils as should maintain it for some time in a sound state. But in all wines an evenness of taste is requisite to affect the palate with an elegant sensation, and it may be observed, the autumn and spring heats being nearly equal, so the first juices of grapes are formed by almost uniform impressions. The summer heats, though stronger, act upon the same principle, for though the grapes remain upon the vine some part of the autumn, perhaps in this space they gain little more than the juices prepared by the summer's sun, from whence the tastes of wine are more simple than otherwise they would be. Thus are we directed that a first wort shall have the least share of heat of the whole brewing, and the last wort the greatest. Intermediate worts, if any, must be proportioned to both, and if several mashes of extracts are made to compose a wort, these must be equal as to their heat, being careful at the same time to preserve to the process the medium heat which is to govern the whole. By this means we shall obtain our intended purpose, and place into the drink one and the same smooth taste. In the table, showing the different effects produced in the grain by the different degrees of heat, the numbers, with respect to beers, express not only the mean of the degrees of dryness the malt had with those also of heat in the extracting liquors, but also is implied the power communicated by the hops, that is, it imparts to us the idea of the whole combination. As malt liquors are made with different views, so must the principles on which they are formed be varied. Beers intended long to be kept require more heat in their extracts in order to produce such oils or so many in quantity from the grain as shall retard and delay the quick effects of fermentation. And malt liquors which are soon to be brought into use claim an opposite management. This is imitating nature, for we have before observed, the hotter the autumnal, the vernal and maturating heats are, with more power do the wines resist the impressions of time and the air. And we traced the rule which governed this variety by an inquiry into the number of degrees required to form the juices of grapes, and applied their number to discover the first and last heats they were impressed with. In calculations to find out the heat to be given to water properly to resolve the malt, the same method must be followed, it being equally necessary here to employ only such a proportion of the number of degrees which constitute the whole of the fermentable principles in malt that are needful to the purpose we would answer. We have said malts continue in possession of all their constituent parts from their first degree of dryness 119 to 129 degrees. By age alone beers obtain spontaneous pellucidity, when urged in the whole of their process with a heat so great as 138 degrees, precipitation or art extends it to near 157 degrees, after which neither the acid parts furnished by the air nor art avails. An obstinate foulness is the result, from whence it may be concluded, that at or beyond this heat, so great a part of the fermentable principles is dispersed, as what remains in the grain has not power sufficient to produce transparency. The following table, founded on these principles, will hereafter be found directive to fix the first and last heats to be given to the extracts of malt. A table showing the quantity of fermentable principles residing in malts at their several degrees of dryness, or the number of constituent parts which form beers in proportion to their properties, specified in degrees, and to be used in calculations made to ascertain the proper heats to be given to the first and last extracts of malt. Mean degrees of heat affecting malt and constituent parts. 119 degrees leaves 10 parts. 124 degrees leaves 9 parts. 129 degrees leaves 8 parts. 134 degrees leaves 7 parts. 138 degrees leaves 7 parts. 143 degrees leaves 6 parts. 148 degrees leaves 5 parts. 152 degrees leaves 5 parts. 157 degrees leaves 4 parts. 162 degrees leaves 3 parts. 167 degrees leaves 2 parts. 171 degrees leaves 1 part, and 175 degrees leaves no constituent parts fermentable. Though beers and ales are divided into strong and small, this division regards only the proportion of the vehicle and not that of the constituent parts. The same means as to the heat of the extracts must be employed to form small beers capable of preserving themselves sound for some time, as are used to make strong drinks. For though a small liquor possesses more aqueous parts, the oils and salts of the malt are only more diluted, not altered in their proportions, and this causes but a very small difference in the duration of the liquor. It now remains to apply these rules deduced from the theory to the several sorts of malt liquors, which answer to the 4 modes of extraction just before laid down. The first and most perfect is, when the malt is chosen of such dryness and the extracts made with such heats as give the beers an opportunity of being improved by time and slow fermentations to become spontaneously bright and transparent. Under this head may be comprehended all pale keeping strong and all pale keeping small beers. From its name, regard must be had to the colour of the malt, and such only used as is dried the least, or by 119 degrees of heat. The hops should likewise be pale, and their quantity used in proportion to the time the drink is intended to be kept. Suppose in this case it is 10 months, 10 pounds of fine hops for every quarter of malt will be required. The highest degree of heat, or rather the medium of the highest dryness in malt, with the mean heat of the several extractions to admit of spontaneous pellucidity, we have seen in the foregoing table page 124 to be 138 degrees. And this medium is chosen as it answers not only the intent of long keeping, but of brightness also. From the medium degree of the malt's dryness and of the heat of the extracts, to determine the heat of the first and the last extract and the value in degrees of the quantity of hops to be used, for brewing pale strong and pale small beers, intended to be kept about 10 months before they are used, and expected to become self-transparent. 119 degrees the malt's dryness, and use 138 degrees the mean of malt dryness, heat of extracts, and value of hops. Subtract 3 degrees the value of 10 pounds of hops, gives 135 degrees, mean of malt's dryness and heat of extracts. For the first liquor, 135 degrees as before, less 3.5 degrees, half the number of the constituent degrees answerable to 138 degrees the mean heat of the whole process to be subtracted, gives 131.5 degrees governing the first extracts. Once again 119 degrees the malt's dryness. If we use 144 degrees, first rule to discover the heat of the first extract, they sum to 263 degrees for a mean of 131.5 degrees as above. For the last liquor, use 135 degrees as before, plus 3.5 degrees, half the number of the constituent degrees to be added, to find 138.5 the degrees governing the last extract. Once again 119 degrees the malt's dryness, If we use 158 degrees, the first rule to discover the heat of last mash, they sum to 277 degrees for a mean of 138.5 as above. The elements for forming pale strong and pale small beers intended to be kept are therefore as follows. Malt's dryness 119 degrees, value of hops 3, whole medium 138, first heat 144 plus 2 degrees, last heat 158 plus 2 degrees heat lost at the time the extract separates from the grist. The proof of this is as follows. 144 heat of the first extract, 158 heat of last extract. Sum to 302, half of which 151 degrees, mean heat of extracts. 119 degrees malt's dryness. Sum to 270, half of which 135, mean heat of malt's dryness and of heat of extracts, plus 3 degrees value of hops, 138 degrees whole mean given as above. It is necessary to add 2 degrees to the heat of every mash, such being the mean of 4 degrees constantly lost in every extract at the time they are separated from the grist and exposed to the impressions of the air. The second mode of extraction is that in which every advantage which can be procured from the corn, from art, and from time is expected. This produces such drinks as cannot become spontaneously pellucid, but require the help of precipitation. The improvement which every fermented liquor gains by long standing is very considerable. The parts of the grain, which give spirit to the wine, being, by repeated fermentations, constantly attenuated, not only become more light and pungent, but more wholesome. If, in order to give to beers more of the preservative quality, greater quantities of oils are extracted in proportion to the salts, transparency cannot take place. But when the heat employed for this purpose does not exceed certain limits, this defect may easily be remedied, and the drink be fined by precipitation. As time enables it to take up part of the very oils which at first prevented its transparency, it will by long standing and by precipitation become both brighter and stronger. Where the demand for a liquor is constant and considerable, but the quantity required not absolutely certain, it ought to be brewed in such manner that time may increase its merit and precipitation render it almost immediately ready for use. These circumstances distinguish this class of extraction and justify the preference given to porter or brown beer, which comes under the mode we are now treating of. Though transparency in beers is a sure sign of the salts and oils being in an exact proportion, it is in no wise a proof of the justness of taste. For strong salts acting on strong oils may produce pellucidity, but the delicacy and pungency of taste depend on the finer oils and the choicest salts being wholly preserved, these best admitting of fermentation and most perfectly becoming miscible with the liquor. The more volatile oils and salts of the grain if excluded, by the malt being too high dried, the consequence in the beer must be an heavy and rancid taste. The less dried the malts are, which are brewed for beers to be long kept, the hotter are the extracts required to be. But this greater heat being communicated to the grain through water, an element 800 times more dense than air, the finer parts of the corn, though acted upon by an heat which in air would disperse them, by this means are retained. It appears by the table that drinks brewed from malts affected by heats whose medium is 148 degrees, and with 12 pounds of hops to every quarter of malt, require from 6 to 12 months with precipitation to become bright. This is the age generally appointed for brown beers to be drank at, and by the table, page 133, we find the proper malts where the medium heat of the whole process is 148 degrees must be such as have been dried with 130 degrees to form this liquor, whose color as yet is expected to be full or brown without being deprived of more valuable qualifications. In the drink before examined, the number of degrees which constitute the properties of malt affected by a mean heat of 138 or 7 degrees were employed, they being intended to become in time spontaneously bright. But as this quality in the present case is required only with the assistance of precipitation, the number 5 in the table, showing the constituent parts remaining in the grain at every degree of dryness, page 168, as this corresponds to the medium 148, is undoubtedly that which must answer our purpose, both as to the nature and to the time this liquor is in general made use of. These conditions being premised, the proper degrees of the first and last extract for porter will be found by the same rules as were used before. 130 degrees malt's dryness, 148 degrees whole medium intended, 4 degrees value of hops fraction omitted, 144 degrees mean of malt's dryness and heat of extracts. For the first extract, 144 as before. 2.5, half the number of the constituent degrees to be deducted, makes 141.5, mean of malt's dryness and of the heat of the first extract. 130, malt's dryness, 153, rule to discover the first heat, added together 283, half of it 141.5 as above. For the last extract, 144 as before. 2.5, half the number of the constituent degrees to be added, makes 146.5, mean of malt's dryness and of the heat of the last extract. 130, malt's dryness, 163, rule to discover the last heat. Added together, 293, half of which 146.5 as above. The elements for brewing brown strong beers with 2 degrees added to the first and last extracts for what is lost at their parting from the malt, independent of its farther division into the respective mashes. Malt's dryness 130. Value of hops 4. Medium heat of the extracts, malt's dryness and value of hops 148. First heat 155, last heat 165. Brown beers brewed with malt so low dried as 130 degrees 20 years since would have appeared very extraordinary, and most likely at that time, when a heaviness and blackness in the drink formed its principal merit, would have been a sufficient reason to condemn the practice. But strength and elegance being now more attended to, have justified the brewer in making porter to employ malt of such degree of dryness as he shall think will best answer these purposes. As high liquors used to extract low dried malt will form a must capable to preserve itself equally a long time as an adequate liquor used to high dried malt doth, and the first of these methods having greatly the advantage of the other in point of taste, as 130 degrees of dryness in malt is one, from its change of colour, where part of its finer principles may be supposed to be evaporated. It may not be amiss to inquire if there be not reasons why malt less affected by fire should be used for manufacturing this commodity. End of section 18.
Section number 19 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Neilson, Vancouver, BC. The Theory and Practice of Brewing by COMBRUNE. Section 19 of Extraction, Part 2. The medium of the malt's dryness and of the heat of the extracts, together with the value of the hops which are to make porter, is 148 degrees. This because precipitation has been found convenient and necessary for this drink, yet when at the proper age it has undergone this last operation, it is supposed to shew itself in its best form, bright, well tasted, and strong, that is, in such state as drink should be, which becomes spontaneously transparent and is capable of preserving itself a long time. If from the value of the oils yielded by the hops, see page 180, is deducted, 148 degrees minus 4 degrees will remain 144 degrees. And by table, page 162, we find a must under the mean of 144 degrees should be formed with malt dried to 125 degrees. With this circumstance, the elements of brewing porter will be as follows: 125 malt's dryness, 148 degrees whole medium intended, minus 4 value of hops equals 144 mean of malt's dryness and heat of extracts. For the first extract, 144 as before, minus 2.5, half the number of the constituent parts to be deducted, equals 141.5 mean of the malt's dryness and the heat of the first extract. 125 malt's dryness plus 158 rule to discover the first heat equals 283. For the last extract, 144 as before, minus 2.5, half the number of constituent parts to be added, equals 146.5 mean of malt's dryness and the heat of the last extract. 125 malt's dryness plus 168 rule to discover the last heat equals 293. Elements for brewing porter with malt dried to 125 degrees and 2 degrees added to the first and to the last extracts for what heat is lost at their parting from the malt, but this independent of a further allotment of this heat to the respective mashes. Malt's dryness 125, value of hops 4, medium of the heat of the extracts, malt dryness and value of the hops 148, first mash 160, last mash 170. Whether any attempt to improve this liquor by using malt of less dryness than 125 degrees may ever be put in practice is very uncertain. Porter, if brewed with malt so low as 119 degrees, probably would succeed, for, in this case, the last mash, according to the foregoing rules, would be at the 174th degree, at which the spirit of the grain could not be dispersed, and probably the result would be a more delicate, more strong, and more vinous liquor. It may be observed that 4 degrees are charged for the quantity of hops used, as this number corresponds to the quantity proper to form beer of this denomination. A greater or less proportion of hops is sometimes allowed to this drink, on account of its better or inferior quality, of the necessity there may be to render it fit for use in a shorter time than which is commonly allowed, from 9 to 12 months. And lastly, of old, stale, or otherwise defective drinks blended with new guiles. In these cases, which cannot be too rare, the errors should be corrected only by the addition of hops, and no alteration be made, either in the dryness of the malts or in the heat of the extracts. The third mode of extraction is that which intends spontaneous transparency, but not a durable liquor. Under this head is comprehended common small beer, soon to be drank. Common small beer is supposed to be ready for use in winter from 2 to 6 weeks, and in the heat of summer from 1 week to 3. Its strength is regulated by the different prices of malt and hops. Its chief intent is to quench thirst, and its most essential properties are that in the winter it should be fine, and in the summer sound. This liquor is chiefly used in and about great trading cities, such as London, where, for want of a sufficient quantity of cellar room, drinks cannot be stowed, which, by long and slow fermentations, would come to a greater degree of perfection. The duration of this kind of liquor being short, and there being a necessity of brewing it in every season of the year, dividing it into very small quantities, easily affected in its conveyance by the external heat, generally neglected, and placed in repositories influenced by every change of air, the incidents attending it, and the methods for carrying on the process must be more uncertain, various, and complicated than those of any other liquor made from malt. The incidents attending this species of malt liquor are so many, so short of existence, so contrary to one another, and often so different from what should be expected in the different periods of the year, that an attempt to guard in just proportion against every one of them, and against what may happen, and oftentimes does not, must be fruitless. After many endeavors of this sort, which terminated in a doubtful success, we have found it most eligible to form these drinks in proportion to the principal circumstances constantly attending them, and the result was more fortunate, as, in general, the drink was able to maintain itself against that variety of temperature it met within the places allotted to it. In proportion as it is brewed in hot or cold season, we must employ every means, either to repel or attract the acids circulated in the air. For this purpose, the degree of dryness in the malt, the quantity of hops, the heat of the extracts, and the degree of temperature the wort is suffered to ferment with, must vary as such seasons do. The success in brewing common small beer greatly depends on its fermentation being retarded or accelerated in proportion to the heat of the air, and expansion being the principal effect of heat. Was a wort of this sort suffered in winter to be so cold as 40 degrees, the air would, with difficulty, if at all, penetrate the must or put it in action. This slow fermentation would not permit the beer to be ready at the time required. For these reasons, brewers let down their worts in that season at 60 degrees, whereas in summer the air of the night is made use of to get them as cold as possible, by which means a part of them may be 12 degrees colder than the medium of the heat of the day, and the whole of the worts nearly 5 degrees in the space of 24 hours. The choice of the malt as to its dryness and color for brewing this liquor should be varied in proportion to the several seasons, but custom requires it should be kept nearly to a uniform color. For this reason, when the air is so cold as the lowest fermentable degree, a greater dryness than 119 degrees is required, but the dryness of the malt forming only one part of the process, the proper medium directing the whole must be brought to its true degree by the heat given to the extracts. In the high of the summer, malt dried to 130 degrees seems to be the best, as it unites the properties of speedy readiness, preservation, and transparency, and these several characteristics are, at that time, requisite in this liquor. To come as near as possible to the inclination of the consumers, or to maintain as near as may be a uniform color, if in the hottest season malt dried to 130 is best for this purpose, the mean between this and 119, the first degree that constitutes malt, must answer nearest every intent, when the heat of the air at 40 degrees. Upon this footing, the following table will, from the proportion of these two extremes, shew the color of the grain for every season of the year. Heat in the air, 35, malt's dryness, 122, value of hops in degrees, 1. Heat in the air, 40, malt's dryness, 124, value of hops in degrees, 1. Heat in the air, 45, malt's dryness, 125, value of hops in degrees, 1. Heat in the air, 50, malt's dryness, 127, value of hops in degrees, 1. Heat in the air, 55, malt's dryness, 129, value of hops in degrees, 1.5. Heat in the air, 60, malt's dryness, 130, value of hops in degrees, 2. If common small beer was immediately to be used after being brewed and fermented, and it was free from the incidents, most of which we have just now enumerated, no hops would be required, and the medium degree of the whole process would be that of the lowest dried malt, 119, to be employed when the heat of the air was at its first fermentable degree, or 40, as with adequate malts. This would make the liqueur that would be ready in the least space, and at the same time yield its constituent parts. But if small beer was intended to be kept some short time, brewed without hops and not liable to any accidents, and the process to be carried through in a heat of air equal to the highest fermentable degree, or 80, in this case the governing medium for the whole process must be the utmost heat the grain is able to endure, where malt chars, or 175 degrees. As malt liquors are principally affected by heat, we will first proportion the medium heat directive of each process for every fermentable degree, without any regard had to any incident whatever. Fermentable degrees, 40, mean heats to govern the processes, 119. Fermentable degrees, 45, mean heat, 126. Fermentable degrees, 50, mean heat, 133. Fermentable degrees, 55, mean heat, 140. Fermentable degrees, 60, mean heat, 147. Fermentable degrees, 65, mean heat, 154. Fermentable degrees, 70, mean heat, 161. Fermentable degrees, 75, mean heat, 168. fermentable degrees 80, mean heats 175. Now, the principal heats affecting common small beer with regard to its duration are the degree of heat under which the beer is at first fermented, that of the air when brewed, and when conveyed from place to place, and that of the cellar where it is deposited. Let us, in regard to these heats, take the mean of the circumstances this drink is liable to, at the time when the air is at the first fermentable degree, and at the time when the season is hottest, taking for this the medium heat of the whole 24 hours. Having these two extremes, and making a fit allowance for hops employed, we shall be able, from the above table, to fix the medium heat that should govern the several processes for making common small beer in every season of the year. I observed in page 183 that when the heat of the air is 40 degrees, brewers set the worts of common small beer to be fermented at a heat of 60. Add to this 10 degrees more heat, excited by the fermentable action, makes 70 degrees. The heat of the air we fixed for the first extreme was the first fermentable heat, 40. In page 156, we said cellars in winter were generally 10 degrees hotter than the air, but we observed those employed for this use were the worst of the kind, subjected to exterior impressions, or perhaps other defects, for which reason we here set this heat only at 46. Total 156, divided by the number of circumstances, 3, equals 52 degrees, is the mean of the principal incidents affecting small beer in this season, and by the foregoing table, this degree indicates a medium to govern the whole process, 136, to which must be added for preservative effect bestowed by the hops used 1 degree more, which makes it at this heat in the air 137 degrees. When the mean heat of the whole 24 hours is 60 degrees, see page 150, if, as in page 183, by the advantage of the evening and night to cool the wort, an abatement of 5 degrees is obtained, the whole of the heat is 55 degrees. Add to this only 8 degrees more, because at this time the beer is divided and put in casks long before the first fermentable act is completed, and their real heat will be the medium heat of the air in the hottest season, page 150, 60. In page 156, we say the heat of the cellars in summertime is generally 5 degrees colder than the exterior air, but these being the worst of the kind may certainly be thought somewhat more exposed, though not much affected in summer as in winter, when there are fewer culinary fires. For this reason we fix their heat at 56. Total 179, divided by the number of observations, 3, equals 59 degrees, is the mean of these incidents affecting the small beer at this season. And by the foregoing table it indicates a medium heat to govern the whole process, 146 degrees, to which, if 2 degrees more be added for the effect of the hops, as experience teaches us, 6 pounds of hops in summer scarcely are so powerful as 3 pounds in winter, it will give us, for the mean of the heats drying the malt, those impressed in the extracts, together with the allowance made for the hops, 148 degrees. Spontaneous pellucidity is always expected in this drink, although the time allocated to gain this in general is much too short. To forward this intent as far as possible without hazarding the soundness of the drink, in the computations to determine the heats of the first and last extracts, the whole number of constituent parts of malt, or 10 degrees, are employed. Having premised these rules, the heats for the first and last extracts are to be found by like operations before made use of, an example of which we shall state, and knowing the mean heats required for two distinct distant processes in proportion to these, I shall form a table for brewing this drink in every season of the year. When the air is at 40, the degree of dryness fixed for malts to be used for common small beer is 124. The quantity of hops 3 pounds per quarter, the medium of their dryness, and the heat of the extracts, together with the value of the hops added thereto, is 137 degrees. 124 degrees malt's dryness. 137 medium intended minus 1 value of hops equals 136 mean of malt's dryness and heat of extracts. For the first extract, 136 as before, minus 5, half the number of the whole constituent degrees to be deducted, see page 168, equals 131. 124 malt's dryness plus 138 rolled to discover the first heat equals 262. For the last extract, 136 as before, plus 5, half the number of the whole constituent degrees to be added, see page 168, equals 141. 124 malt's dryness plus 158 rolled to discover the last heat equals 282. The proof: 138 heat of the first extract plus 158 heat of the last extract equals 296. 148 mean heat of extracts, 124 malt's dryness equals 272. 136 mean of malt's dryness and heat of extracts plus 1 value of hops equals 137 medium intended as above. The elements for forming common small beer when the heat of the air is at 40 degrees, independent of the proper division of this heat, adequate for each mash. Malt's dryness 124, value of hops 1, whole medium 137, first heat 138 and 2, last heat 158 and 2. The medium of the heat lost in the mash tun, amounting to 2 degrees, is added to the heat of the first and last mash in the following table. A table of the elements for forming common small beer at every degree of heat in the air, with the allowance of 2 degrees of heat in the first and last extractions. Heat of air 35, malt's dryness 122, value of hops 1, medium heat of the processes 135, first heat 138, last heat 158. Heat of the air 40, malt's dryness 124, value of hops 1, medium heat of the processes 137, first heat 140, last heat 160. Heat of the air 45, malt's dryness 125, value of hops 1, medium heat of the process 140, first heat 145, last heat 165. Heat of the air 50, Malt's dryness 127. Value of hops 1. Medium heat of the processes 143. First heat 149. Last heat 169. Heat of the air 55. Malt's dryness 129. Value of hops 1.5. Medium heat of the processes 146. First heat 152. Last heat 172. Heat of air 60. Malt's dryness 130. Value of hops 2. Medium heat of the processes 148. First heat 154. Last heat 174. From due observation of this table, it appears how necessary it is for brewers to be acquainted not only with the daily temperature of the air, but also with the medium heat of such spaces of time where a drink like this is expected to preserve itself. This I have estimated for every 14 days, page 150, but as the event may not always exactly correspond with our expectations, an absolute perfection in this drink as to its transparency and soundness is not to be expected. It greatly depends on the care and attention given to it, and on the temperature and quiescent state of the cellars it is placed in. The first of these circumstances is often neglected, and the other hardly ever obtained, as the places where common small beer is kept are generally the worst of the kind. In keeping beers, every circumstance is assistant to form them so as to obtain elegance in taste, strength, and pellucidity, either spontaneously or by precipitation. But in common small beer, from the shortness of its duration and from the many complicated incidents that occur, only the medium of the effect of these can be attended to, which governing medium in general differs so much from those which form more exact fermentable proportions, that in these extracts there cannot be expected that near resemblance to natural wines, which, under more favorable management, is capable of. The fourth mode of extraction is that which, by conveying a heat equal to what is practiced for keeping pale strong, and keeping pale small beers to the liquors, commonly known by the names of pale ale, amber, or twopenny, the softest and richest taste malt can possibly yield, and which makes them resemble wines formed from grapes ripened by the hottest sun. Though artfully exciting periodical fermentations, they are in a very short time made to become transparent. As wines have, in general, been named from the town or city in the neighborhood of which the grapes from which they are made are found growing, this has, though with less reason, been the case with the numerous class of soft beers and ales. These topical denominations can indeed constitute no real, or at least no considerable difference, since the birthplace of any drink is the least of all distinctions, where the method of practice, the materials employed, and the heat of the climate are nearly the same. Ales are not required to keep a long time, so the hops bestowed on them, though they should always be the finest color and best quality, are proportionately fewer in the winter than in the summer. The reason is that the consumption made of this liquor in cold weather is generally for pearl, whereas in summer it is longer on draft. It requires a more preservative quality. The properties of this liquor are that it should be pale. Its strength and taste principally depend on the malt, and its transparency should be the effect of fermentation, accelerated by every means, which will not be hurtful to it. Malt capable of yielding the strongest extracts is such whose dryness does not exceed 120 degrees, and 138 we have seen to be the highest means of the extracts, and of the dryness of the malt to admit of pellucidity without precipitation, the hops used being only so many as are necessary to resist the heat of the seasons the ale is brewed in, may in general be estimated in one value, 1 degree. From these premises, the elements for brewing this drink will be found by the same rules as before, where 10 degrees are supposed to be equal to the whole of the constituent parts, and the whole of these are employed to accelerate its coming to perfection. 120 degrees of malt's dryness. 138 degrees whole medium intended. Less 1 value of hops equals 137 mean of malt's dryness and heat of extracts. For the first extract, 137 as before, minus 5, half the number of the whole constituent degrees to be deducted, equals 132 mean of malt's dryness and the heat of the first extract. 120 malt's dryness plus 144 rule to discover the first heat equals 264. For the last extract, 137 as before, plus 5, half the number of the whole constituent degrees to be added, equals 142, mean of malt's dryness and of the heat of the last extract. 120 malt's dryness, plus 164 rule to discover the last heat of the last extract, equals 284. The elements for brewing pale ale or amber, with the allowance of 2 degrees for the heats lost in the extracts. Malt's dryness, 120. Value of hops, 1. Medium of the whole, 138. Heat of first mash, 146. Heat of last mash, 166. The time this liquor is intended to be kept should entirely be governed by the quantity of hops used therein, for this ale being required to become spontaneously fine, the medium of the whole, or 138 degrees, cannot be exceeded. In and about London, and in some counties in England, these ales, by periodical fermentations, are made to become fine, sooner than naturally they would do, and often in a shorter time than 1 week. The means of doing this, by beating the yeast into the drink, as it is termed, has by some been greatly blamed, and thought to be an ill practice, an opinion that the yeast dissolved in the drink, and thereby made it unwholesome, prevailed, and some brewers, erroneously led by this, and yet willing that their commodity should appear of equal strength with such, had undergone repeated fermentations, had been induced to add ingredients to their worts, if not of the most destructive nature, at least very unwholesome. The plain truth is that by returning the elastic air in the fermentating ale, the effects of long keeping are greatly imitated, though with less advantage as to flavor and to strength. But as this case relates to fermentation, we shall have hereafter an opportunity of explaining it more at large. It is under this class that the famous Burton ale may be ranked, and, if I do not mistake, it will be found that its qualities and intrinsic value will be the same, when judiciously brewed in London or elsewhere, from whence it may be exported at much cheaper rates to Russia and other parts than when it is increased in price by a long and chargeable land carriage. When drinks are made so strong as these generally are, only 2 mashes can take place, by which the whole virtue of the malt not being expended, small beer is made after these ales. The purest and most essential parts of the grain being extracted, it is not to be expected from an impoverished grist that beers can be made to possess all their necessary constituent parts, or to keep so long as where fresh malt is used, but the sort of small beer which answers best to the brewer and is most salubrious for the consumer must be, by the addition of fresh hops, to form the remaining strength into keeping small beer, the greater quantity of hops necessary to be allowed, beside those boiled in the ale, is 2¼ pounds for every barrel intended to be made. As much more water must be employed for this small beer, besides its length, as will steam away in 2 hours boiling, and 1/8 of a barrel per quarter of malt for waste. The heat regulating the extract of small will be found by the following rule. 138 medium heat intended for keeping small beer, minus 2 value of hops, equals 136 mean of malt dryness and heat of extract. 120 malt's dryness, plus 152 heat of the mash for keeping small after amber, 1 mash, and 1 wort, equals 272. All the hops after these 2 brewings, as those added for the keeping small beer, have been boiled but in 1 wort, are in value for the next gill of beer equal to 1/10 of fresh hops. We should now put an end to this section, but as other drinks are brewed besides those here particularly treated of, we shall just mention them, to show how their different processes are reducible to the rules just laid down. Brown ale is a liqueur, whose length is generally 2 barrels from 1 quarter of malt, and which is not intended for preservation. It is heavy, thick, foggy, and therefore justly grown in disuse. The hops used in this differ in proportion to the heats of the season it is brewed in, but are generally nearly half the quantity of what is employed. At the same time, for common small beer, the system it ought to be brewed upon is not different from that of this last liquor. The medium of the malt's dryness and the heat of the extracts are the same for each degree of heat in the air, and it requires the same management when under fermentation. But though common pale small beer and brown ale are so much alike in their theory, yet from the difference of the dryness of the malt, which for brown ale is constantly so high as 130 degrees, the practice will appear greatly different. Small beer is made after this ale, but the same rules as that made after pale ale or amber. The malt must, in that case, be valued according to the original dryness, and the medium governing the process be the same as for small beer. And, as if no extract had been taken from the grain, no small beer brewed after ales can ever be equal in goodness to such as are brewed from entire grists, but that which is made after brown ale, from the grain being so highly dried and nearly exhausted, is neither nourishing or fit to quench thirst. Brown stout is brewed with brown malt, as amber is with pale. The system for brewing these liqueurs is the same, allowing for the difference in the dryness of the malt. The overstrength of this drink has been the reason of its being discontinued, especially since porter or brown beer has been brought to a greater perfection. That which is brewed with an intent of being long kept should be hopped in proportion to the time proposed, or the climate it is to be conveyed to. Old hock requires the same proportion of hops as are used in keeping pale strong, or keeping pale small beer, but more or less, according to the time it is intended to be kept before it becomes fit for use. The length is about 2 barrels, from a quarter of the palest and best malt. As spontaneous pellucidity is required, its whole medium must not exceed 138 degrees. For the drying and extracting heat, the management of it when fermenting is under the same rules with keeping small beer, or those which are allowed as due time to become of themselves pellucid. Dorchester beers, both strong and small, range under the same head. They are brewed from barleys well germinated, but not dried to the denomination of malt. The rule of the whole, 138 degrees, for the governing medium, must, even with this grain, be observed to form these drinks. But from the slackness of the malt and the quantities of salt and wheaten flour mixed with the liquor, when under fermentation, proceed its particular taste, its mantling, and its frothy property. End of section 19. Recording by Lynda Marie Neilson, Vancouver, BC.
Section 20 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 20 of The Nature and Properties of Hops. The constituent parts of malt, like those of all vegetable sweets, are so inclined to fermentation that, when once put in motion, it is difficult to retard their progress, retain their preservative qualities, and prevent their becoming acid. Among the many means put in practice to check this forwardness of the malt, none promised so much success as blending with the extracts the juices of such vegetables as, of themselves, are not easily brought to fermentation. Hops were selected for this purpose, and experience has confirmed their wholesomeness and efficacy. Hops are an aromatic, grateful bitter, endued with an austere and astringent quality, and guarded by a strong resinous oil. The aromatic parts are volatile, and disengage themselves from the plant with a small heat. To preserve them in the processes of brewing, the hops should be put into the copper as soon as possible, and be thoroughly wetted with the first extract while the heat of the wort is at the least, and the fire under the copper has little or no effect thereon. Whoever will be at the trouble to see this performed by the means of rakes or otherwise will be made sensible that flavor is retained which, when the wort comes to boil, is otherwise constantly dissipated in the air. The bitter is of a middle nature or semi-volatile. It requires more fire to extract it than the aromatic part, but not so much as the austere or astringent. Hence it is plain that the principal virtues of this plant are best obtained by decoction, the austere parts not exhibiting themselves, but when urged by so violent and long continued boiling as is seldom or never practiced in the brewery. It would be greatly satisfactory to fix from experiments the degrees of heat that first disperse the aromatic, next the bitter, and lastly the austere parts, as it is likely by this means a more easy and certain method of judging of the true value and condition of hops than any yet known might be discovered. This vegetable is so far from being, by itself, capable of a regular and perfect fermentation that, on the contrary, its resinous parts retard the aptness which malt has to this act. Hops from hence keep barley wines sound a longer space of time, and, by repeated and slow frettings, give an opportunity to the particles of the liquor to be more separated and comminuted. Fermented liquors acquire, by this means, a greater pungency, even though it was admitted they received no additional strength from this mixture, the direct contrary of which might easily be made to appear. Hops, then, are not only the occasion of an improvement of taste, but an increase of strength. Dr. Grew seems to think the bitter of the hops may be increased by a greater degree of dryness, but perhaps this is only one of the means of their retaining longer this quality, which undoubtedly decreases through age, in a proportion, as near as can be guessed, of from 10 to 15% yearly. The varieties of the soils in which hops are planted may have some share in the inequality we perceive in them. They seem to be much benefited by the sea air. Whoever will try similar processes with the Worcester and Kentish hops will soon perceive the difference, and the general opinion strengthens this assertion, as the county of Kent alone produces nearly half the quantity of hops used in this kingdom. The sooner and the tighter hops are strained after having been bagged, the better will they preserve themselves. The opinion that they increase in weight, if not strained until after Christmas, may be true, but will not recommend the practice. The hops imbibe the moisture of the winter air, which, when the weather grows drier, is lost again, together with some of the more spirituous parts. Nor is this the greatest damage occasioned by this delay, as hops, by being kept slack-bagged in a damp season, too often become mouldy. Hops may be divided into ordinary and strong, and into old and new. The denomination of old is first given to them 1 year after they have been bagged. New ordinary hops, when of equal dryness, are supposed to be nearly alike in quality with old strong ones. The different taints with which hops are affected from the fire of the kiln afford in brewing the best rule for adapting their color to that of the malt. In general, the finest hops are the least, but the most carefully dried. To extract the resinous parts of the hops, it is necessary they should be boiled. The method of disposing them is generally to put the whole quantity in the first wort, which, being always made with waters less hot than the succeeding extracts, possesses the greatest share of acids, and is in want of the largest proportion of resins and bitters to defend it. The virtue of the hops is not entirely lost by once boiling. There remains still enough to bitter and preserve the second wort. But where the first wort is short of itself, and a large quantity of hops are required for the whole, it is needless and wasteful to put more in at once than it can absorb, the overplus of which appears by a thin, bitter pellicle floating on the wort when laid to cool in the backs. No particular rules can be given to avoid this inconveniency, as the nature and quantity of the worts on one side, and the strength of the hops on the other, must occasion a difference in the management, easily determinable by experience. When waters not sufficiently hot have been used, the wort, for want of the proper quantity of oils, readily admits of the external impressions of the air, and is easily excited to a strong and tumultuous fermentation, which disperses the bitter particles and diminishes the effects of the hops. The virtue of this plant is therefore retained in the drinks in proportion to the heat of the extracts and the slowness of the fermentation. But beers, being a composition of malt, hops, and water, united by heat, and the properties of this combination being judged of by the medium of the whole number of degrees of fire made use of in the process, as we brought the virtues of malt to this denomination, it is also essential to reduce those of hops. After many tedious calculations and experiments made with this view, and unnecessary here to mention, we were obliged to have recourse to a more simple and probable hypothesis, and confirm the truth thereof by repeated experiments, the relation of which, as it becomes here necessary, will show the necessity we were under to take a general view of the whole process before we attempted to ascertain this point. In the table showing the mean heat of the air applicable to practice, the greatest cold is 35 degrees, and in this season we observed, page 156, the repositories of beers were more warm than this by 10 degrees, which makes the greatest cold of cellars to be 45 degrees. In the same table, the highest heat is 60, when cellars are 5 degrees colder than the external airs. The utmost difference, then, in the temperature of cellars is 10 degrees, and this takes place in 6 months, so that the whole variety of heat beers deposited for keeping undergo in 1 12-month is 20 degrees. There is no specie of beer in brewing of which it is requisite the artist should be more attentive to alter his process in proportion to the change of heat in the air than common small beer, which, though brewed in every season, is constantly expected to be in an uniform order for use. In the preceding section, in the table directing this variety, we find a difference of 5 degrees of heat in the air requires an alteration in medium heat of the whole process of 3 degrees. And as it is from the mean heat of the dryness of the malt, of the heat of the extracts, and of the value of hops in degrees, that we are to discover the quantity of fire to be given to the extracts, This can be done only by deducting from such medium so much as it is affected by the properties of the hops. Just before we have seen that the whole of the variety of heat beers deposited in cellars to keep 12 months undergo amounts to 20 degrees, these in a proportion of 5 to 3 would be 12, without being scrupulously exact. Hops, with regard to their proportion in the whole process, must be admitted to be 1/3 part thereof, and in this case, of the proportion 12 now found, only 4 degrees would be what they contribute towards preserving the drink 12 months. The quantity of hops necessary to maintain beers in a sound state this space of time we have found to be 12 pounds. This quantity, then, is equal to 4 degrees of the medium heat of the whole process. On these grounds, we repeatedly tried the experiment in a variety of brewings made for different purposes, and never found any inconveniencies from the estimating hops in such like proportion. Hops should be used in proportion to the time the liquors are intended to be kept, and to the heat of the air in which they are fermented. The quantity requisite to preserve beers 12 months, experience has shown to be 12 pounds, of a good quality, joined to 1/4 of malt, and when the heat of the air is at 40 degrees, 3 pounds to every quarter has been found sufficient to preserve drinks from 4 to 6 weeks, as 6 pounds are to keep them the same term when the thermometer is so high as 60 degrees. From these facts, founded on informations obtained from long practice, we shall hereafter ascertain the proper quantities to be used in all cases. Having premised these observations sufficiently accurate for the government of this art, the construction as well as utility of the following tables will be obvious. A table of the value of the hops expressed in degrees to be added to the medium of the dryness of the malt and of the heat of the extracts. Hops, 15 pounds equal 5 degrees new or strong, 3 3/4 degrees pale, low dried, or old. 12 pounds equal 4 degrees new or strong, 3 degrees pale, low dried, or old. 8 pounds equal 2 degrees new or strong, 2 degrees pale, low dried, or old. 4 pounds equal 1 degree new or strong, 1 degree pale, low dried, or old. A table of the quantity of hops requisite for every quarter of malt brewed for porter, supposed to be fit for use from 8 to 12 months. Old ordinary hops started over old beer, 14 pounds per quarter. Ditto neat guiles, 12.5 pounds per quarter. Strong good old hops, when started over old beer, 12.5 pounds per quarter. Ditto neat guiles, 12 pounds per quarter. New strong hops, when started over old beer, 12 pounds per quarter. Ditto neat guiles, 11.5 pounds per quarter. New ordinary hops, started over old beer, 12.5 pounds per quarter. Ditto neat guiles, 12 pounds per quarter. Nota bene. The quantity of old beer to be blended with new is here supposed never to exceed 1/8 part of the whole. A table of the quantity of hops requisite for common small beer for each quarter of malt in every season. Heat in the air 35 degrees. New hops 2 pounds 8 ounces. Old hops 2 pounds 8 ounces. Heat in the air 40 degrees. New hops 3 pounds 0 ounces. Old hops 3 pounds 0 ounces. 45 degrees. New hops 3 pounds 8 ounces. Old hops 3 pounds 8 ounces. 50 degrees. New hops 4 pounds 4 ounces. Old hops 4 pounds 8 ounces. 55 degrees. New hops 5 pounds 0 ounces. Old hops 5 pounds 8 ounces. 60 degrees. New hops 6 pounds 0 ounces. Old hops 6 pounds 8 ounces. 65 degrees. New hops 6 pounds 12 ounces. Old hops no entry. 70 degrees. New hops 7 pounds 8 ounces. Old hops no entry. 75 degrees. New hops 8 pounds 4 ounces. Old hops no entry. 80 degrees. New hops 9 pounds 0 ounces. Old hops no entry. The medium heat of the hottest days in England in the shade seldom at any time exceeds 60 degrees, but I continued the table proportionably, as what is here set down is from repeated experiments, and from thence it appears, at the lowest fermentable degree of heat, 3 pounds of hops are required for each quarter of malt. At the highest, 9 pounds of hops should be allowed for the same quantity. This, in some measure, determines the effect of a greater activity in fermentation. A table of the quantity of hops necessary to each quarter of malt in brewing amber or twopenny. Heat in the air 35 degrees. New hops 2 pounds 8 ounces. Old hops 2 pounds 8 ounces. Heat in the air 40 degrees. New hops 3 pounds 0 ounces. Old hops 3 pounds 0 ounces. 45 degrees. New hops 3 pounds 8 ounces. Old hops 3 pounds 8 ounces. 50 degrees. New hops 4 pounds 0 ounces. Old hops 4 pounds 4 ounces. 55 degrees. New hops 4 pounds 8 ounces. Old hops 4 pounds 12 ounces. 60 degrees. New hops 5 pounds 0 ounces. Old hops 5 pounds 4 ounces. Amber is a liquor which, by repeated periodical fermentations, is so attenuated as to be soon fit for use, and, by its strength, is supposed to resist the impressions of the air longer than common small beer, especially in winter. For this reason it wants fewer hops than that drink does, and in the summer both require equal quantities on account of the fermentation of amber being carried to a greater degree. The hops once boiled in amber, but used afterwards for small beer, may be estimated equal to 1/4 of their original quality. When 12-shilling small beer is made after amber, the quality of the hops used should at least be equal in value to the quantity of 10 pounds fresh hops to every 5 barrels of beer, when brewed from entire grists of malt for this purpose. A table of the quantity of hops necessary for each quarter of malt in brewing Burton ale. This liquor requires fewer hops than such ales as are more diluted by water. As it is always brewed in the winter, The quantities here set down are for the number of months it is supposed to be kept before it is drank or bottled. 1 month, 1 pound 0 ounces. 2 months, 1 pound 8 ounces. 3 months, 2 pounds 0 ounces. 4 months, 2 pounds 8 ounces. 5 months, 3 pounds 0 ounces. 6 months, 3 pounds 8 ounces. 7 months, 4 pounds 0 ounces. 8 months, 4 pounds 8 ounces. 9 months, 5 pounds 5 ounces. 10 months, 5 pounds 8 ounces. 11 months, 6 pounds 0 ounces. 12 months, 6 pounds 8 ounces. Though common amber, keeping amber, and Burton ales require the same degree of heat to govern the whole of their processes, yet some small difference will be found in the heats of their extracts on account of the different quantity of hops used. Besides the use of hops for keeping the musts of malt, they may also, with great propriety, be employed both to strengthen and preserve sound the extracts. 1 or 2 pounds in a net suspended in the water the mash is to be formed with are sufficient for this purpose. Though the purchasing the materials used in manufacture does not immediately relate to its practical part, yet, as in this case, it is of great importance to the brewer to know what stock it is prudent for him to keep of an ingredient equally necessary and variable in its value. I hope the attempt of a calculation on this subject will easily be pardoned. The amount of the duty upon hops for 16 years, from 1748 to 1765, was £1,171,227, which sum, estimating the duty at 21 shillings per bag, gives 1,115,454 bags used in that time. At the beginning and expiration of this interval, hops sold at such high prices as no considerable stock can be supposed to have remained in hand, namely, from 8 pounds to 10 pounds per hundred. If therefore to the aforesaid quantity of 1,115,454 bags, which may be supposed to have served for the whole consumption during this period, we add what may have escaped paying duty, the annual consumption of hops may be estimated at 70,000 bags, including what is exported to Ireland or elsewhere. From these premises, the following table was constructed, which, though not capable of absolute certainty, may be of some service to the brewers in informing them of the quantities that probably remain in hand at any time, and the stock which prudence will suggest to them to lay in. A table showing the medium price hops should bear in proportion to the growth, and determining the quantity to be purchased in proportion to the stock in hand. Price of hops at a medium per hundredweight, 30 shillings. Stock of new and old hops in the whole kingdom after the harvest, 130,000 bags. Quantity of hops equal to as many weeks' consumption, 70 bags. Price of hops at a medium per hundredweight, 35 shillings. Stock of new and old hops in the whole kingdom after the harvest, 125,000 bags. Quantity of hops equal to as many weeks' consumption, 65 bags. Price per hundredweight, 40 shillings. Stock of new and old hops, 120,000 bags. Quantity of hops, 61 bags. Price per hundredweight, 45 shillings. Stock of new and old hops, 115,000 bags. Quantity of hops, 57 bags. Price per hundredweight, 50 shillings. Stock of new and old hops, 110,000 bags. Quantity of hops, 53 bags. Price per hundredweight, 55 shillings. Stock of new and old hops, 105,000 bags. Quantity of hops, 47 bags. Price per hundredweight, 60 shillings. Stock of new and old hops, 100,000 bags. Quantity of hops, 44 bags. Price per hundredweight, 70 shillings. Stock of new and old hops, 95,000 bags. Quantity of hops, 40 bags. Price per hundredweight, 80 shillings. Stock of new and old hops, 90,000 bags. Quantity of hops, 36 bags. Price per hundredweight, 90 shillings. Stock of new and old hops, 85,000 bags. Quantity of hops, 32 bags. Price per hundredweight, 100 shillings. Stock of new and old hops, 80,000 bags. Quantity of hops, 28 bags. Price per hundredweight, 110 shillings. Stock of new and old hops, 75,000 bags. Quantity of hops, 24 bags. Price per hundredweight, 120 shillings. Stock of new and old hops, 75,000 bags. Quantity of hops, 20 bags. Price per hundredweight, 130 shillings. Stock of new and old hops, 70,000 bags. Quantity of hops, 16 bags. Price per hundredweight, 140 shillings. Stock of new and old hops, 67,000 bags. Quantity of hops, 12 bags. Price per hundredweight, 150 shillings. Stock of new and old hops, 65,000 bags. Quantity of hops, 8 bags. Price per hundredweight, 160 shillings. Stock of new and old hops, 62,000 bags. Quantity of hops, 4 bags. Price per hundredweight, 170 shillings. Stock of new and old hops, 60,000 bags. Quantity of hops, no entry. Price per hundredweight, 180 shillings. Stock of new and old hops, 57,000 bags. Quantity of hops, no entry. Price per hundredweight, 190 shillings. Stock of new and old hops, 55,000 bags. Quantity of hops, no entry. Price per hundredweight, 200 shillings. Stock of new and old hops, 52,000 bags. Quantity of hops, no entry. This chapter should not be dismissed without reminding the brewery of the gross imposition they submit to in purchasing hops. The tare which justice requires to be allowed in the sale of all packed merchandise by the hop factors is refused, who exact payment for the bagging at the same price as for the commodity itself. If the consumption of hops in England is yearly 172,268 hundredweight, and these be packed 1/2 in bags and the other half in pockets, taking the mean price of hops to be £3 14s per hundredweight. In this case, the consumers are defrauded at least of £39,834 per annum. That, on a just regulation of this matter, the commodity itself would rise in price, there is not the least foundation for. The present practice of monopolizing hops, by much too frequent, is a farther reason to induce the brewery to exert the influence they ought to have with superior power, to obtain a right so justly due to them. End of section 20.
Section 21 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 21. Of the lengths necessary to form malt liquors of the several denominations. By length, in the brewery, is understood the quantity of drink made from 1 quarter of malt. Beers and ales differ in this respect, and the particular strength allowed to every sort of drink varies also somewhat, according to the prices of the materials. This increase or abatement is, however, never such as to make the profits certain or uniform, for the value of the grain being sometimes double of what it is at other times, a proportionable diminution in strength can by no means take place. It might be expected to find here tables determining the differences in strength and quality of each drink, in proportion to the prices and the expenses of the brewer. But this, for many reasons, would be inconvenient, and in some respects impracticable. He who chooses to be at this trouble ought not only to take into the account the prices of malt and hops, but the hazards in the manufacturing them, those of leakage, of bad cellars, of careless management, the frequent returns attended with many losses, the wearing out of utensils, and especially of casks, which last article engrosses at least 1/5 of the brewer's capital, the charges of servants, horses, and carriages, for the delivery of the drinks, the duties paid immediately to the government, without any security for the reimbursement, the large stock and credit necessary to carry on this trade, and many other incidents, hardly to be estimated with a sufficient accuracy, and never alike to every brewer. In general, it appears, when malt and hops are sold at mean prices, the value of what is employed of these is equal to the charge attending the manufacture, or of about half the value of the drinks. Hence, this conclusion, sensibly felt by every honest trader, that from change of circumstances the reputation of the profits has outlived the reality of them, and that a trade, perhaps the most useful to the landed interest, to the government, and to the public, of any seems distinguished from all by greater hazards and less encouragement. But in a treatise like this, where only the rules upon which true brewing is founded are laid down, I would avoid anything that might, though undesignedly, give handle to invidious reflections and ill-timed controversies. I therefore content myself with setting down the latitudes of the lengths which should be made for drinks of every denomination. Lengths of beers according to the excise gauges observed within the bills of mortality or the Winchester measure. From 1 quarter of malt. Length of common small beer 4 1/4 barrels to 5 1/4. Length of keeping small beer 4 3/4 barrels to 5 1/2. Length of amber or pale ale 1 1/2 barrel to 1 3/4. Length of brown, strong, or porter 2 1/4 barrels to 2 3/4. Length of burnt nail, 1 barrel to 1 1/4. End of section 21. Recording by Monika MC.
Section 22 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elsie Selwyn. The Theory and Practice of Brewing by Michael COMBRUNE. Section 22. Method of calculating the height in the copper at which worts are to go out. The expected quantities or lengths of beer and ale can only be found by determining at what height in the copper the worts must be when turned out. Brewers have several methods of expressing to what part they would have the worts reduced by boiling. Brass is the technical appellation for the upper rim of the copper. It is a fixed point from which the estimation generally takes place, either by inches or by the nails, which rivet the parts of the copper together. These last are not very equal, either in the breadth of their heads or their distances from each other. Inches, then, though not specified on the copper, but determined by the application of a gauge on which they are marked, claim the preference. The necessity of coppers being gauged in the contents of what they contain on every inch, both above and below brass, must appear in a stronger light, the nearer we bring the art to exactness. The following tables will show the most useful manner in which I conceive this gauging should be specified. Gauges of coppers. Great copper, set up November 30th, 1750. 17 inches above brass. Current of great copper allowed. 15 barrels, 3 firkins, 4 gallons. 16 inches above brass. Current of great copper allowed. 15 barrels, 2 firkins, 1 gallon. 15 inches above brass. Current of great copper allowed. 15 barrels, 0 firkins, 5 gallons. 14 inches above brass. Current of great copper allowed. 14 barrels, 2 firkins, 8 gallons. 13 inches above brass. Current of great copper allowed. 14 barrels, 1 firkin, 4 gallons. 12 inches above brass. Current of great copper allowed. 13 barrels, 3 firkins, 7 gallons. 11 inches above brass. Current of great copper allowed. 13 barrels, 2 firkins, 3 gallons. 10 inches above brass. Current of great copper allowed. 13 barrels, 0 firkins, 6 gallons. 9 inches above brass. Current of great copper allowed. 12 barrels, 3 firkins, 2 gallons. 8 inches above brass. Current of great copper allowed. 12 barrels, 1 firkin, 5 gallons. 7 inches above brass. Current of great copper allowed. 12 barrels, 0 firkins, 1 gallon. 6 inches above brass. Current of great copper allowed. 11 barrels, 2 firkins, 4 gallons. 5 inches above brass. Current of great copper allowed. 11 barrels, 0 firkins, 8 gallons. 4 inches above brass. Current of great copper allowed. 10 barrels, 3 firkins, 3 gallons. 3 inches above brass. Current of great copper allowed. 10 barrels, 1 firkin, 7 gallons. 2 inches above brass. Current of great copper allowed. 10 barrels, 0 firkins, 2 gallons. 1 inch above brass. Current of great copper allowed. 9 barrels, 2 firkins, 6 gallons. At the brass. Current of great copper allowed. 9 barrels, 1 firkin, 1 gallon. 1 inch below the brass. Current of great copper allowed. 8 barrels, 3 firkins, 8 gallons. 2 inches below the brass. Current of great copper allowed. 8 barrels, 2 firkins, 6 gallons. 3 inches below brass. Current of great copper allowed. 8 barrels, 1 firkin, 4 gallons. 4 inches below brass. Current of great copper allowed, 8 barrels, 0 firkins, 2 gallons. 5 inches below brass. Current of great copper allowed, 7 barrels, 2 firkins, 8 gallons. 6 inches below brass. Current of great copper allowed, 7 barrels, 1 firkin, 6 gallons. 7 inches below brass. Current of great copper allowed, 7 barrels, 0 firkins, 4 gallons. 8 inches below brass. Current of great copper allowed, 6 barrels, 3 firkins, 3 gallons. 9 inches below brass. Current of great copper allowed, 6 barrels, 2 firkins, 2 gallons. Little copper, set up August 3rd, 1753. 15 inches above brass. Current of little copper allowed, 11 barrels, 2 firkins, 7 gallons. 14 inches above brass. Current of little copper allowed, 11 barrels, 1 firkin, 5 gallons. 13 inches above brass. Current of little copper allowed, 11 barrels, 0 firkins, 3 gallons. 12 inches above brass. Current of little copper allowed, 10 barrels, 3 firkins, 1 gallon. 11 inches above brass. Current of little copper allowed, 10 barrels, 1 firkin, 7 gallons. 10 inches above brass. Current of little copper allowed, 10 barrels, 0 firkins, 6 gallons. 9 inches above brass. Current of little copper allowed, 9 barrels, 3 firkins, 4 gallons. 8 inches above brass. Current of little copper allowed, 9 barrels, 2 firkins, 2 gallons. 7 inches above brass. Current of little copper allowed, 9 barrels, 0 firkins, 8 gallons. 6 inches above brass. Current of little copper allowed, 8 barrels, 3 firkins, 6 gallons. 5 inches above brass. Current of little copper allowed, 8 barrels, 2 firkins, 5 gallons. 4 inches above brass. Current of little copper allowed, 8 barrels, 1 firkin, 3 gallons. 3 inches above brass. Current of little copper allowed, 8 barrels, 0 firkins, 1 gallon. 2 inches above brass. Current of little copper allowed, 7 barrels, 2 firkins, 7 gallons. 1 inch above brass. Current of little copper allowed, 7 barrels, 1 firkin, 5 gallons. At the brass, current of little copper allowed, 7 barrels, 0 firkins, 5 gallons. 1 inch below brass, current of little copper allowed, 6 barrels, 3 firkins, 5 gallons. 2 inches below brass. 6 barrels, 2 firkins, 5 gallons. 3 inches below brass. Current of little copper allowed, 6 barrels, 1 firkin, 5 gallons. 4 inches below brass. Current of little copper allowed, 6 barrels, 0 firkins, 5 gallons. 5 inches below brass. Current of little copper allowed, 5 barrels, 1 firkin, 5 gallons. 6 inches below brass. Current of little copper allowed, 5 barrels, 2 firkins, 5 gallons. 7 inches below brass. Current of little copper allowed, 5 barrels, 1 firkin, 5 gallons. 8 inches below brass. Current of little copper allowed, 5 barrels, 0 firkins, 5 gallons. 9 inches below brass. Current of little copper allowed, 4 barrels, 3 firkins, 4 gallons. 10 inches below brass. Current of little copper allowed, 4 barrels, 2 firkins, 5 gallons. 11 inches below brass. Current of little copper allowed, 4 barrels, 1 firkin, 6 gallons. By the foregoing table, it is seen that my great copper holds nearly 9 barrels of water to brass, and as the difference of the volume between boiling worts of most denominations and cold water is nearly as 7 to 9, the quantity it will yield of boiling worts will be but 7 barrels. The diameter of this copper, just above brass, is 68 inches at a medium, and at that mean it holds 12 gallons, 7 pints of cold water, or nearly 11 gallons of boiling worts upon an inch. Hops macerated by being twice boiled take up for every 6-pound weight of volume in the copper equal to 4 gallons and a half of water, or a pin. In a copper, the gauges of which have just been set down, it is required to know what number of inches a length of 24 barrels must go out at, with 15 pounds of hops, the guile of beer to be brewed at 2 worts. 24 barrels length of beer minus 14 barrels for 2 full brass equals 10, plus 34 numbers of gallons to a barrel accounted by the excise out of the bills of mortality equals 40 hops twice put in 15 pounds is 30. 40 hops twice put in 15 pounds is 30. 30 hops is equal to 30 gallons. 6 pounds and 30 ounces times 5 times 4.5 equals 22. 340 gallons of boiling wort upon an inch plus 22 equals 11 gallons 362 pints. 3 inches above brass the 2 worts to go out together. When 3 worts are boiled, the amount of 3 full brasses must be deducted from the length, and as the hops go into the copper 3 times, they become more macerated and take up much less room. The proportion is then nearly 13 or 14 pounds of hops for each 4 gallons and a half. Thus in copper, which have never been tried or used, we are able by the gauges alone to determine our lengths, but as their circumferences are not always exact, and the worts are of very different strengths, we should never neglect such trials as may bring us nearer to accuracy and truth. End of section 22.
Section 23 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avayi in December 2019. The Theory and Practice of Brewing by Michael COMBRUNE. Section 23 of Boiling. It has been a question whether boiling is necessary to a wort, but as hops are of a resinous quality, the whole of their virtues are not yielded by extraction. Decoction or boiling is as needful as the plant itself, and is, together with extraction and fermentation, productive of that uniformity of taste in the compound which constitutes good beer. Worts are composed of oils, salts, water, and perhaps some small portion of earth, from both the malt and hops. Oils are capable of receiving a degree of heat much superior to salts, and these again surpass in this respect the power of water. Before a wort can be supposed to have received the whole of the fire it can admit of, such a degree of heat must arise as will be in a proportion to the quantity of the oils, the salts, and the water. When this happens, the wort may be said to be intimately mixed and to have but one taste. The fire, made fiercer, would not increase the heat, or more exactly blend together the constituent parts. This purpose once obtained, the boiling of the wort is completed. It follows from thence that some worts will boil sooner than others, receive their heat in a less time, and be saturated with less fire. But, as it is impossible, and indeed unnecessary, to estimate exactly the quantities of oils, salts, and water contained in each different wort, it is out of our power previously to fix, for any one, the degree of heat it is capable of. This renders the thermometer in this case useless, and obliges us to depend entirely on experiment, and to observe the signs which accompany the act of ebullition. Fire, as before has been mentioned, when acting upon bodies endeavors to make its way through them in right lines. A wort set to boil makes a resistance to the effort of fire in proportion to the different parts it is composed of. The watery particles are, it is imagined, the first which are saturated with fire, and becoming lighter in this manner endeavor to rise above the whole. The salts are next, and last of all the oils. From this struggle proceeds the noise heard when the wort first boils, which proves how violently it is agitated, before the different principles are blended one with another. While this vehement ebullition lasts, we may be sure that the wort is not intimately mixed, but when the fire has penetrated and united the different parts, the noise abates, the wort boils smoother, the steam, instead of clouding promiscuously as it did at first round the top of the copper, rises more upright, in consequence of the fire passing freely in direct lines through the drink, and when the fierceness of it drives any part of the drink from the body of the wort, the part so separated ascends perpendicularly. Such are the signs by which we may be satisfied the first wort, or the strongest part of the extracts, has been so affected by the fire as to become nearly of one taste. If, at this time, it is turned out of the copper, it appears pellucid, and forms no considerable sediment. The proper time for the boiling of a wort hitherto has been determined, without any regard to these circumstances. Hence the variety of opinions on this subject, greater perhaps than on any other part of the process. While some brewers would confine boiling to so short a space as 5 minutes, there are others who believe 2 hours absolutely requisite. The first allege that the strength of the wort is lost by long boiling, but this argument will not hold good against the experiment of boiling a wort in a still and examining the collected steam, which appears little else than mere water. Those who continue boiling the first wort a long time do it in order to be satisfied that the fire has had its due effect, and that the hops have yielded the whole of their virtue. They judge of this by the wort curdling and depositing flakes like snow. If a quantity of this sediment is collected, it will be found to the taste both sweet and bitter, and if boiled again in water, the decoction, when cold, will ferment, and yield a vinous liquor. These flakes, therefore, contain part of the strength of the wort. They consist of the first and choicest principles of the malt and hops, and, by their subsiding, become of little or no use. It appears, from these circumstances, that boiling a first wort too short or too long a time is equally detrimental, that different worts require different times, and these times can only be fixed by observation. The first wort having received, by the assistance of the fire, a sufficient proportion of bitter from the hops, is separated therefrom. The hops, being deprived of part of their virtues, are, on the other hand, enriched with some of the glutinous particles of the malt. They are afterwards, a second, and sometimes a third time, boiled with the following extractions, and thereby divested not only of what they had thus obtained, but also of the remaining part of their preservative qualities. The thinness and fluidity of these last worts render them extremely proper for this purpose. The heat is never so intense as that of the first when boiling, for, as they consist of fewer oils, they are incapable of receiving so great a degree of heat. This deficiency can only be made up by doubling or tripling the space of time the first wort boiled, so that what is wanted in the intenseness of heat may be supplied from its continuance. The following table is constructed from observations made according to the foregoing rules. It may perhaps be objected that, by a long boiling of the last worts, the rough and austere parts of the hops may be extracted, and give a disagreeable taste to the liquor, but it should be observed this only happens either in beers to be long kept, or in such as are brewed in very hot weather. In the first case the roughness wears off by age, and grows into strength, and in the last it is a check to the proneness musts have in such seasons to ferment. One observation more is necessary under this head. Most coppers, especially such as are made in London and set by proper workmen, waste or steam away, by boiling, about 3 or 4 inches of the contained liquor in each hour. the quantity wasted being found on trial, and knowing how much water the copper holds upon an inch, what is steamed away by boiling in each brewing may easily be estimated. End of section 23.
Section 24 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elsie Selwyn. The Theory and Practice of Brewing by COMBRUNE. Section 24. Of the quantity of water wasted and of the application of the preceding rules to two different processes of brewing. Wastewater in brewing is that part which, though employed in the process, yet does not remain in the beers or ales when made. Under this head is comprehended the water steamed away in the boiling of the worts, that which is lost by heating for the extracts, that which the utensils imbibe when dry, that which necessarily remains in the pumps and underback, and more than all, the water which is retained in the grist. The fixing to a minute exactness how much is thus expended is both impossible and unnecessary. Every one of the articles just now mentioned varies in proportion to the grist, to the length made, to the construction and order of the utensils, and to the time employed in making the beer. To these different causes of the steam being lessened or increased might be added every change in the atmosphere. However, as upon the whole the quantity of water lost varies from no reason so much as from the age and dryness of the malt, experience is, in this case, our sole and surest guide. I have in the following table placed under every mode of brewing how much I have found necessary to allow for these several wastes and evaporations. Brown strong and pale strong beers. For old malts, allow 1 barrel pin, 5 per quarter. For new malts, allow 2 barrels pins, 0 per quarter. Keeping small and common beers. For either new or old malt, allow 2 barrels pins, 4 per quarter. Amber or pale ales, for either new or old malt, allow 1 barrel pin, 5 per quarter. Keeping small or common small after amber, allow for waste 0 barrel pins, 2 per quarter. It is now time to begin the account of two brewings, which admit of the greatest variety, both in themselves and the season of the year. The same processes will be carried on in the sequel of this work until they be completed. On the 10th of July, a brewing of common small beer is to be made with 6 quarters of malt. By page 150, the medium heat of the air at this time is 60 degrees. By page 184, the malt to be used for this purpose should be in dryness at 130 degrees. By page 210, the proper quantity of new hops is 6 pounds per quarter. The length, according to the excise gauge without the bills of mortality, may be rated at 5 barrels 1/8 per quarter, or from the whole grist at 30 barrels 3/4 per quarter. See page 219. By page 222, the inches required in the copper to bring out this length at 2 worts will be, for copper set gauged page 221, 56 inches in the 2 worts above brass. The state of this part of the brewing is therefore 6 quarters of malt dried to 130 degrees, 36 pounds of hops for 30 barrels 3/4 to go out at 56 inches above brass. 30 3/4 barrels length, 5 1/4 barrels for boiling by page 228, 1 wort 1 hour and a half or 5 inches, 2 wort 3 hours or 9 inches. 15 barrels wastewater, page 231. Together equals 51 barrels, whole quantity of water to be used. And by page 191, we find the heat of the first extract to be 154 degrees, and the heat of the last 174 degrees. The other brewing of which I propose to lay down the process in this treatise is one for brown beer, or porter of 11 quarters of malt, to be brewed on the 20th of February. By page 150, the medium heat of the air at this time is 40 degrees. By page 174, the malt to be used for this purpose should be at 130 degrees. By page 209, the quantity of hops is 12 pounds per quarter. The length I would fix for this liquor, according to the excise gauge without the bills of mortality, is 2 barrels and 4 pins from a quarter, or from the whole grist 27 barrels 1/2. See page 219. By page 222, the inches required in a copper, such as I have specified, page 221, to bring out this length at 3 worts are 31 above brass. The state of this brewing, so far as we have considered it, is therefore 11 quarters malt dry to 130 degrees, 132 pounds of hops for 27 barrels 1/2, to go out at 31 inches above brass. 27.5 barrels the length, 8 1/4 barrels boiling by page 228, 1 wort 1 hour or 4 inches, 2 wort 2 hour or 6 inches, 3 wort 4 hours or 12 inches, 18 barrels wastewater, page 231 old malt, 1 5/8 per quarter. Altogether equals 54 barrels, whole quantity of water to be used. And by page 177, we find the heat of the first extract to be 155 degrees and the heat of the last extract to be 165. End of section 24.
Section 25 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 25. Of the division of the water for the respective worts and mashes, and of the heat adequate to each of these. That the whole quantity of water, as well as that of the heat required, ought not in any brewing at once to be applied to the grist, is obvious both from reason and from the example of nature, who, in forming the juice of the grape, divides the process, and increasingly successfully both the moisture and the heat gives time to each degree to have its complete effect. A division of the water and heat to form malt liquors is equally necessary, but previous to this division the following general rules may be laid down. The grist, if possible, is at no time to be left with less water than what will cover the malt, to put all its parts in action. In the first mashes for strong beer, an allowance is to be made for nearly as much water as the grist will imbibe. And lastly, the whole quantity of water used in brewing should be divided, in a proportion analogous to that of the degrees of heat. Processes for brewing are carried on either with 1 copper or with 2. Though the first of these methods is almost out of use, it may be necessary to give an example or two of the division of the water used in this case, the doing which will point out the absurdity of this practice. In brewing with 1 copper, scarcely more than 3 mashes can be made. Otherwise, the time taken up in boiling the worts and preparing the subsequent waters for extraction would be so long and to cause the grist to lose great part of its head, and, in warm weather, perhaps to become sour. The whole water required might naturally be divided into 3 equal parts, was it not for the quantity at first imbibed by the grist. But as, in this way of brewing, the best management is to make the first wort of 1 mash, and the second wort of the other 2, it will be found necessary to allow, for the first extracting water, 4 parts out of 7 of the whole quantity required, and to divide the remainder equally for the other 2 mashes. Thus, if the whole quantity of water required was 51 barrels, the lengths of the extracting waters would be as follows: 1 liquor over 29 barrels over 1 wort, 2 liquor over 11 barrels, 2 wort, 3 liquor over 11 barrels, 2 wort. The water imbibed and retained by the malt is allowed for this computation, which will be found just to every purpose for small beer brewed in 1 copper only. But in strong beers and ales with 3 mashes, whether brewed at 1, 2, or 3 worts, the case will be somewhat different, as care should always be taken to reserve for every mash a sufficient quantity of water to apply to the grist. For this reason, no greater proportion ought to be used in the first mash than that of 3 parts out of 7, and the volume of the malt is in a greater proportion to the quantity of water than in the preceding case. If, therefore, the whole quantity of water used was 35 barrels, the lengths of the liquor would be 1 liquor, 15 barrels, 2 liquor, 10 barrels. 3 liquor, 10 barrels. Employing only 1 copper must from hence appear and is allowed to be bad management. For, in some part or other of the process, however well contrived, the business must stand still and consequently the extracts be injured by the air continually affecting them. The best and most usual practice, and that which here will be set an example, is to brew with 2 coppers. Other rules consequently are necessary to be observed, and I shall be more particular in the explanation of them. To preserve order and to convey our ideas in the clearest manner, we shall make use of the 4 modes of brewing we mentioned in the 4th section. The first of these, which implies keeping pale, strong, and keeping pale small beers to become spontaneously fine, are best brewed with 2 worts and 4 mashes, to allow for what is imbibed by the grist, and what is steamed away during the first part of the process, 4/7 of the whole of the water employed, and consequently a like proportion of the number of degrees which constitute the difference between the first and last heats of the whole brewing, are required for the first wort and the remainder to the last or second. The proportion as to the water is permanent, but having now only a division of heat in the progressive state for the temperature to be given to the extracts, to put in practice the principles laid down in pages 64-65, the first wort, however composed of several mashes, must be of one uniform heat, though less than that of the second, whose extracts, though more powerful, must, notwithstanding, be of equal heat amongst themselves. According to the rules laid down in section 8, the whole quantity of water requisite for a guile of keeping pale strong, or keeping pale small beer, is 51 barrels. In page 171 we found, including the heat lost at the time of extract separates from the grist, the first heat to form this process to be 144 degrees, and the last 158 degrees. The quantity of water and the difference between these 2 degrees are required to be divided in such proportions as are best applicable to the purpose we intend. Water, 51 barrels, multiplied by 4, divided by 7, 204, gives 29 barrels for the first wort, and this deducted from 51, leaves 22 barrels for the second wort. The 29 barrels equally divided between the 2 first mashes is 14 barrels and a half for each, and the 22 barrels equally divided between the 2 last mashes is 11 barrels for each. The last heat for pale keeping beers is 160 degrees, and the first is 146 degrees. Their difference is 14. This, as above, multiplied by 4, and divided by 7, is 56, leaves 8 degrees. The proportion to be allotted to the first wort, and 6 degrees, the remainder, to the last, in a regular progressive state, the elements for this brewing would stand as under: malt dryness, 119 degrees. Value of hops, 3 degrees. Whole medium, 138 degrees. First mash, 146 degrees. Second mash, 154 degrees. Third mash, 157 degrees. Fourth mash, 160 degrees. First mash, 14.5 barrels. Second mash, 14.5 barrels. Third mash, 11 barrels. Fourth, 11 barrels. But more exactly, to imitate the fermented liquors formed by nature, our first wort, answering to the germinating part of her process, must be one of the uniform heat in the extracts, and must likewise our second wort, see page 165. The mean, then, of the progressive heats of the first wort will be that which must be applied both to the first and second mashes, and the mean of the progressive heats of the second wort, that which must direct the third and fourth mashes, from whence are deducted. Elements for forming, keeping pale strong, and keeping pale small beers. Malt dryness, 119 degrees. Value of hops, 3 degrees. Whole medium, 138 degrees. First mash, 150 degrees. Second mash, 150 degrees. Third mash, 158.5 degrees. Fourth mash, 158.5 degrees. First mash, 14.5 barrels, first wort. Second mash, 14.5 barrels, first wort. Third mash, 11 barrels, second wort. Fourth mash, 11 barrels, second wort. That this method of applying the heats to the mashes corresponds to the medium heat, which is to govern the whole process, the circumstances required in page 165, the following operation will prove. 29 barrels, the first wort, heated to 150, 1450, 29, 4350, 22 barrels, the second wort, heated to 158.5, 11, 176, 110, 22, 3487, 4350 whole quantity of water. Barrels 51, 7837, 153, the mean heat of 4 mashes. 51, 2 deducted for the heat lost at the tap. 273, 151, heat of the tap spending. 255, 119, malt dryness. 187, 270, 153, 135, mean heat of malt's dryness of the extracts. 3, value of hops. 138, mean heat of the whole process. Admitting of the necessary variations in the medium heats, which are to govern processes for different purposes, and of those in the number of degrees forming the constituent parts of the must, in proportion as the drinks are to be formed, either to become spontaneously fine, or made so by precipitation, or intended for a longer or shorter duration. This rule will be found universally true when beers are brewed with 2 worts, but when, for the benefit of the drink, or on account of the smallness of the utensils, as is often the case, when the second mode of extraction is put in practice, we are obligated to carry on the process with 3 worts. These proportions must necessarily be altered, and the following have, in this case, been found most advantageous. The first and second wort ought to have 2/3 of the water. The first wort 2/3 of this quantity, the second remainder of this, and the third wort 1/3 part of the whole. Porter or brown beer is the sort of drink in which this division is most commonly observed. Let the whole quantity of water to be used be that of the brewing, of which the elements have been laid down, page 233, or 54 barrels. 54 times 2, 108, 36 times 2, 72, 24 barrels of water for the first wort, 12 barrels of water for the second wort, 18 barrels of water for the third wort, equals 54 barrels. The last degree for this drink is, with malt dried to 130 degrees, 165 degrees. The first, as per page 178, 155 degrees. Their difference, 10 degrees. Times 2, 20. 7 times 2, 14. 5, heat of first wort. 5 degrees to be proportioned in the first wort, and these deducted from 7 degrees, the number allowed for the first and second wort, there remains 2 degrees for the second wort, and 7 degrees deducted from 10, the whole difference, leaves 3 degrees to be proportioned in the third and last wort. A grist of 11 quarts of malt is too large to admit of the water allowed for the first wort to be equally divided between the first and second mash. Therefore, rather than use the whole 24 barrels in one mash, a sufficient quantity only must be applied to the first mash, both to work it and to get as much of the extract to come down, and will save the bottom of the copper it is to be pumped into. By this management, there will be enough left to form the second extract with, or what by the brewers is termed the peace liquor. The exact quantity of water in the first mash should have, might be referred to the following section, but the order we'll have laid down will excuse our anticipating thereon. It has been found, and will hereafter be proved, that a volume of 11 quarts of malt, dried to 130 degrees, is equal to 6.32 barrels of liquid measure. That malt in general requires twice its volume of water to wet it, and this quantity of water is retained after every tap is spent. 6.32 barrels, volume of the 11 quarts of malt, times 3, 18.96, minus 6.32, 12.64 barrels of water imbibed by the grist, which, deducted from 24, whole quantity of water allowed for the first wort, remains 11.36 extract, which will be yielded from the first and second mash, 3.78 length of the first piece, which is sufficient to save the copper, 3.78 plus 12.64, quantity imbibed as above, equals 16.42, quantity of water for the first mash, plus 7.58, quantity of water for the first mash, equals 24 whole quantity. The elements of this brewing, as we have seen them, page 178, placed in a progressive state, will be as under, where the quantity of water allowed for the first wort is divided into 2 mashes, according to the circumstances just now taken notice of, where the second wort is formed by 1 entire mash, and the water allotted to the third wort is separated equally into 2 parts. For the 2 last mashes, and when the 10 degrees of heat, the difference between the first and last heats employed, are as near possible proportion to the lengths of the worts. Malt's dryness, 130 degrees. Value of hops, 4 degrees. Whole medium, 148 degrees. First mash, 155 degrees. Second mash, 160 degrees. Third mash, 162 degrees. Fourth mash, 164 degrees. Fifth mash, 165 degrees. First mash, 16 barrels. Second mash, 8 barrels. Third mash, 12 barrels. Fourth mash, 9 barrels. Fifth mash, 9 barrels. But for the reasons alleged in page 236, they admit of the following variation. Elements for brewing brown beer or porter. Malt's dryness, 130 degrees. Value of hops, 4 degrees. Whole medium, 148 degrees. First mash, 158.5 degrees. Second mash, 157.5 degrees. Third mash, 162 degrees. Fourth mash, 164 degrees. Fifth mash, 165 degrees. First mash, 16 barrels and 1 wort. Second mash, 8 barrels and 1 wort. Third mash, 12 barrels, 2 worts. Fourth mash, 9 barrels, 3 wort. Fifth mash, 9 barrels, 3 wort. As, if proved as before, the same correspondence will be found with a medium governing heat. The third mode of extraction is intended for a drink which is soon to be ready for use, in which, in the coldest season of the year, transparency is expected, and, in the hottest months, soundness. To procure these intents, we have already shown, page 191, it was necessary to vary the medium heats governing these several processes, in proportion as the seasons of the year differed as to heat and cold. Our present business is a proper division of the whole quantity of water necessary for brewing into the respective worts and mashes, and to apply to each the adequate degree of heat. One single example will suffice for the operation, and the whole variety this drink is subjected to will be expressed in the table subjoined. The general practice to brew common small beer, and which is best, is to form with it 2 worts and 4 mashes, and, in this case, as was before practiced for keeping pale beers, in order to allow for the water at first absorbed by the grist. 4/7 of the whole quantity is required for the first wort, and the remainder for the second wort, dividing these quantities again into equal parts for their respective mashes. As a speedy as spontaneous placidity is expected in every season of the year, and as every means for producing this without affecting the soundness of the drink must be put in practice, and the whole number of constituent parts are not only applied, but likewise the progressive heats suffered to take place. For here, through necessity, we are compelled to forsake the rules nature pointed out, as in pages 64-65. The reasons why are obvious. This drink receives no benefit by the slow progress nature recommends, and therefore very little by the impressions of time. In page 232, we found the whole quantity of water to be used for the brewing there specified, 51 barrels, and in page 191, we find when the heat of the air is at 60, the first heat is 154, the last 174 degrees. Water, 51 barrels multiplied by 4, divided by 7, 204. Gives 29 for the first wort, and this is deducted from 51, leaves 22 for the second wort. The 29 barrels divided into the first and second mashes will be 14 barrels and a half for each, and the 22 barrels, equally divided by the third and fourth mashes, is 11 barrels each. The last heat for this brewing of common small beer is 74 degrees. The first heat, 154 degrees. Their difference, 20, multiplied by 4, and divided by 80, leaves, to avoid fractions, nearly 12. To be proportioned in the first wort, and 8 degrees, the remainder of the 20, to the second wort, in a regular progressive state. The elements for this brewing are malt's dryness, 130 degrees, value of hops, 2 degrees, whole medium, 148 degrees, first mash, 154 degrees, second mash, 166 degrees, third mash, 170 degrees, fourth mash, 174 degrees. First mash, 14.5 barrels, first wort. Second mash, 14.5 barrels, first wort. Third mash, 11 barrels, second wort. Fourth mash, 11 barrels, second wort. The quantity of water used for brewing small beer is in proportion to the largeness of the grist and the price of the grain. This admitting of almost an endless variety, it is needless to pursue it. But the dryness of the malt, the value of the hops, the medium governing the process, and the heat of the extracts being fixed, and constant degrees of the heat in proportion to that of the air, I have constructed the following table, which will be found useful to the practitioner in every season of the year. Heat of air, 35. Malt's dryness, 122. Value of hops, 1. Whole mash, 135. First mash, 138. Second mash, 150. Third mash, 154. Fourth mash, 158. Heat of air, 40. Malt's dryness, 124. Value of hops, 1. Whole mash, 137. First mash, 140. Second mash, 152. Third mash, 156. Fourth mash, 160. Heat of air, 45. Malt's dryness, 125. Value of hops, 1. Whole mash, 140. First mash, 145. Second mash, 157. Third mash, 161. Fourth mash, 165. Heat of air, 50. Malt's dryness, 127. Value of hops, 1. Whole mash, 143. First mash, 149. Second mash, 161. Third mash, 165. Fourth mash, 169. Heat of air, 55. Malt's dryness, 129. Value of hops, 1.5. Whole mash, 146. First mash, 152. Second mash, 164. Third mash, 168. Fourth mash, 172. Heat of air, 60. Malt's dryness, 130. Value of hops, 2. Whole mash, 148. First mash, 154. Second mash, 166. Third mash, 170. Fourth mash, 174. The last business of this section is to divide the quantity of water requisite to brew pale ales or amber, and to apply to such divisions their necessary degrees of heat. This liquor is rather an effort of art than an extract imitation of nature, as in it the greatest transparency, joined to the greatest strength, is expected in a very short time. To obtain these ends, the whole number of the constituent properties of malt and 2 mashes only are employed. In the first, in order to favor its pellucicity, the lowest adequate extracting degree must be used. And in the second, to cause the malt to yield the whole of its necessary parts, the highest fitting heat must be applied. The whole of the process is, nevertheless, subjected to the governing medium heat of 138 degrees, the highest which admits of voluntary brightness. But where a drink is formed with 2 mashes only and boiled off 1 entire wort to keep the due proportion between the quantity of water used and the heat required in the extracts, and at the same time to allot the proper quantity for which is imbibed by the grist, the most convenient division found will be 3/5 of the whole quantity of water to be applied to the first mash, and the remaining 2/5 to the other. I know to this, custom may be objected that the first mash for amber should be a stiff one, in order the better to retain the heat. But this, in the division here proposed, may equally be obtained by a proper allowance made in the intemperating of the water without affecting the proportion of the heats required, as otherwise must be the case. From 8 quarters of malt to make 13 barrels of fine ale. 13 length, half, boiling half hour, equals 12.5 wastewater, 26 whole water employed, multiplied by 3, equals 78. Divided by 5 gives 16 barrels for the first mash and leaves 10 barrels for the second mash, the lowest heat being required in the first extract and the highest in the last, according to page 194. For the 16 barrels, it will be 144, and for the 10 barrels, it will contain 164 degrees. But as the heat of the air occasions a difference in the quantities of hops to be used, and from hence the extracts are somewhat varied, it has been judged convenient to add the following table. A table of the elements for forming pale ale or amber at every degree of heat in the air, with the allowance of 2 degrees of heat in the first and last extractions. Heat of air, 35. Malt's dryness, 120. Value of hops, 1/2. Medium heat of the extracts of the malt's dryness, 138. First heat, 147. Last heat, 167. Heat of air, 40. Malt's dryness, 120. Value of hops, 3/4. Medium heat of the extracts and of malt's dryness, 138. First heat, 146. Last heat, 167. Heat of air, 45. Malt's dryness, 120. Value of hops, 1. Medium heat of the extracts and of malt's dryness, 138. First heat, 146. Last heat, 166. Heat of air, 50. Malt's dryness, 120. Value of hops, 1.5. Medium heat of the extracts and of malt's dryness, 138. First heat, 145. Last heat, 165. Heat of the air, 55. Malt's dryness, 120. Value of hops, 1.5. Medium heat of the extracts and of malt's dryness, 138. First heat, 145. Last heat, 165. Heat of air, 60. Malt's dryness, 120. Value of hops, 2. Medium heat of the extracts and of malt's dryness, 138. First heat, 144. Last heat, 164. In summer times, it's sometimes thought better to brew this drink with malts more dried. For convenience's sake, I here insert 2 examples. Heat of air, 60. Malt's dryness, 122. Value of hops, 2. Whole medium, 138. Heat of first mash, 142. Heat of last mash, 162. Heat of air, 60. Malt's dryness, 124. Value of hops, 2. Whole medium, 138. Heat of first mash, 140. Heat of last mash, 160. For the management of small beer made after amber, see page 197. Thus, having shown how to ascertain the quantities of the malt, the hops, the water, and the heat to be used, and to proportion them to each other, as the good or bad properties of beers arise from these extracts, and fire is the governing agent, we must now seek the means to administer the right portion of heat, and so to temper the water that is to form the extracts, as to not be disappointed of our intentions. In the calculations made by this purpose, not only the water and the copper, but the value and effect of the grist as to heat and cold must be considered. End of section 25. Recording by Matthew Newell.
Section 26 of The Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE, Section 26, An Inquiry into the Volume of Malt in order to reduce the grist to liquid measure. The gallon by which malt is measured, though less, is nearly of the same capacity with that which is used for beer or water. The quarter of malt contains 64 gallons of this measure, and the barrel within the bills of mortality, according to the gauges used by the excise, contains 36 gallons, but without the bills, 34. Though the first quantity is the measure for sale throughout the kingdom. Hence it would appear that proportioning the grain to the barrel of water would be no difficult undertaking. This, however, is so far from being the case that, after having made use of several calculations to help us to the true proportions, we shall find they want the corroborating proofs of actual experience to be entirely depended upon. The ultimate parts of water are so very small as to make this, as well as all other liquids, appear to the eye one continued uniform body, without any interstices. This cannot be said of malt laying together, either whole or ground. There are numbers of vacancies between the corns when whole, and between the particles when ground. But for our present purpose, the volume occupied by any quantity of malt is properly no more than the space which would be occupied by every individual corn, either whole or cut asunder, were they as closely joined together as water. To determine with precision the quantity of cold water to be added to that which is brought to the boiling point, an act by the brewers called cooling in, it is necessary to know what proportion a quarter of malt bears to the measure of a barrel of water. Several operations will be found requisite to come to this knowledge, namely, to take several gauges of different brewings, more especially in the first part of the process, to be well acquainted with the degree of dryness of the malt used, the heat of the first extract, and the quantity of liquor the mash tun holds upon every inch, to find out what degrees of expansion are produced by the different degrees of heat in the first mash, how much less water the mash tun holds upon an inch when hot than it does when cold, what quantity of water is lost by evaporation, and in what proportion at the several terms of the process. In order to put this in practice, the gauges of the following brewings were taken: 5 quarters of malt dried to 125 degrees. The quantity of water used for the first mash was 12 barrels, 2 firkins, 3 gallons. The malt and water gauged together in the mash tun just before the tap was set, 25.0 inches. Allowance for the space under the false bottom boards of the mash tun as near as could be computed, 0.66 inches. The goods gauged in the mash tun after the first tap was spent, 15.41 inches. First piece gauged in the copper, 8 barrels, 0 firkins, 2 gallons. The water employed for the second mash was 12 barrels, 2 firkins, 3 gallons. The grist gauged with this water just before the tap was set, 30.62 inches, and just after the tap was spent, 15.63 inches. The first wort consisting of these two pieces gauged in the copper, 21 barrels, 2 firkins, 0 gallons. The water used for the third mash was 8 barrels, 3 firkins, 6 gallons. Just before the tap was set, the grist with this gauged in the mash tun, 24.60 inches, and just after the tap was spent, 15.20 inches. The water used for the fourth mash was 8 barrels, 3 firkins, 6 gallons. The mash gauged just before the tap was set, 24.60 inches, and just after the tap was spent, 15.16 inches. The heat of the first extract was 136 degrees, to which adding 2 degrees for what is lost by the tap spending, the true heat of the mash is 138 degrees. The first extract, before it is blended with hops, may be estimated to be nearly as strong as a first wort of common small beer. This, when under a strong ebullition, raised the thermometer to 216 degrees, and 7 barrels of such a wort, when boiling, occupied an equal space with 9 barrels of cold water, at the mean temperature of 60 degrees. Now, if the degrees of expansion follow the proportion of those of heat, the following table, constructed upon this supposition, will show how many barrels of cold water would be necessary to occupy the same space with 7 barrels of wort of different heats. Degrees of heat, 216, barrels of cold water, 9, barrels of wort, 7. Degrees of heat, 206, barrels of cold water, 8.87, barrels of wort, 7. 196 degrees, 8.75 barrels of cold water, 7 barrels of wort. 186 degrees, 8.62 barrels of cold water, 7 barrels of wort. 177 degrees, 8.50 barrels of cold water, 7 barrels of wort. 167 degrees, 8.37 barrels of cold water, 7 barrels of wort. 158 degrees, 8.25 barrels of cold water, 7 barrels of wort. 148 degrees, 8.12 barrels of cold water, 7 barrels of wort. 138 degrees, 8.0 barrels of cold water, 7 barrels of wort. 127 degrees, 7.87 barrels of cold water, 7 barrels of wort. 119 degrees, 7.75 barrels of cold water, 7 barrels of wort. The quantity of water evaporated in a brewing when not in immediate contact with fire is more considerable than it is generally apprehended to be. After repeated trials, I have found that what was lost in this manner amounted nearly to 1/5. Now, since the heat of the first tap was 138 degrees, and my mash tun holds 20.25 gallons upon an inch, the following proportion may be deduced from the preceding table. If 8 barrels cold water is to 7 barrels wort, then 20.25 gallons per inch times 7 divided by 8 is equal to 17.71 gallons per inch. and this is the true quantity contained in 1 inch at a heat of 138 degrees. The quantity of water used for the first mash was 12 barrels, 2 firkins, 3 gallons, or 428 gallons, of which 1/5 is supposed to be steamed away when the first liquor is gone through the whole process of the extraction. But as the gauges of the malt and water together are taken before the tap is set in the beginning of the process, the whole evaporation ought not to be deduced, and 1/6 seems to be a sufficient allowance on this account. We may therefore suppose 357 gallons to be in the mash tun at the time of gauging, which number, being divided by 17.71, will show how many inches are taken up by the water at that heat. 357 gallons divided by 17.71 gallons per inch equals 20.15 inches. The mash gauged just before the tap was set, 25 inches. Allowed for the space under false bottoms, 0.66 inches equals 25.66 inches. Deduct the inches taken up by the water, 20.15 inches, equals remainder for the 5 quarters of malt, 5.51 inches, or 1.10 inch for 1 quarter. This number being multiplied by 17.71, the quantity of gallons contained upon 1 inch at this heat will give 19.48 gallons for the volume of 1 quarter of this malt. There now remains nothing but to bring a barrel of water of 34 gallons, under like circumstances as to expansion and evaporation, with these 19.48 gallons, with this difference only, that as the proportion required is at the time the water and malt first come in contact, and not after the mash has been worked, a less allowance for steaming will be sufficient, and may well be fixed at 1/7. Gauge within the bills of mortality. If 7 barrels wort is to 8 barrels water, then 36 gallons times 8 divided by 7 equals 41.14 gallons, minus 5.87 gallons lost by steam equals 35.24 gallons. Gauge without the bills of mortality. If 7 barrels wort is to 8 barrels water, then 34 gallons times 8 divided by 7 equals 38.85 gallons, minus 5.55 gallons lost by steam equals 33.30 gallons, the barrel of water reduced. And as 19.48 gallons under the same circumstances were found equal to 1 quarter of malt, the following division will show the proportion between them. Within the bills of mortality, 35.24 gallons divided by 19.48 gallons equals 1.81 quarters. Without the bills of mortality, 33.30 gallons divided by 19.48 gallons equals 1.70 quarters. Thus, in malt dried to 125 degrees, the quantity of 1.70 quarters is required to make a volume equal to 34 gallons, or a barrel of water, according to the excise gauging without the bills of mortality, and the quantity of 1.81 quarters is required to make a volume equal to 36 gallons, or a barrel of water, according to the excise gauging within the bills of mortality. The more the malt has been dried, the larger the interstices are between its parts. The quantity of water it admits will consequently be greater than what is absorbed by such as is less dry. More of this last malt will be necessary to make a volume equal to that of the barrel of water, and every different degree of dryness must cause a variety in this respect. It will therefore be proper to repeat the operation with a high-dried grist. Gauges of a brewing of 8 quarters of malt dried to 140 degrees. The water used for the first mash, 11 barrels, 2 firkins, 4 gallons. Malt and water gauged together in the mash just before the tap was set, 26.25 inches. Allowed for the space under the false bottom of the mash tun, 0.66 inches. Goods gauged in the mash tun after the first tap was spent, 22.36 inches. First piece gauged in the copper, 5 barrels, 0 firkins, 0 gallons. The water for the second mash was 11 barrels, 2 firkins, 4 gallons. The mash gauged just before the tap was set, 35.70 inches. Just after the tap was spent, 22.19 inches. The wort made of these 2 pieces gauged in the copper, 17 barrels, 0 firkins, 0 gallons. The water used for the third mash was 8 barrels, 3 firkins, 6 gallons. The mash gauged just before the tap was set, 31.10 inches, and just after the tap was spent, 21.77 inches. The water used for the fourth mash was 8 barrels, 3 firkins, 6 gallons. The mash gauged just before the tap was set, 30.50 inches, and just after the tap was spent, 21.60 inches. The heat of the first extract was 142 degrees. Now, by the table of expansions, page 256, if 8.05 barrels cold water is to 7 barrels wort, then 20.25 gallons of cold water upon an inch in mash tun times 7 divided by 8.05 equals 17.60 gallons will be the real quantity of water upon an inch in the mash tun when heated to 142 degrees. Quantity of water in the first mash, 11 barrels, 2 firkins, 4 gallons, equals 395 gallons, minus deduction for the evaporation at this period, 1/6, 65.83 gallons, equals 329.17 gallons, true quantity of the water for the first mash, which must be divided by the real quantity of water contained upon an inch in the mash tun. 329.17 gallons divided by 17.60 gallons per inch equals 18.70 inches taken up in the mash tun by the water used in the first mash. The mash gauged just before the tap was set, 26.25 inches. Allowed for the space under the false bottoms, 0.66 inches, equals 26.91 inches minus inches taken up by the water of the first mash, 18.70 inches, equals space occupied by these 8 quarters of malt, 8.21 inches of mash tun, divided by 8 equals space occupied by 1 quarter, 1.02 inches per quarter, times 17.60 gallons of water equals 17.9520 gallons of water equal in volume to 1 quarter of this malt. Excise gauge without the bills of mortality. If 7 barrels wort is to 8.05 barrels of water, then 34 gallons times 8.05 divided by 7 equals 39.10 gallons expansion of the barrel of water, out of which 1/7 is to be deducted for evaporation, 5.58 gallons, remains 33.52 gallons for the barrel of water reduced, which the quarter of malt, or 17.95, is to be compared to. Excise gauge within the bills of mortality. If 7 barrels wort is to 8.05 barrels water, then 36 gallons times 8.05 divided by 7 equals 41.44 gallons expansion of 1 barrel of water, less 5.92 gallons, 1/7 to be deducted for evaporation, equals 35.52 gallons, barrel of water reduced, which the quarter of malt, or 17.95, is to be compared to. 33.52 gallons divided by 17.95 gallons equals 1.86 quarters, quantity of malt dried to 140 degrees equal to 1 barrel of water. 35.37 gallons divided by 17.95 gallons equals 1.97 quarters, quantity of malt dried to 140 degrees equal to 1 barrel of water, according to the excise gauge within the bills of mortality. Having found the volume of malt at 2 distant terms of dryness, we might divide the intermediate degrees in the same manner as we have done before, could the certainty of these calculations be entirely depended upon. But as some allowances have been made without immediate proof, how near soever truth the result thereof may from experiments appear, it may be proper to point out what is wanting to make our suppositions satisfactory. Some part of the calculation depends on the quantity evaporated. This, in the same space of time, may be more or less, as the fire under the water is brisk or slow, or as the weight of the atmosphere differs. The gauges are taken at the time the malt and water are in contact, and more or less water may be imbibed in proportion both of the dryness and age of the malt. Water as a fluid, malt as a porous solid body, must differ in their expansion, but in what proportion is to me unknown. Effervescence may be another cause of want of exactness. The different cut the malt has had in the mill, its being or not being truly prepared, and lastly, the difference as to time of the mashing or standing of the grist, prevent our relying wholly upon the calculation. It is, however, not improbable that some of these incidents correct one another. Since 1.70 quarter of malt dried to 125 degrees are equal to 1 barrel of water, and 1.86 quarter of malt dried to 140 have the same volume, the difference being but 16 parts out of 100, the whole of the error cannot be very great, and 1/4 6 bushels of malt may, at a medium, be estimated of the same volume with 1 barrel of water. But as experience is the surest guide, I have, from a very great number of different brewings, collected the following proportions, and repeatedly found them to be true. I have added in the table the weight malt ought to have at every degree of dryness. A table showing the quantity of malt of every degree of dryness equal to the volume of 1 barrel of water, and of the mean weight of 1/4 in proportion to its dryness. Barley, degree of dryness 80 degrees. Excise gauge without the bills, volume of grain 1.56. Excise gauge within the bills, volume of grain 1.59. Weight in pounds 376. Degree of dryness 100 degrees. Excise gauge without the bills, volume of grain 1.62. Excise gauge within the bills, volume of grain 1.63. Weight in pounds 306. 105 degrees. Without the bills 1.62. Within the bills 1.67. 301 pounds. 110 degrees. Without the bills 1.65. Within the bills 1.71. 296 pounds. 115 degrees. Without the bills 1.67. Within the bills 1.75. 291 pounds. Malt 119 degrees. Without the bills 1.68. Within the bills 1.79. 286 pounds. 124 degrees. Without the bills 1.71. Within the bills 1.83. 281 pounds. 129 degrees. Without the bills 1.74. Within the bills 1.87. 276 pounds. 134 degrees. Without the bills 1.77. Within the bills 1.91. 271 pounds. 138 degrees. Without the bills 1.80. Within the bills 1.95. 266 pounds. 143 degrees. Without the bills 1.83. Within the bills 2.00. 261 pounds. 148 degrees. Without the bills 1.86. Within the bills 2.03. 256 pounds. 152 degrees. Without the bills 1.89. Within the bills 2.07. 251 pounds. 157 degrees. Without the bills 1.92. Within the bills 2.11. 246 pounds. 162 degrees. Without the bills 1.95. Within the bills 2.15. 241 pounds. 167 degrees. Without the bills 1.98. Within the bills 2.19. 236 pounds. 171 degrees, without the bills 2.01, within the bills 2.23, 231 pounds. 176 degrees, without the bills 2.04, within the bills 2.27, 226 pounds. With a table thus constructed, it is very easy to reduce every grist to its proper volume of water. Suppose those of the brewings we have already mentioned. That of the small beer consists of 6 quarters of malt dried to 130 degrees, the proportion of which in the table is as 1.75 to 1. If 1.75 quarters of malt is to 1 barrel of water, then 6 quarters of malt is equivalent to 3.42 barrels of water. These 6 quarters of malt occupy therefore an equal volume with 3.42 barrels of water. A brown beer grist of 11 quarters dried to 130 degrees. The proportion of this in the table is as 1.74 to 1. If 1.74 quarters of malt is to 1 barrel of water, then 11 quarters of malt is equivalent to 6.32 barrels of water. The volume of these 11 quarters of malt is therefore the same with that of 6.32 barrels of water, and the whole being brought to one denomination, we are enabled to find the heat of the first mash. But the effervescence occasioned by the union of the malt and water must prevent this calculation being strictly true, the consideration of which shall take place hereafter. The circumstances are different in the other mashes. The waters used for these meet a grist already saturated, and the volume is increased beyond the quantity found for dry malt. The quantity to be allowed for this increase cannot be determined by our former calculations, and new trials are to be made in order to fix upon the true proportion. Gauging is undoubtedly the most certain method of proceeding in these researches, but even this becomes less sure on account of the expansion, evaporation, effervescence, and other incidents already mentioned. Our errors, however, cannot be very considerable when we deduce our conclusions from numerous and sufficiently varied experiments. The volume of the grist of pale malt was found, after the parting of the first extract, to be 15.41 inches, though the space occupied by the malt, when dry, was only 5.51 inches, and the volume of the brown grist at the same period was 22.36 inches, though the dry malt filled only a space of 8.21 inches. The proportion in both these cases, and in all those which I have tried, answers nearly to 1/3, so that the volume of the grist in the second and all subsequent mashes may be estimated at 3 times the bulk of the malt when dry, and this is sufficiently accurate for the operations of brewing, in which, for conveniency's sake, the application of whole numbers should be effected. As it is found by the gauges that the goods, after the several taps are spent, remain sensibly of the same volume, or at least very little diminished, may we not conclude the parts absorbed by the water, in which the virtue of the grain and the strength of the beer consist, are contained in an amazing small compass? It is indeed true that hot waters and repeated mashes do swell somewhat the hulls and skins of the malt, but no allowance made for this increase will be sufficient to remove the cause of our surprise. End of section 26.